the one we saw that was the worst tube, or the worst tube, the one with the defects, as we saw on the previous slide, you can see it yields at about half of what the bad tube yielded at. So 40, 45 kilonewtons instead of 90, which is not what we expected at all. This could be due to two reasons. This tube was much shorter than the previous one, since polymers get all their strength from the length of the fibers. If you cut the fibers short, they're not going to do much. Like if you've ever had just like held like a piece of fiberglass and it's really small, you can see it like it just like falls apart. And the other thing is we couldn't guarantee that the samples were actually flat across the top, so we couldn't guarantee that the load was applied evenly. Because the Instrom is just such a precise machine, it's so flat. We can't, with our like 120 grit sandpaper, we can't do that well. So that was pretty interesting to us. But we still flew this rocket, and the rocket launched nominally at IREC, so we know that this is an acceptable test. This is fin results. It's good because it's pretty linear relationship. You can see when like that wasn't actually failure. You can see when we just took the load off. Basically, since our plates are like this thick, so like they're pretty thick for fins. So the fibers just kept breaking, but since there were so many layers built up, it was able to make a full recovery. Again, this is not indicative of what would happen during launch, not indicative of flutter conditions. But we got the Young's modulus and it was around 50 gigapascals, which we can use, which is important because we can use them in our FinSim aerostatic analysis. In FinSim, you can input a user-defined material, and from the testing, we can get all of these different values, which allow us to get the flutter pretty accurately, where by using our own materials instead of values we find online. So our flutter is about 1.7 times the speed that we're actually going, which is about 1,000 feet per second is our max velocity. So flutter is not at all a risk, which is great news, having lost a rocket to flutter before. Yeah, future work is pretty important in this case. We want to find the optimized layer count, fiber orientation to just achieve desired strength and performance. This will allow us to save time and materials, reduce drag on the fins, and most importantly, reduce mass on the rocket. As QRET's moving towards a hybrid rocket, mass plays a pretty important role in the success of the hybrid rocket. And you can't just buy a better motor as we have been doing before to suit your needs. You actually need to build a better rocket, and building is much harder than buying. We also want to characterize the impact of rate loading for composite materials. So this can involve talking to a faculty advisor to get their input into it, and just doing more research into the subject. The other thing is we want to standardize our procedures. So we have like years of data that we can compare them to and see if we are improving, see if our values that we're getting now are comparable to the ones we got in years past. And yeah, make sure that we are continuously improving and not just building the same thing every year, because that would just be a waste of time. That brings me to my end of the presentation. If we have time for questions, you can ask them. If not, reach out.
Great presentation. Great. 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 Let's test. Test. First of the day. Hello. Okay, great. Great presentation. Thank you. I love the blend of theory and practice and justification of how that's going to help for the future. Do we have any questions from the audience? Awesome. I'm going to come to you. And I love how your TA couldn't understand your context of testing. It's quite fitting to Rocketry.
I might have missed it, but did you find vacuum bag versus like hand layups completely different? Did you do testing on both vacuum bag and hand layup stuff? And was it worth the extra money to actually do vacuum infusion?
So currently all of our layup processes are like just wet layup. We don't vacuum anything but our plates. So we don't do vacuum infusion. And since we didn't actually, this is like preliminary testing, we didn't make materials to test. We didn't actually we didn't see the difference because we didn't have anything to test it against.
Great answer. Any other questions at the back? Oh. We do have to speak in the mic just for the live stream, so I know you're close, but
Great presentation, Emma. The 50 gigapascals for the fins that we found, how did that compare to kind of default values? Like, do you know how that compares to kind of what we were expecting?
My colleague did a lot of the number crunching, so I don't know exactly what it is, but I think it's comparable to values that we've gotten years past. And again, it's not really the point of just how comparable it is important, but we're going to use this anyways. We need to characterize the material. So.
Based on your experience, do you have recommendations for trying to make non-isentropic materials more closer to your isentropic approximations?
Again, I don't. This is a difficult question. Just because I going into third year engineering, I'm not in materials, so I don't actually know that much about. I just know what Excel puts out for me. So yeah, I don't know the difference between what standardized testing would be.
But if I can have a follow-up question to like how to make those simulations more realistic. So you mentioned how you had limitations on the rate of load that you can apply to your material. Do you have any solutions for the future where you can maybe accelerate that loading?
Yeah.
Or approaches, maybe like hammer testing, or I'm not in materials either, but any approaches that can make it more realistic?
Yeah, definitely talking. Queens has a really big materials department, so talking to faculty who have more industry experience. Currently, we do this testing through the civil department, and they take things much more slowly over there. So they get when I say, yeah, I want you 4 kilonewtons in 1 second, they're like, what are you talking about? So yeah, getting like going in with a plan. When we got there, I had extrapolated the rate from previous things, but I didn't know that you couldn't just apply a force, you applied a deformation. So that was a big thing. I'm like, oh, I didn't know that. I want force. And he's like, we can't do force. We do displacement. And I'm like, I guess that makes sense. That is what you can measure with the machine. So yeah, just knowing more about the machines is more important going into testing.
And is there a way you can modify that approach to increase the loading?
Yeah, you can definitely load it faster. At some point, we were doing 2 inches, 2 millimeters per minute or something, whereas we started with 0.5. So yeah, seeing if the lab techs will allow us to max out the machine, that would be best.
I think at some point at McGill, we just resorted to dropping weights on.
Yeah.
That's the best way to simulate dynamic, quick loading. And I don't think civil takes any dynamic classes, so it's tough on that side.
So there's kind of a wide variety of experience that comes to this competition where people are just getting into this, and it's very recommended that they buy tubes to get started because they're offloading the testing. And the best part is the part you don't have to make, because then it's sort of not your problem.
Yeah.
However, we as engineering students really want to do everything ourselves because we're then getting the experience so we can transfer it later. Your team has a lot of wide experience. At what point do you kind of recommend that teams should make your own tube and start testing it, make your own fins, start testing it?
As I've talked to a lot of teams at this competition, a lot of the barrier for making tubes is not team interest. It's faculty reluctance. The materials that you use is really hazardous. Queens is lucky enough that we have both a layup room and a sanding room that theoretically has proper ventilation, but we also have access to respirators and safety procedures. It's really hard to say to the faculty, hey, we need this. We've never done it before, but we think it would be cool. And they're like, well, we don't have the space for that. We can't allocate safety resources for that. So that's what I found is the biggest barrier. Um, but as soon as there is team interest and as soon as the faculty approves it, I think it's a great idea to not just start making tubes for testing, but start making tubes for rocketry, but start making tubes for testing. Saying like, oh, this is what we want our layup process to be like. This is what other teams have done. Let's try it here, see how it works for us. So yeah, not so much a willingness barrier.
I think in rocketry, especially student rocketry, there's often a triangle where you can only choose two, and it's willing students, willing faculty, and facilities.
Yeah,
And you
yeah.
can never have all three.
Yeah.
Any other questions from the audience? Well, wonderful, Emma from Queen's Rocket Engineering Team. Thank you so much. Okay, so we're a little bit before schedule, so I'm gonna give maybe an overview. I realized I hadn't had the chance to give an overview for the day, so I'm gonna take the next few minutes to do that, and also thank all of our attendees on the live stream. We're very happy to be able to have this set up to help you attend virtually this in-person event. And as I mentioned on the live stream in the chat, feel free to drop questions in the chat. I actually am checking it on the side, and when I get the chance, I can relay your questions to our speakers here. So if you have parents or other people that want to express support, feel free to do so. So for the rest of the day, we have some very interesting talks. So we just had QRED come up stage. Next, we'll have UVic Rocketry, talking about applying selective laser melting aluminum to structural rocket airframes. So thank you for our conference director for grouping aerostructure presentations together. It helps my brain this morning. But then we're going completely in the opposite direction with the next speaker after that, which will be Charlie Garcia at 9:30. He will be representing Reflect Orbital to talk about giant mirrors in space. That's pretty exciting. And then after the break at 10:15, we'll have two tech dev teams. We'll have Queens that will come back for a second presentation to talk about their hybrid engine test time. I'm very looking forward to that. And we have Mark that will talk about their liquid engine test time. We then have at 11, our own conference director, Ariana, will be talking about RDEs, so rotating detonation engines, representing CanDet. And it'll be followed by Oranos Polytechnique, which will be talking about airframe manufacturing, compression molded fins, and filament wound non-constant sections. So that is our morning, a lot of airframe structures and giant mirrors in space. In the afternoon, we'll have Arbalest Rocketry to talk about the development of Goose 4, which is our multi-stage solid rocket. Beautiful finish, by the way, with the black and the red and the different fin sizes. It's quite nice to look at. And we'll have one more tech dev. That'll be the last tech dev of the conference at 1:15 with Rockets, which will be presenting the rocket tracking camera. And that will be the project of Mathieu Gagnon, which has been at Launch Canada for every year so far and doesn't want to retire. So shout out to Mathieu. And then we'll have Adam Lackman from Airjet Rocketdyne, who has been, I think, the chief engineer of Airjet Rocketdyne for a couple of years, and is a great LinkedIn influencer to follow. Makes a lot of fun jokes. I don't follow a lot of influencers, but Scott Manley and him are two people that I quite enjoy. And the last student talk of the day will be by, actually not student talk of the day, last talk of the day before the keynote will be by Mac Tafazoli from Transport Canada, which will talk about orbital launch safety. And we will be presenting it only in person. It won't be on the live stream. Confirm that, Ariana? It will only be in person. So a little gift to all of you that have traveled all the way to Timmins. We'll have a break then, and it will be followed at 3:15 by our keynote speaker, the MDA keynote. I think it will be Dave Mann, who will be coming for this speech to Timmins, and we'll talk about our future in space. So hopefully we'll have all of you there to talk about our future in space. So now we have a 5-minute break, and we'll be back at 9 a.m. for UVic Rocketry to talk about applying selective laser melting aluminum to structural rocket airframes. Thank you very much.
Check. Is the TV in the way? No.
Okay. Hello, Launch Canada. Welcome back to this next presentation. The next speaker I have kind of a bias for because I say it every year, but the next speaker is University of Victoria Rocketry, or UVR. Is that the right way to say it? UVR. Wonderful. They are the team that has traveled the longest distance to be here today, right? They have crossed not only the entire country, but also water before crossing the entire country. So shout out to UVR. I don't know how you guys are getting back with the Launch Canada strikes. You're driving, I guess? Driving back? Flying with Porter? Nice. That's being smart. That's rocketry. We're thinking in advance. We're planning for everything. Planning for Murphy's Law. Maybe, we'll figure it out. But all of that to say, we're very grateful to have you here. Thank you. and it wouldn't be Launch Canada without UVic and all of the West Coast as well. So on that note, I will introduce the team. The University of Victoria Rocketry team is a student-led group at the University of Victoria that designs and builds competitive-sounding rockets. The multidisciplinary team provides students with hands-on experience in designing, manufacturing, testing, and launching and recovering high-powered rockets. This year's presentation focuses on using selective laser melting to produce aluminum airframe components. I'm quite excited to hear about it. So please, everyone, a warm welcome for University of Victoria.
All right. Thank you, Cyril, for the kind words. Good morning, everyone. Welcome. My name is Julian Edwardson. I'm the team captain of the University of Victoria Rocketry team. Perfect. We have the slides. A little bit closer to the mic. Sounds good. My name is Julian Edwardson. I'm the team captain for the University of Victoria Rocketry team. I'm a fourth-year mechanical engineering student, and I'm here to discuss sort of the student approach to metal additive manufacturing for use in rocket airframes. This is something that we've done for the first time as a team, as the University of Victoria, and it's something that we've been really excited to do, and we've learned a lot doing it, so we really wanted to share it with all of you and share the lessons that we've learned along the way. So we're really, really thrilled to be here. So a couple of definitions before we sort of get going. We're going to be talking about additive manufacturing, but more specifically, we're going to be talking about selective laser melting, and that's the method of sort of depositing aluminum and then melting it into place over the course of multiple layers in order to create very specific geometry in a sort of more solid format than other methods such as, or more porous methods such as direct metal laser sintering. This is one of the fastest growing manufacturing methods that we have available to us today. It's a very modern way of making more complex geometry that has been sort of previously more difficult than a lot of traditional manufacturing techniques. So there's sort of going to be three main pieces of motivation that we're going to be looking at this through as three sort of approaches that we're going to be looking at. The first one is that every manufacturing method we look at is going to have advantages and limitations. We accept that there's no way around those, but we do always look for ways that we can sort of suppress the limitations and leverage the advantages of any given manufacturing format. And that's what we're going to be looking at today for this additive manufacturing method. The second one is that the designer interaction with these benefits and limitations is not necessarily fixed. We control how we use this technology. Just because we're committing to using a certain technological method doesn't mean that we're necessarily committing to a specific manufacturing approach, a specific design approach. And we're always looking for new ways that we can use the same technology to produce results that are better and achieve what we want to achieve. And then the third one that should come across as no surprise is that a better understanding of our manufacturing methods is going to lead to better results in our airframe, better results in the project that airframe is a part of, and a better overall mission result when it comes to sort of achieving the goals that we've set out to achieve. Final sort of thing I want to touch on before we really get going is, why is UVic giving this talk? As I mentioned a moment ago, this is the first time we've done this. So this is our rocket, you can see on screen, Anduril 2. This is a nearly entirely aluminum rocket, and one of the cornerstones, one of the key pieces of this rocket is the lower airframe portion, which is an integrated boat tail, fin can, and thrust assembly. So it performs three roles. It performs an aerodynamic role, it performs a fin support structural role, and it performs a thrust transfer role. And those are three really important aspects of the rocket. And they're all in the same place. So it makes that one location, that one component really, really important and really worthy of a lot of analysis and a lot of looking after. And so that's sort of where we've chosen to focus this technology and try to unleash it to solve the set of problems for this. All of the effort that's gone into that has yielded a lot of lessons, and it's yielded a lot of learning onto the team that we've all managed to learn some amazing things about this technology that we can now leverage and try to use in other places, both with this technology and with existing manufacturing methods. So the first part about designing with SLM technology is deciding in the first place that you want to use SLM. That's a major decision that we make, and it's a big commitment to do. And we're going to talk a little bit about why that's such a big commitment and why that's such an important decision to take seriously. So every design starts somewhere. That place is usually a requirement spreadsheet. It's usually where you lay out exactly what you're trying to achieve, what functions this thing needs to perform, and how to best perform those functions. Or how to best perform those functions is what we're looking to resolve. So thinking about the purpose naturally lends itself to thinking about the form and the shape of this object. So in this case, we're looking at an aerodynamic piece. So it's meant to perform a certain function aerodynamically, which means that it has to have a certain shape along the exterior of the rocket. And so we're already thinking about shape, we're already thinking about form. We can now start looking at things like material. And this is sort of the first step in this concept selection is we start looking at, do we want to continue with a traditional design that we've done in the past that we know and have proven works? So on the left-hand side of the screen there, or on the right-hand side of the screen, you'll see there's a more traditional thin can assembly that we flew on our first supersonic rocket versus sort of an alternative design with a more integrated approach using a different manufacturing method. Now that additive manufacturing is becoming taking a more prominent role in aerospace, and it's becoming more affordable, it's becoming more attainable especially for student teams, the cost is coming down. It's a very, very special time to be looking at airframe manufacturing. This has now become an option on the table. We're used to sort of a set of traditional options, but now that this is becoming more accessible, this has now become an option that's on the table, and that makes it quite appealing to start looking at. So if we've identified a shape that we want, and we've identified sort of an ultimate outcome that we want to achieve, we can really look at what material we want to use and sort of look at the set of traditional solutions to this. As many of you, I'm sure, are perfectly aware of sort of tip-to-tip composite layups. It's a very tried and true method of making rockets, a very reliable method. We wanted to try something a little bit different. We wanted to do this approach of an integrated, of a single integrated material, because it means that we can hopefully leverage the material properties, the known repeatable material properties that metal has, and use that for sort of superior analysis that allows us to more reliably predict the outcomes and the performance of this part. So now that we're defining the shape, we can really narrow down our options and select what outcome we want. And if we're happy with metal laser melting, we can really settle on that and really start designing for that particular process instead of just identifying what material we want to use. So now that we've chosen this material property, we can really start thinking about what it is and what it does and what makes it special and how we need to design for it in particular. So we're really used to thinking about additive manufacturing through the lens of sort of 3D printing. It's the most common form of additive manufacturing, plastic 3D printer. Plastic 3D printers are everywhere. They're in homes, schools. They're really accessible, and so it's natural to think about metal laser melting as a sort of extension to that rather than a completely different process. But if we start doing that, all of a sudden we're going to start missing the more intricate differences that really do make a difference in how we actually design the shape of these parts. And that becomes sort of, in a sense, quite dangerous because it allows us to slip into the trap of just thinking that it's another 3D printed part, only stronger. And that misses some really great opportunities that we have with metal laser melting, such as post-processing. It allows us for much better strength treating. We can do heat treatments on it. We can explore all sorts of different options for improving the strengths of these materials after they're manufactured, and then improving the tolerances of these materials after they're manufactured. Two things that are both very important in rocketry, and that we'll touch on in a sec here. So we're looking at the material now, and we're sort of going back to that initial principle that we identified of advantages and disadvantages. And we know that every material comes with them, so we need to really identify what those advantages and disadvantages are through the lens of the project that we've chosen to apply this material to. So with a fin can, these are some of the examples of the parts that we identified that we were experiencing trade-offs for. And so we're identifying things like thin features, we had to print that at a much slower speed, and so that increases the cost. It has a certain risk of warping, so you can have some tolerances degrade over that section of the print. Things like high angle overhangs, they're possible to do with this technology, but they come with a risk of sagging, they come with a risk of tolerance deformation in the z-axis, and they come with an additional level of risk while manufacturing these parts. Other things like mating surfaces, you need to explore, so post-machining, and we'll touch on that in a sec. And then other things just like volume and height, there are restrictions on that with the printers that you're using. And so really thinking about being careful, making sure that we're designing deliberately for a process. And we need to start answering the question sort of, what can SLM do versus what should SLM do in the prospect of like what we've chosen to apply it to. So in an airframe, we're really looking for high strength. We're really looking for high tolerances because this is a part that mates with a lot of other components in the rocket. So we may not want to be attempting to experience these sort of higher risk operations that come with the more experimental uses of this technology, and instead really focus on creating shapes that we can predictably analyze and apply to our rocket. We start to encounter the realities of manufacturing once we actually set out to make this. The biggest reality of manufacturing is, of course, the cost. Once you've committed to SLM, it can be quite challenging because all of a sudden that's a very significant cost, and the design that you've made that is going to take that cost cannot necessarily be easily converted to another manufacturing method. So if you choose a design that is very particularly optimized for this manufacturing method, you run the risk down the line if you decide that you actually cannot be paying for something as expensive as direct metal laser melting. It becomes quite difficult to convert that design to, say, for example, a machine part. It becomes quite difficult to convert that to another manufacturing method that is cheaper without vastly having to modify the design. So as soon as you engage in that manufacturing method, you have to be ready to make trade-offs in other parts of the rocket. So for example, in Anduril 2, this works really well with our design philosophy, where we wanted to make an airframe that was solid aluminum for much of the airframe, including the fuselage. And so we managed to take much of the money that we usually spend on a carbon fiber fuselage, and instead we purchased an aluminum tube and we machined it down to size, and that was vastly cheaper. It cost us just over $100 to make the fuselage, and now we can set aside that approximately $2,000 and put it towards that bottom aerostructure component. So it's just something that as a team you have to be ready for. In order to engage with this technology, you have to be ready for the cost and know where that money's coming from and know that you're ready to make that commitment. The next section to look at is post-machining and tolerances. As we discussed, this is a very high tolerance part because it aligns the fins. Those need to be very well aligned and very repeatable over the entire, all four fins of the rocket. And then the tolerances on the motor mounting and the motor integration need to be very high tolerance in order to properly center the motor. And then furthermore, the mating with the fuselage is also very important because otherwise you can get a leading edge on one side and a trailing edge on the other. The additive manufacturing process has a high tolerance, but it's not that high. So we need to look for other ways to bring it down to the tolerance, bring it down to the size that we're happy with, and that method is post-machining. It's important to identify these locations early on because we need to be ready to we need to know that this is going to be a part that we need to post-machine, and we need to know how we're going to post-machine it, because now it's not just a metal laser melted part. It is now being compounded with a second manufacturing operation that needs to be planned out. So if we don't want that that second machining operation to cost a lot of money, we need to be designing this in a way that we can both optimize it for the laser melting as well as the machining. So we need to have a plan set aside for how we're going to machine these surfaces and how we're going to machine them to the tolerance that we need in order to achieve our goals. So if we leave that to, say, the last minute, it can become quite challenging to identify what your costs are going to rise to. It can be quite challenging to identify whether you're actually going to be able to achieve the tolerances that you're looking for, or the concentricity that you're looking for. And that can be a major programmatic risk if this is such an expensive and critical part of the rocket. Furthermore, if you're a student team and you have equipment to machine yourself, something that we had to think about was, do we want to machine this ourselves? Eliminate the risk of paying for post-machining, but increasing risk of potentially damaging the part and having to pay for a new one. It's just a balance that any team that trying to pursue this technology will have to make. We chose to have the company that was printing this part, we chose to have them machine it to eliminate that risk. But any team might choose to make a different decision if they were more confident that they could hold on to that risk to save a little bit of money. We're going to be looking into optimization strategies here because we're really looking for, that's at the end of the day, so one of the things that we're targeting with this technology and targeting with this material is trying to optimize it for either weight or trying to optimize it for a certain load case that we're really worried about. And so really trying to leverage that technology to avoid those scenarios and make sure that we're prepared for them. So the first step in any of that, though, is obtaining information. So one of the biggest things that we found to be critical when using this technology was that we had to identify the process, the material, the machine, and the temper right out of the gate. And that's really important because any of those variables significantly changes the material properties. So the temper can significantly change your strength. It changes it by approximately 50%, depending on what temper the machine runs. And so you need to be very prepared to know that your strengths might be significantly different if it's tempered versus if you're using it right off the machine. And then other things like just the machine pattern can change the grain of the metal. And you need to be prepared for how that's going to affect it. But things like tempering, things like planning out a deliberate tempering process can take out some of that risk and make you more prepared to actually accept that part and know that it's to the specifications that you designed it to be. So establishing a relationship with that manufacturer is a very important step if you want to use an SLM process. The finite element analysis is very critical, obviously, for analysis. And the great thing about this technology is that this does not differ much from a lot of solid components. If you can successfully do a temper, which we'll talk about in just a sec here, and if you can get a temper that produces a more uniform and a more importantly isotropic material, you can be more confident in your analysis and more confident in your simulations that the part's going to perform as you expect, especially if you can do some validation and testing, which we'll get to in a second. So the validation and testing here is an important part because on any sort of analysis you do, you need to be able to validate your models. In situations like these, you want to be validating on small parts. You do not want to be doing full-scale destructive testing unless you're really willing to pay for the full cost of that component. For a part like this, which costs approximately $4,000, we do not want to do full destructive testing on one of these fin cans. It's not a good use of money. So instead, we're looking at purchasing smaller representative components that represent the regions that we're worried about, and that we can successfully simulate those load cases to know that what we're testing is actually representative of the final part. And that we can, if we can successfully validate the analysis on these smaller pieces, then we can be confident that our process is good, and that we can generalize our process to a broader model, to a model of the full flight hardware under flight conditions. So you see here on the screen, actually, you see two test pieces, and they're two separate test pieces because we want to be able to make sure that the effects of one test are completely isolated from the effects of the other. So the one on the right, the curved one, is a shortened and just a section of the fin can, and it's meant to be epoxied to a plate, and then to test the bending strength of that support, of that fin root support. So that means that we can fully test that specific area, and we can test how the ribs in that fin can are going to support the fin. The other one is for threads. Threads are also a bit of a concern because the material can behave quite differently when it's under the shear from a screw. And so we need to be confident that the screws that are holding this thing into the airframe are going to be able to hold it in and not release it partway through the flight, which would lead to the rocket not coming back in one piece. Keeping these in mind while budgeting is important because these are not cheap. They're cheaper than the full piece, but they're still not cheap. So understanding that you're going to have to do testing, and that testing is also going to cost some money, is important in your initial budgeting. So a lot of this does come down to planning. A lot of it does come down to expecting sort of the costs and then knowing what's coming. Once you've validated this model, you can start to become more confident in your design. You can start to become more confident in the design decisions that you've made, and you can start to apply those and be confident that the actual flight is going to be successful, or that you're going to have a higher factor of safety on that component, and you can be comfortable perhaps lowering that factor of safety in order to cut down on some weight. The final aspect that I think is important to talk about with this technology is not necessarily a technological benefit. It's not necessarily a benefit to the rocket itself. It's a benefit to a team. We live in a time where this additive manufacturing process is becoming more attainable and is going to become a bigger and bigger part of engineering, and especially mechanical engineering in the future. And so we really do, as university teams that are teaching students, we do really want to make sure that we are teaching people and that we are exposing them to not just current manufacturing solutions, which are very important, but we also want to be exposing them to sort of what's coming next and making sure that they're prepared for when they enter the workforce and they're more competitive, and make sure that they can sort of pursue the opportunities that they're really passionate about and know that they've been exposed to the technology that's coming down the line that they're going to encounter in the workforce. That's something we really believe in, and we really encourage other teams to do the same and pursue that technology because it allows it to become broader and more important in the rocketry community as a whole, and makes it more accessible to everyone if it becomes more important to all the teams involved with Launch Canada. So prioritizing your team members, very important, and then really just seeking out these opportunities to innovate is just something we really are looking to do. That's all for me. I hope you've learned something today. If there are questions from the audience, I'm more than happy to take them. Yeah.
Great presentation. I really like how you went through every step of the design of a new project, looking at finances, training, how it affects other projects. It was really complete, and you brought us through the thought process of doing additive manufacturing for that part. So that was very interesting. Do we have any questions from the audience? Okay.
Yes.
Good morning, and thank you very much for that talk. That was excellently done, and Anduril 2 looks sick.
Thank you very
That's
much.
a gorgeous looking rocket. I have a lot of questions about the additive manufacturing process. I'm not as familiar with the space. Specifically, I'm more familiar with laser powder bed fusion, which seems
Okay.
very similar. Is that the same thing as SLM?
I'm actually not. I'm not fully certain on that. My understanding is that the powder bed fusion is sort of the broader term that covers, I believe, both sintering and melting. And so you can. It just depends on how you're binding that material together.
Okay, thank you for the context. And then my follow-up is, is your team wanting to, as you've gathered this experience, carry it forward and explore implementing compliant mechanisms with it, where you're implementing failure modes that will fail predictably to create actuation as a single part? I'm specifically referencing with PLA and plastic 3D printing, there's lots of instances of printing parts that are multiple pieces interlocked, such as, say, chainmail that you can then break apart after taking it out. I'm more thinking, could you lead to roller-ons as one 3D printed thing?
That's a good question. I know one of the concerns with SLM parts is always fatigue failure. So if you have a mechanism that's compliant but meant to be repeatedly used, that would be a serious concern. So for example, we're pretty familiar with the aluminum that we've been using, and it does experience sort of a higher rate of fatigue than even normal aluminum, which is notorious for fatigue failure. But if the mechanism is meant to be sort of repeatedly reused, I think that would be a primary concern. If it's not, I could see it as potentially being an opportunity to like leverage that weakness of the material to allow for like maybe a more predictable break if you can successfully study how that is going to repeatedly fail, and if you can tune the material process and the temper to really be a very predictable material, then you could probably like tune a compliant mechanism quite successfully.
When you were manufacturing the tubes, in my experience of doing that, the aluminum gets hot and wants to expand well in the chuck. So I've had tubes jump off of the machine and very dangerous. What kind of situation did you encounter with those risks?
So that is definitely a very large risk. So they're very thin wall tubes, so they do tend to try and grab the tools on the lathe. The thing we found is running them very slowly with flood coolant all the time, and that sort of helps prevent that safety risk and helps mitigate the risk from that machining process.
Amazing. Did you find that you had, going back to the 3D printing, any sort of minimum radii that you were unable to go below? I'm more familiar with orifice diameters, but I'm assuming the same thing applies to your leading edge of the fins.
So, sorry, the leading edge of
the leading edge of your fins, or the trailing edge, but a minimum radii that it cannot go below?
So we actually machined the fins to like a fully sharp point, and then just deburred them afterwards to bring them to something that's less less prone to damage. The angle is also sort of fairly wide that you don't need to take off very much material sort of in the axial direction in order to bring it to a more rigid state. And so you can get sort of a very similar geometry to your intended analyzed geometry, which is sort of, I guess, like a perfect point, at the cost of a very small geometric change. And you make sure that it's still quite rigid.
Wonderful. We have time for one more question. I do have one, but I just want to see if the crowd has one. My question for you is, so the entire presentation, you were talking about the cost. You were talking about the part and how it's expensive. You have to budget for it. And in my head, I was just thinking testing, validation. You still have to like test it, right? You have to destructively test it to prove it. And then you talked about making sections, and that's cheaper. How do you select those sections, to be representative of the rest of the fin can under that destructive testing to bring value to that test so that you can actually extrapolate it, as you were saying, to the whole fin can?
Yeah, for sure. That's a really good question. There's a certain iterative process that you have to follow, because when you first start off with a design, you won't know where those failure points necessarily are. But once you get sort of a first design going, and you can do even just a preliminary simulation of your structure, then you can start to narrow down quite quickly actually where your failure modes are going to be. And you can sort of test a whole length. So for example, we showed sort of a compressed version of the full length of the fin can. And so that allows us to test that fin section. And as we're pressing it, we don't actually know where along that fin support area it's going to fail necessarily until we do the fully refined simulation. But during testing, we could sort of order that piece while we still don't know where the exact failure point is going to be. And then when we perform that failure point, all we have to do is validate that it occurred where we expected it to occur once we finally do perform the full analysis on the finalized design. And it's sort of this step of, you don't need to fully do the simulation on the exact final geometry, but as long as you're doing it on a piece of representative geometry that you're comfortable sort of generalizing the results to, you can only generalize them so far. You can be happy that the failure mode is going to be reasonably similar to what you found in your testing.
Great answer. Thank you. Everybody,
very much.
a warm round of applause for you, Vic.
Thank you very much.
Okay. All right. Beautiful presentation. And going from one beautiful presentation to the next, we have someone here that has traveled to Timmins now for a second year in a row from the US to come and visit us. And like Scott Manley, this person I think is an inspiration to a few of us here. And he's also just a cool guy. And that's Charlie Garcia. And Charlie Garcia is the chief engineer at Reflect Orbital and a builder at heart. Before joining Reflect, he helped scale Agile Space Industries as a leading rocket engine developer and previously gained experience at SpaceX. With an aerospace degree from MIT and a garage full of CNC machines and even a popular YouTube channel, he truly lives and breathes engineering. And today, as if this intro is not already cool enough, he will be presenting his work at Reflect Orbital on giant mirrors in space. So everybody, please welcome Charlie Garcia.
Good morning, Rocketeers. Our next talk is from Charlie Garcia on giant mirrors in space. Come check it out.
We're just going to get those slides loaded, and we'll be right with you. And just as an introduction, as we're getting the slides loaded, the next speaker, what I do like with him is that every year there's some people that you're not sure if you're going to see at LC, and you always tell yourself, well, I'm looking forward to seeing them. If they're there, it would be awesome. And then you walk around, and it's the chaos of the morning of the first day, and you see colleagues that you haven't seen in a long time. You say hi to them. And then you see people like Charlie, and you're like, oh my God, it's been so long. I haven't seen you since last LC. And so we're very happy to have you come every year to attend with us and present your work, always with a different project, a new update, a new amazing presentation to share. And today, we're going to talk about giant mirrors in space, and that's not every day that we get to do that. So everybody, please welcome Charlie Garcia.
Good morning, everybody. How are we doing? We are here to talk about space, as expected. Let's see. Is that? Oh, there we go. Okay, fantastic. Um, excellent. So, if I asked you hear that ringing? Okay. Testing, testing. Cool. Mic check 1, 2. How are we doing, folks? Everybody like that better?
Yeah, that's great.
Awesome. So the sun powers everything. Hopefully that's not too controversial of a statement. Everything from fossil fuels to ultimately like nuclear power came from the giant fusion engines we call stars. And here on Earth, more than 99% of our total power on this planet running the biosphere, not just humanity, but everything on this planet comes from the sun. There is, however, a problem. The sun is not available at night. While a seemingly obvious statement, for the first time in human history, this is not just a given. We can use fossil fuels to run thermal power plants at night and use lights to enable productivity and safety at night. We can use batteries to store power and release it at night. But what if we could just go directly from the sun itself at night? Reflect Orbital is a company that is trying to do just that. We are building a constellation of orbiting reflector satellites to reflect the sunlight down from space onto the Earth at night. A little bit about me. I am Charlie Garcia. You may know me already. If you know me previously, it may be from my work at Agile Space Industries, where I was for the last 6 years as chief engineer, developing new rocket engines to enable moon landings, tactically responsive space, and new launch vehicles. Before that, I spent a brief stint at SpaceX doing stage 2 manufacturing and launch integration engineering. I have a degree in aeronautics and astronautics from MIT, where I was president of the MIT rocket team and the publicity chair of the MIT rocket team for 4 years. So why giant mirrors in space? There have been a plethora of objections raised to this idea over the years, and I think it helps to start this discussion with why do we need to do this? And for me, as a resident of planet Earth, I am somewhat excited about living on planet Earth for the rest of my hopefully many years. And unfortunately, Earth is not in such a hot spot right now, or rather, Earth is in a hot spot, and that is the problem. Climate change has been causing increasing global maximum temperatures for the past several decades. And that trend is currently resolving itself into more severe storms, an increased rate of extinction events for keystone species around the planet, and ultimately impacts on human life and well-being. Additionally, power is good. Power has made human life safer, better, and more enjoyable around the globe for members of all civilizations and cultures. And in general, as a rule of thumb, the more power your civilization has access to, the better your health outcomes, the better your educational outcomes, and the better your quality of life outcomes. There is no such thing as a high-income, low-power country. So as a proxy for quality of life, it is really essential that we continue to keep the ability to generate and use more power part of human civilization, which is to say we don't want to fix climate change by all going back to a hunter-gatherer lifestyle. That is just not progress in any way, shape, or form. So why do we want to use solar to fix that problem? Well, first, solar is not a carbon-generating power source. Solar is intrinsically carbon neutral. And solar is also something that we've invested a tremendous quantity of effort and resources into over the past couple of decades. Total PV deployments around the globe are in the trillions of dollars, particularly in the United States and China, where they're scaling the fastest. You can see a chart there on the bottom of the slide, bottom left of the slide, that shows bottom right of the slide, that shows total solar deployments by country over the last decade. Additionally, if you're familiar with the duck curve, the problem is that solar panels are actually a lowly utilized resource. We build these solar farms and we only use them for about a third of a day. They're only useful for about 8 hours at a time. But they already have all the infrastructure needed to connect to the grid around the clock. They have the interconnects already deployed, the land is already cleared, the solar panels are already built out. So they represent an underutilized asset that with the correct deployment of additional infrastructure, we can turn into an around-the-clock baseload clean power source. So why now? If you know the history, which we'll get to in a little bit, people have talked about doing space mirrors for about 70 years at this point in time. However, the current epoch in history represents the culmination of two moments. The first is there's now enough solar photovoltaic deployed around the world that by increasing its utilization, we can meaningfully make an impact in how much total power the world generates. Secondly, launch costs are getting cheaper, and they're about to get way cheaper. With the investment in the number of launch companies around the globe, not only is there now a competitive market, but there's also, to some greater or lesser extent, there's a subsidized market as companies are attempting to get and retain a share of the launch vehicle market before an inevitable consolidation. So if you are trying to send thousands of tons of mirrors to space, now is a great time to be doing it, as several launch companies will likely be competing for your business and giving you an opportunity to get mirrors in space for much cheaper than you could have historically. You can see that trend line there on the log plot. Launch costs are falling and expected to fall by another order of magnitude or possibly more with the operationalization of SpaceX's Starship vehicle. So I promised we'd get to the history, and we're there now. This idea was actually, at the risk of getting a little too historical here, like most things in the space industry, probably started with the Nazis. There was, in fact, some discussion in 1930s and then later Germany about what you could do with mirrors in space. Luckily, they didn't do anything with that, and a much more peaceful and hopefully grounded use of the technology was discussed by NASA in the 1980s, where they published a paper on the possibilities of illumination from space using giant orbital mirrors. You can see the illustration of the proposed NASA spacecraft there on the slide. These look pretty different from what Reflect Orbital is proposing now. These were originally large geostationary mirrors intended to replace streetlights, and so they would orbit over a fixed target and then send down their illumination and power from there. However, this idea did not just remain in white papers, as about 9 years later, as with all great ideas, the Russians decided to take a crack at it. Reeling from the fall of the Soviet Union, the Russian Space Agency was attempting to show that they were still relevant. So they launched and operated two solar reflecting spacecraft, the Zamaya spacecraft. They were converted Progress resupply vehicles that were intended to visit space stations and deliver supplies. And after they completed that mission, they unfurled a mirror and they reflected sunlight down from space. This light was only about the brightness of a full moon, and they had poor tracking abilities. So it mostly just glossed over much of Southern Europe a couple of times, not being put to any industrial purpose. So this is where we come in. The Russians maybe were onto something, but they skipped a really critical step, which is that their mirrors are so wrinkly that their light went everywhere over the entire southern half of a continent. This is not particularly useful, and also it irritates astronomers. And so Reflect Orbital enters the picture here, where as with most structures, tension is the key. Hopefully your statics professors have all delivered that memo, but if you put just a little bit of strain energy into the mirror, your wrinkles go away and you get a very shiny mirror. I was attempting to characterize how much better our mirror was than the Russians' mirror. I gave up after counting 117 wrinkles. Maybe you can get further than me. But if you look there on the right, you can see no wrinkles, a dramatic improvement. So this is one of Reflect Orbital's very first tensile mirror specularity coupons. Certainly did not stop there, though, as our plan is to deploy these on 3,250 square meter mirrors that unfurl in space from a 600 millimeter by 600 millimeter by 1.4 meter deployable bus structure. So how are we approaching that goal? Well, we've been making mirrors, a lot of mirrors. These are made from 2.5 micron thin film polymer coated in a layer of aluminum and then a layer of ceramic to protect the aluminum from atomic oxygen exposure in low Earth orbit. Here you can see one of our 1/30th scale mirrors with my buddy Sam Austin checking it out. So you can see that this mirror only has about 7 newtons of tension in it. For reasons that we probably won't go into too much detail on, the entire figure of merit for how good of a spacecraft you built is how little stress you need to put into the mirror in order to get it flat. If you get this number lower, your reaction wheels get smaller, your deployable structure gets lighter, and your mirror gets lighter. So the fact that you're able to get a mirror this shiny with that little tension is one of the really critical technical innovations we've made at the company. We also need to be able to build these mirrors quickly. Next year, I have to build 80 24 meter by 24 meter mirrors in our factory. And so one of the ways we do that is we build tooling and equipment to enable us to assemble these mirrors very quickly. Here you can see Noah Chalfant actually showing us one of his taping apparatuses. So this is a CNC tape deployer to enable us to put together those mirrors without having to measure out every piece of tape. It's a little counterintuitive, but the tape is actually super important how you put the mirror together because the tape is how stress flows through the mirror. So if you don't put your tape down very accurately, you will actually induce wrinkles in the mirror. We also need to build a low-cost bus. We're talking about deploying thousands of these spacecraft. And you can't do that if each spacecraft costs $1 million because that means you have to spend $1 billion building your spacecraft. So a really critical aspect of what we're trying to do at Reflect Orbital is we're trying to build the very lowest cost spacecraft bus you've ever seen. And this causes it to look more like an expensive car than a cheap satellite. So at volume, we expect that we can build these spacecraft at something like $55,000 a piece, containing low-cost analog radios, very simple mechanical structures, an array of low-cost consumer-grade sensors, and then ultimately the thin polymer mirror, which is the purpose of the spacecraft. So there's been a whole effort at Reflect Orbital to start bringing in-house these components that we use to build our spacecraft. Things like cell phone-grade cameras for star trackers, where using the right filtering algorithms to reject hot pixels in consumer-grade sensor electronics, you can use them to replace very expensive sensors as long as they only need to operate for a couple of years. So what do we have left to go? Well, we need to get better at doing everything. Right now, our spacecraft are too expensive. Our mirrors are not quite shiny enough. Our mirrors are not quite big enough. And also, we only do about 2 spacecraft a year at our facility in Hawthorne, California. So we need to take everything we're doing, get a little better at it, and do a whole lot more of it, which is why Reflect Orbital is hiring. So the whole reason that I am here is to talk to you folks today. Reflect Orbital is a proud sponsor of Launch Canada. I did lots of rocket launching competitions when I was in college. I think they're the best way to learn engineering skills. And if you enjoy building, making things, and launching rockets, there's a chance you might enjoy working at Reflect Orbital. We offer paid internships and full-time employment. And we also sponsor foreign nationals with both work visas and export licenses. So if you would like to come try the US aerospace industry down in Los Angeles, you might enjoy doing that at Reflect Orbital. And also, we play in the aerospace games every year, which is a ton of fun. So if you are excellent at dodgeball, watermelon eating, human pyramid, or relay races, that's a 17th reason we could use you on our team. So with that, that is the whole pitch of what we do at Reflect Orbital. And we have about 10 minutes here to take questions. Anybody would like to start?
Great presentation.
Thank you. Very nice presentation, first and foremost, and a very interesting product. I was wondering, for those satellites or mirrors that you have, what's the lifetime that you'd be looking into them for, how long they can be useful for?
Yeah, that's a fantastic question. There's a couple of factors that limit the life of the spacecraft. For our first spacecraft, we're actually expecting the spacecraft's end of life to be caused by atomic oxygen exposure. So if you're familiar with the solar cycle, right now the sun is a little angrier than usual with the Earth. The solar flux a little higher than usual. And so this means that actually the atmosphere grows a little during these cycles. And so the upper layers of those atmosphere consist of some partial fraction of atomic oxygen. And if you just do the math out on the effective temperature of a single atom of oxygen with a velocity of 8,000 meters a second striking your spacecraft, you will find that it will react with anything on your spacecraft, but especially our polymer structures. And so we expect those to erode over time and then fail. We have a path forward to provide a protective coating on the back side of our, it's actually eroding from the back because the front of the mirror has a protective layer. For technical reasons, we can't put that protective layer on both sides of the mirror right now, but we have a plan to do that in the near future, at which point in time we expect the spacecraft to last 5 to 7 years before orbital drag causes them to deorbit.
One of my colleagues that's running around has a follow-up question for this and just texted it to me. What is the impact of micrometeorites on that life expectancy and on the reflectivity?
That's also a great question. So we're expecting about 4 micrometeoroid impacts per year on the first spacecraft. and we expect that trend to continue as we start building out the constellation. This has actually driven a lot of the work we've had to do on the mirror design, which is we need to design in ripstop properties. So just like you folks might be using ripstop nylon so that if you do get a small tear, it propagates until it reaches one of those thicker fibers that stops the tear from propagating. The mirror itself has some anisotropic properties in the polymer that cause those rips to degrade the mirror a little bit, cause it to provide stress flow around the failed portion of the mirror, and then the remainder of the mirror continues functioning.
Great answer.
Hi, super cool stuff. I was wondering, what do you have in terms of attitude control on the spacecraft? And then following that, what's the plan if you lose attitude control of the vehicle?
Sorry, what's the second half of the question?
What happens if you lose attitude control of the vehicle?
Two great questions. So for the vehicle, we have a relatively simple attitude determination control suite consisting of magnetometers, star trackers for pose, GPS for position and orbit determination. We have backup radar Dopplerometry for attitude determination. And then for actuators, we have magnetorquers to push off of the Earth's magnetic field to dump momentum back to the Earth. And then we have some of the very largest reaction wheels that have ever flown in space, maybe ever, but it's bold to make that claim because the arms that deploy the mirrors are so long and you get a nice little R² effect on your moment of inertia. We actually have incredibly large mass moment of inertia comparable with, things like the International Space Station is only, I think, an order of magnitude and a half larger than our 100-kilogram spacecraft. It's kind of wild. And then if we lose it, the spacecraft deorbits very, very quickly. So in order to keep our spacecraft in orbit, we actually have to do a little bit of solar sailing, and we have to be in a low drag configuration at night when the spacecraft is in eclipse. And if you lose the ability to do that, from 380 kilometers, our spacecraft deorbits in 2 weeks. From 500, it deorbits within 2 months. So it's down very, very quickly.
Great, thank you.
Nowadays, we're seeing with things like Telesat Lightspeed, we're using a lot of light communication between satellites. Do you think it would be possible for your system to have mirrors on the reverse side to be able to direct light to additional mirrors to hit the arc across the eclipse, or to other satellites to provide additional power to them? You essentially could be making an entire power network in space.
Yeah, fantastic question. So for satellite-to-satellite power beaming, that definitely is possible. It unfortunately does not pencil out on the economics most of the time. There's about a 20-minute sliver of the night where it's unclear if flying a satellite higher or doing a multipath bounce down to the ground is more efficient. Probably just based on the fact that everything else in the constellation is doing direct power bounces. We'll probably stick with that. But it definitely got looked at, and the Rube Goldberg aspect of it is quite fun. As far as bouncing the spacecraft to increase their power generation, you can definitely do this, and you get way more power way more quickly than you do bouncing it to the ground because you don't have as much R² loss. Having said that, it does induce some tricky spacecraft design challenges. So the further away something is, the slower the spacecraft has to rotate to track it. And think about other spacecraft is that they both move very quickly and they're relatively close. So you actually induce much higher rotational speeds on the spacecraft that cause you to need much higher torque in your attitude control system. So unless you're flying in a very similar orbit, it's difficult to share power with another spacecraft, but maybe in a couple of years, that's something we could look at.
Hi, thank you. What's the, you said we looked at the Russian spacecraft, which had solar incidence of the full moon. What is one of these satellites going to produce in terms of solar incidence on the surface?
Yeah, that's a great question. Our demo spacecraft is going to be about 5 times the brightness of the full moon. And our operational spacecrafts are going to be at about 9 lux. So about an order of magnitude brighter than the first demonstration spacecraft. That does mean that you're going to need hundreds of spacecraft to achieve brightness levels like daylight on the surface of the Earth. Now, for our lighting customers, that actually doesn't matter. A lot of our customers are just buying the light directly. And so the human eye is actually a really incredible machine. So for things like search and rescue, concerts, and sporting events, you can make do with 1 or 2 satellites very easily. But for power generation, like on solar farms, what we actually need to do is we need to multiplex hundreds of satellites onto a single location on the ground to generate meaningful amounts of power, which is coming back to why we need to build these satellites so cheaply and so many of them.
And just to follow up on that, given that they're in low Earth orbit and the fact that, you know, there's going to be so many of them, will the satellites need to essentially like quickly, once they're unable to keep holding that position on the Earth, scatter that light across the rest of, you know, a path before it is no longer pointing at the Earth? And is that just considered acceptable, or just, you know, small enough levels of light that it's okay?
Yeah, that's a great question. A really big thing for us at Reflect is consensual spot surveying. So there are things that will be harmed by being lit up from space when they shouldn't be. Things like circadian rhythms of animals, things like astronomical instruments. In fact, some telescopes are even so sensitive you could permanently damage the sensors if you were to hit them with one of our satellites. So to track this, we actually have we call it the red map and the green map of places where we have legal authority over the entire territory to serve a spot. We have spots where we have, you know, gray zones where we can like slew on and off of spots, but don't want to serve spots. And then we have red zones, which is areas where it's unacceptable for any of our light ever to fall. And so this is how we're trying to work with the dark skies community and the international astronomical community to make sure that we're responsible players and not just another Starlink constellation ruining the night sky for them.
Cool, thank you.
Excellent answer. Thank you.
Yeah, so you mentioned that you can use these satellites to like cast light on concerts and things like that. How big of the Earth's surface would one of these satellites cast its lights?
Sorry, the question is how big on the Earth's surface is one of these satellites?
So yeah, so the satellite's reflecting the sun's lights onto the surface of the Earth. Roughly how big of an area does the light get cast?
So the spot changes a little bit in shape and size over the duration of a spot serve as you fly over the target. It's smallest and brightest when this satellite is directly overhead, and then, you know, slightly oval shaped and slightly dimmer as the satellite's closer to the limb of the Earth. Good average value is that the spot is about 6,000 acres of coverage per spacecraft, and so that's about 5.1 kilometers in diameter across. So it's really quite a large spot. And that also kind of gives some intuition for why we need so many satellites in space to get brightness on the ground, because you need the same amount of mirror area in space to get the same level of brightness on the ground, because that light spreads out. So if you have a 5.1 kilometer diameter spot on the ground, you need a 5.1 kilometer diameter mirror in space to get equivalent brightness. We obviously don't have that. Our mirror is only about 55 meters across. So that gives you the intuition for why you need hundreds of mirrors in space to achieve an equivalent level of brightness.
Hi, that was a really cool presentation. I just had a question about the environmental impact of the mirrors. So you did mention that by using these mirrors, you're reducing the environmental cost of producing energy. However, if you scale these mirrors up, you're reflecting sunlight onto the Earth during the night. So I was wondering if you've taken into factor the greenhouse effect that would be caused by all these mirrors, and what mitigation strategies you've used to either mitigate the greenhouse effect or to see if it's any significant in its impact.
Fantastic question. Could I get my slides back for 1 second? I actually have a chart on this. We have done the math on this. I think it is so important that as we take these steps to control our environment more, we do so in a responsible fashion. And this is part of the reason why I'm so excited to be at Reflect. I have the highest opinion of the team I'm working with, smart people, kind-hearted people, and people who really care about making the world a better place. So this is actually one of the problems that we tackled. You can see here, the bottom chart on this slide shows the net added energy to the atmosphere over the lifetime of a spacecraft over a certain number of years. So you can see that even just adding solar power with batteries causes dramatically more total energy addition to the planet than Reflect does. So Reflect's total thermal added power mostly comes from reflected rays. We're essentially full spectrum sunlight, so including those IR and UV tails. And then a little bit of contribution from greenhouse gas effects, mostly generated actually by the launch vehicle. Each launch vehicle is about 1.1 million pounds of fuel and oxygen. So that I think comes out to something like 400,000 pounds of additional carbon dioxide. and then that's ultimately removed through various processes. But then if you use either a methane or a hydrogen rocket instead of current kerosene rocket technologies, you get an even dramatically superior performance as far as total added energy in the atmosphere over time. Hopefully, eventually, this becomes a significant phenomenon because that means that all of the fossil fuel generating power capacity on the Earth has been offboarded. And we start talking about maybe we generate power in space and we start moving data centers and compute into space data centers. And maybe reflect satellites start pointing at those data centers instead. However, for at least the next couple of decades, we expect that this is a dramatically more effective approach to addressing climate change than certain other technologies. So. And thank you for asking a question I had a slide on. I was so excited. I got to go back to that.
No, I just wanted to say that was a very impressive answer. Thank you.
And so just to clarify, you said that using the solar panels and the batteries on Earth would generate more greenhouse effect than the added energy dumped into the atmosphere by reflection.
Yeah, and there's a couple of mechanisms for that. I think one of the big ones that people forget about is that deploying new solar sites requires clearing large quantities of land. Depending on what that land was doing previously, that land is carbon sink and habitat for populations of either humans or animals or part of the biosphere. Additionally, the resources you need to build and deploy those batteries versus using a smaller number of generating capacity more efficiently. And so, if you think about it, you actually need to build 3 times more solar panels plus batteries, and rather a lot of batteries versus operating a solar farm around the clock to generate equivalent amounts of power. And then that's to say nothing of the fact that you can actually, there's an intermediate solution where you use a couple of batteries and reflect orbital together, and you actually dramatically reduce the amount of batteries you need to build out because you're only using batteries to cover 1 or 2 hours latest at night when the satellites are least effective and the batteries are most effective because you're not storing the power for as long versus trying to build batteries to cover an 8 or 9 hour nighttime gap.
Thank you for the talk. I was wondering, what does it look like for someone looking up towards the satellites when they turn on? Is it like a star coming on?
Yeah, that's a great question. So we expect to be a magnitude -11 roughly. It depends on which satellite you're looking at. But yeah, so it's somewhat brighter than looking up at the full moon, but coming from a point. But it's not going to blind you. You could stare straight at the satellite for hours. Now, there's a couple of interesting cases of what will this look like when we have a bunch of satellites all serving a solar farm together and the entire sky is just kind of glowing from a bunch of directions. I'm actually really excited to see what that looks like. But we do expect it to be safe for both humans and animals alike.
Amazing. Everybody, a warm congratulations to Charlie for being here and talking to us today. Thank you so much. If you have any more questions, will you be here today at the conference? You can go talk to Charlie directly. I'm sure he'll be happy to talk more about the Reflect Orbital. And by the way, great name, Reflex Orbital, Reflect Orbital. Awesome. Okay, so we are entering our first break of the day for 10 minutes. And we will be back at 10:15 for the Tech Dev Team 7 and 9. That is Queens and Mock. See you soon.
Good morning, Rocketeers. We are back from our break. Our next two talks are going to be made up of tech development projects from you students. They're going to be featuring the hybrid test stand for Queens and the liquid engine test stand for Bob. They're extremely excited about these projects that are coming together, being accomplished in 5 years of work. And Mott's very excited to present their take on regen tooling. So don't miss out.
Okay, welcome everybody. It is 10:15. We will start this second part to our morning of the second day of the Launch Canada conference. Right now we have two tech dev teams, as Ariana introduced, which will be speaking to us about fluid testing. And the Tech Dev Challenge, for context, for those online watching the live stream, is a new challenge this year, but before it was a category within the same Launch Canada Challenge. Now it has its own challenge and its own trophy on the stage. And for a little bit of context, that is Adam's LR101 engine, which will be given as a prize at the end for the winner. And what's interesting is that today we'll be talking about fluid testing. And these are two teams, so Queens and Mach, which will be participating in the Tech Dev Challenge for that on fluid testing subjects. And like you can't have a good burger if you don't master the barbecue, or a good Launch Canada without great volunteers. Well, you can't have a good hybrid or liquid engine program without a solid fluid testing setup. And by fluid testing setup, what do we mean? We mean test stands, sensors, pumps, flow meters, DAQ, regulators, and everything else that makes data and fluid flow. And today we have two presentations on the topic, starting with Queen's University and followed by Mach. And so let's talk about Queen's. QRED has been constructing, so QRED being Queen's Rocketry engineering team, has been constructing high-powered rockets for competition since 2016 for the past few years, and they've been designing supersonic flights to over 30,000 feet and recently won first place in the basic category at the 2023 Launch Canada competition. Outside of high-performance rocketry, the team has also been developing a custom hybrid rocket engine and various side projects, including autonomous rocket tracker. And today, presenting this, we have Hazian, which consists of Noah, Aslan, Eric, Zach, Andrew, and Hans. Everybody, welcome Hazian to the stage.
Good morning, everyone. My name is Andrew, and I'm one of 22 people that make up the propulsion sub-team of the Queen's Rocket Engineering team. And yeah, this is going to be a high-level overview of what we do for working on the hybrid rocket engine that we've developed this year, and we're really excited to share it with you. So we're going to be taking you through six different components, starting off with team introduction, then moving through the project overview, technology impact, expected results, how we're going to measure our success, and finally a financial review. So to start off with a bit of a team introduction, who is QRED? So QRED is a team at Queen's, one of our 17 ratified design teams under the Engineering Society, which has roughly 100 members under all of our sub-teams. So starting off, we have three executives, Carter, our president, and then Nick and Tegan as our vice presidents. And then we have 8 sub-team leads, that being 2 aerostructures leads, avionics, payload, mechanical, kit rocket, and then our 2 propulsion leads, Noah and Aslan. So for a breakdown of propulsion, we have currently 22 active members. Yeah, this isn't all of us. And those subteams break down into our aux tank, combustion chamber, fuel grain, our nozzle, GSC, and electrical, which we'll get into a little bit later.
Yeah, so our first year of tech dev, we created a backup telemetry system. And the next year, we decided to do a sunflower tracking system, which used GPS to track rockets in the sky. Last year, we did our next iteration of this design, in which we used machine vision to track rockets. This year, we've decided to bring propulsion into the tech dev challenge to show off all the hard work that we've been doing this year.
Okay, so to give a little background on our project, rocket engines are a very exciting technological development that combine various complex components and strands of engineering to make one continuous system. Our team has been working towards a hybrid rocket engine to help further our engineering understanding and knowledge and test us in the field. So our project overview. So our project consists of 3 main systems, such as our propellant feed system, our oxidizer tank, and our combustion chamber. This allows us to expand our knowledge in various strands of engineering, both mechanical, electrical, chemical, and our system utilizes 3D printed ABS fuel with nitrous oxidizer. Our planned demonstration is to do a static hot fire test of the engine here at LC 2025.
All right, so the propellant feed system is all made out of 316 stainless, mostly with swage lock fittings. We also have an SRAD vent valve. This is our first time ever going down the SRAD valve route. It's a poppet style valve using 2 O-rings to seal over the valve. It's normally open because with vents, that's the state we want to be in. We have nitrogen in parallel with the nitrous. This allows us to purge, and it also powers our pneumatics.
So the oxidizer tank consists of a tank made of 6061 aluminum and 2 bulkheads, which are each fitted with 26 shoulder bullets. This connects the propellant feed system to the combustion chamber, allowing for the reaction.
So here's a picture of a cross-section of our combustion chamber. So I'm just going to kind of go through all of the components here. So at the top there, you can see the injector, which is housed inside the forward enclosure. We are using 24 quarter 20 bolts to fix both the forward retainer and the nozzle retainer, but we'll get to that, and two O-rings. So below the injector, and we're using a showerhead injector to atomize the oxidizer as it goes into the combustion chamber. Below the injector there, the yellow part is the phenolic liner. We chose phenolic because we needed something to insulate the aluminum combustion chamber, and phenolic works well for our purposes. The fuel grain is 3D printed ABS. A lot of teams who do hybrid rocket engines end up choosing paraffin wax for their fuel grain. The reason we chose to go with ABS is because it allows us to 3D print more intricate fuel grain geometries to try and improve combustion efficiency. And we don't currently have the logistical setup to do spin casting or mold casting with paraffin wax. Then below the below the fuel grain there, we have a fiberglass tube that is supporting the fuel grain. And then below that fiberglass tube, we have a mixing plate. So one of the issues with hybrid engines is that you have the liquid oxidizer coming through the middle, and then you have the solid fuel grain on the outsides. But we need those to mix to have the most efficient combustion possible. And so the mixing plate acts as kind of, it's a passive mixing device that you put in the post-combustion chamber of the combustion chamber. And as the kind of burning ABS and oxidizer kind of flow through there, they're able to mix, which improves combustion efficiency. And then we have another fiberglass tube below the mixing plate to kind of hold it all in place. And then below that, we have the nozzle and the nozzle retainer. Again, the nozzle retainer is held in place with 24 quarter 20 bolts. And the nozzle is secured into the nozzle retainer using RTV.
All the components within the phenolic are held in the phenolic with a coating of RTV around the outside, and then the phenolic is slotted into the combustion chamber with a coat of grease around the outside. So another important part of our project is the ground system equipment. And so we have three kind of main projects there. We have the test stand, which is the top picture there. We have the oxidizer tank stand, which is the middle one there, and we have the tank tipper. So the test stand, we have a kind of T-slotted aluminum, we made rails. So the combustion chamber slots into some fittings we made that sit on those rails, and we have a button load cell. And so when the rocket is going, we're able to measure the thrust with that load cell. We're securing it to the ground using 1/4-inch steel aircraft cables that we have crimped loops into, and then we're using earth anchor auger style anchors to drill into the ground. We will be tensioning that by securing them strategically at different points around the test stand, and then we will be pulling it to make sure that everything is tight, and there'll be sandbags on there as well. The oxidizer tank frame stands upright. Again, it has those rails, those T-slotted aluminum rails with a load cell, button load cell on the bottom. And so as we fill the ox tank, we're able to see how much mass is actually in there, and that's how we're measuring how much oxidizer we're going to be using in our fires. The tank tipper was needed because we don't have a dip tube in the pressurized gas canisters, so we needed to tip it upside down to get all the gas out. This is a little bit dangerous if not done properly, because the most kind of vulnerable part of a gas canister is that kind of tip, that nozzle, and so if it hits the ground, we don't want to create any accidental rockets. So this tank tipper, you secure the compressed gas tank to the tank tipper with ratchet straps, and then you're able to tip it up and it stays in place.
So a big part of running a rocket test is collecting data on it, and we obviously don't want to be doing our test if we have no idea how to control our rocket. So we are currently running a setup where we have one board sitting at the panel, and this is an ESP32 that is used to interface with AECs to collect all of our voltage readings to get all of our sensor data. This connects onto a wireless network that we host at the at the panel, and this wireless network is what we use to do all of our control and all of our monitoring throughout. So the ESP32 connects to the network, and we also have a server that's hosted on a Raspberry Pi, and the server manages all the connection between all of our different devices that we have connected. So we have cameras that we connect, we have our ESP32 to do our controlling, and that's all routed through the server, and then the server exposes HTTP endpoints for control, as well as offering out a data stream that can have multi-clients connect to it, meaning you can have our laptop connect to it for control and data streaming, or you can have a phone on your app on your phone that can also connect to it, and everybody can then see the data that's being streamed by the sensors.
Yeah, so why are we doing this in the first place? First is to serve our primary stakeholders, and this is on knowledge development and education. This is both meaning for us as a team to develop our own knowledge in rocketry, in engineering, and practicing things outside of the classroom. But then it's also a part of developing knowledge in the greater Kingston area. So in our outreach programs, we have programs where we work with some schools around the Kingston area to just gauge interest, get the younger generation involved in things that we're so passionate about, and share that knowledge. As well to serve our secondary stakeholders. We're really proud to be a part of the development of aerospace in Canada, reminiscent of what they were saying a lot yesterday. And both from our perspective and the perspective of building knowledge for Ontario and Canada in the aerospace industry, that's something that we're continuously working towards as well. So QRET as a whole has done a whole sort of different kinds of outreach activities, just because we have the privilege to do so, and so we want to get back to the community. So over the recent time, we've been to many different summer camps and things like Science Quest, and the propulsion team as a whole has seen an overall beneficial growth of the team since we started using this hybrid rocket engine. So since the last test last year, there was a YouTube video of it, which has gained over 20,000 views, and since then we have seen over a 50% increase in the QRET Instagram following,
and it's averaging around 20 or 2,000 views per post.
So a big part of developing the hybrid engine has been simulating what we think is going to happen. Hybrid engines are incredibly difficult to simulate accurately just because there's so much going on inside them with interactions between the oxidizer and the fuel grain. But we used a combination of like FEA and fluid sims to try and kind of best determine what we're going to actually see when we do the hot fire. One useful program we used was HRAC, which was developed in part by Peter, who we heard talk yesterday. So we're expecting a peak thrust of, it says 5,300 here, but about 5,500 newtons. We're going to use about 9 kilograms of oxidizer, and the fuel grain, the target OF ratio was 5:1, but we made it fuel rich because we wanted to make sure that the fuel didn't run away. Here you can see a fluid sim of the mixing plate. You can see how the fluid after the mixing plate is a lot more mixed than the fluid before the mixing plate.
Yeah. So with this project, we're trying to validate a flight engine, right? So we have some goals with this project. Some goals are characterizing the ABS fuel grain, validating our new injector design, making sure that we can properly thermally insulate a hybrid rocket engine. We also want to test our new DAC, a data control system. So this is the first time we've ever done this. Last time we were using a lab jack. This is also our first ever nozzle design. So we're trying to validate that as well. And our igniter design as well. We haven't used that to this degree before. We have some KPMs. We're not going to go over them here.
Yeah, and then we'll delve into a little bit of a financial review. So you have our cost breakdown, and I won't get too detailed into it, but basically this year our actuals were 8,500 to develop our hybrid rocket engine, and then to come to competition just over 6,500. And then we also projected our future cost breakdown. So the scope of this project is to integrate it on a flight-ready rocket for the 2026 competition. So that obviously will require integration, and a lot of work needs done, which incites cost. So we're projected between the hybrid engine and competition to be quoted just over 20,000 for next year. And yeah, that brings us to the end of our presentation. Thank you for indulging us. And now we have a time slot for any questions you might have.
I don't think if you asked me, I could summarize a whole hybrid engine program in 50 minutes. That was beautiful. Thank you. Any questions from the audience? Oh, Mitchell.
Hey guys, well done. In terms of your presentation, could you go to the slide where you had the cutaway or section view of the engine? Because you were showing the mixing plate, and then below that, it looks like there's an exposed portion of the combustion chamber. Is that actually exposed, or is there more liner between the mixing plate and the nozzle?
So the mixing plate is held in by a fiberglass additional tube. So there's never exposed aluminum. It's just an additional fiberglass tube to hold the mixing plate. It's just a similar color.
Okay, so it's just a fiberglass tube. It's not actually like
an additional
a phenolic liner.
No, it's a fiberglass tube as well as a phenolic liner in the post.
Yeah, there's the fiberglass, but I'm saying post the mixing plate, between the mixing plate and the nozzle, it's just a fiberglass tube.
No, it's a fiberglass on top of phenolic.
Okay, why put fiberglass on top of the phenolic? Why not behind the phenolic for the thermal protection?
We needed to hold in the mixing plate without exposing the aluminum.
Yes, but couldn't you have had you have the combustion chamber wall, then the fiberglass, then the phenolic?
Combustion chamber wall, phenolic, and then fiberglass within the phenolic, and mixing plate held in by. I can show it to you at a
Okay, sure. Yeah, it's just because it seems like having the liner be exposed fiberglass doesn't seem like the best way to go. Because part of the way that the phenolic acts as a thermal barrier is by ablation, right?
Yeah.
So if there's something between it and the flame, it's not really doing its job.
That's totally fair.
This is a follow-up to that. So we were in a similar situation at McGill where we had the phenolic liner and we couldn't make sections of it because we would have to seal that section to avoid the flow path to the combustion chamber. That's why we had a spacer inside of the phenolic liner. But I'm not sure about fiberglass, so I understand why you have that order, but we'll discuss maybe at your stand for fiberglass. Any other questions? Yes.
Hey guys, what was the name of the software, the FEA software that you used?
The FEA or simulation?
Simulation. I
So
believe.
we use HRAP. It's the Hybrid Rocket Analysis Program. It's developed by the University of Tennessee.
How do you spell it?
HRAP. Sorry, HRAP. My bad. Peter and Nico. Peter and Nick, two LC volunteers who volunteered here have developed that program a few years ago. So, yeah.
Sounds good. Thanks.
And that's why we do these. Knowledge transfer. Yes.
Can you guys elaborate more on why you went fuel rich? Why you guys opted to do that?
So during the burn, we're actually oxidizer rich, but we put more fuel in than the 5-to-1 ratio because we don't want to burn through all of the fuel. The fuel is our first insulator inside the combustion chamber.
Okay, so you're trying to just have extra fuel remaining at the end of the burn?
We want remaining fuel at the end of the burn, yeah.
Okay. I guess one more. What did you guys think was the most difficult thing that you had to deal with during the design?
I think that validating simulation and making sure that your simulation is correct is extremely hard. It's hard to do that without practical testing and to trust your results. You have to be extremely detailed to make sure that you have everything correct. Yeah, simulating motor performance is extremely hard, and we wish we could do it in-house, and maybe next year we will, but we had to rely on external tools this year. And yeah.
We have time for a few more questions. I do have one that's itching me. The difficulty with you're working with nitrous oxide, and the difficulty is when you flip the tank. So you're basically using the self-pressurizing pressure of the nitrous to pressure it down your system. And so with those systems, you get a blowdown, your tank cools, you lose the pressure, you lose performance, and your thrust curve goes down. Do you have any future mitigation strategies to make that better? Heating the tank, having supercharging the tank with helium or hydrogen?
Yeah. We have a heating PCB developed. It just hasn't been manufactured yet, and we're looking into supercharging. I think McGill supercharge is correct, yeah. But it's not something we're actively seeking out right now.
Sorry, and that PCB is designed for a heater on the tank, so just to keep our temperatures up while we're cooling and try and crank some heat into it as it's firing to maintain the pressure.
Are you planning on testing all year, 4 seasons?
Yes.
You definitely want a lot of wattage through that PCB.
Yeah, we have it designed for 600 right now, so.
Sounds good.
Yes.
Adam, did you have one more question? No? Awesome. All right. Thank you, Queens. Appreciate it. So I'm seeing Mark already here. Would you guys be ready to present? Okay, so ahead of schedule. Beautiful. We do have until 11, so that's perfect. Okay, so because it is 20 minutes presentations, I forgot, so we're right on time. Let's talk about Mark a little bit. Formed in June 2018, the Ryerson Propulsion Group is a non-profit student-run, TMU Propulsion Group is a non-profit student-run volunteer-based engineering design team with the mission of educating students in the field of advanced space propulsion. RPG, or MACH, was founded under the assumption that anything is possible for anyone with great idea and determination. Since its inception, students involved have designed and are ready to begin development of a rocket engine without having any prior knowledge aside from fundamental engineering concepts. The latest project undertaken by the team is a nitrogen gas pressure-fed engine design utilizing liquid ethanol as a fuel and liquid nitrous oxide as an oxidizer, so a bi-liquid engine. The small engine is capable of producing 350 pounds of thrust and is intended to be a proof of concept, and the engine system is equipped with pressure transducers, thermocouples, and flow meters at critical areas of interest to allow the team to better understand the mechanics of a working rocket engine. Currently, the design is complete and purchasing info is prepared. If your organization would like to help our team of young aspiring engineers make this initiative a reality, please help our website for more information on funding opportunities. So on that note, I would like to welcome Mach onto the stage to talk about their liquid rocket engine test tank. Everybody, please welcome them.
Good morning, everyone. We are Mach, the Metropolitan Aerospace Combustion Hub, TMU's only liquid rocket team. My name is Eve Samir. I'm with the Propulsion, Media, and Logistics team, and today we're going to talk a bit of what we've brought to you at LC. So here's a little agenda, what we're going to go over today. We're going to start a bit about the team, what we do, what is Mach. We're going to talk about our technology, what Sprint is, the importance of this project. We're going to talk about what the demonstration is going to look like tomorrow or over the next week. Some KPIs, talk about our future projects, and our timeline and cost breakdown. So here's a couple photos from our successful cold flow a couple weeks ago. It was all hands on deck. Our whole team was involved. It was super great to see everybody come out. Like I mentioned, it was successful. It was great. It really lined us up for our hot fire, which we'll talk about in a sec, coming up this week. So, why Mach? Why are we here? What's our purpose? We are TMU's only liquid rocketry team. We're working to push the boundaries of what undergraduate students can do in liquid propulsion and what we can do going into the industry. We conduct high quality research, so compared to our solid or hybrid rockets that we do at TMU, we're also working to increase our specific impulse for our liquid engines. And obviously we're trying to do this safely. So using TNC or our telemetry and control team, which I'll talk about in a second, we tried to make sure everything is well controlled and store both our propellants and our oxidizers separately until we're ready to ignite. This ultimately reduces our risks overall compared to our solid or hybrid teams. So our main technical team consists of three main sub-teams. Our telemetry and control, as I've mentioned, they provide us real-time data that we use during our tests to ensure that we have these safe cold flows and hot fires. They control the precision of the valves, which allows us to control our pressure and ultimately how the test runs overall. Our propulsion team works to build and develop the engine itself, obviously to safely deliver these propellants and generate thrust for the Sprint system. And our structures team develops our mounts to make sure that our engine isn't flying away when we don't want it to. So it makes sure that we're making everything happen safely and that everything is stored together. All right, I'll pass it on.
All right, thank you so much, Eve. My name is Evan, and I'm part of the hardware team. I work primarily for the ground station enclosure. Most of my time is spent working on this big, beautiful box. So let's get right into the primary function of it. The primary function of our ground station is to collect telemetry and control our bipropellant liquid rocket. Now, if you know about GSEs, you know that they can be held technically in a pizza box, theoretically, but we're making it so that this year we have the most robust and standardized ground station enclosure that we've ever had for Mach. So let's get into the enclosure itself. The enclosure is IP65 rated, and all the exterior connectors are IP67 rated. This houses all of our critical electronic hardware, and we've made sure that it's dust resistant and resistant to anything and the critical conditions that would be experienced directly on the pad. So for instrumentation and control, we're also using industry standard equipment such as the LabJack T7 Pro and the Click PLC. The LabJack is primarily for analog instrumentation. I'll get into a little bit of that later. And the Click PLC is to control our relays and our servos, all from software. So in terms of our networking and software control, it's all done through a gigabit Ethernet switch, which allows our software team to remotely connect through Wi-Fi to the ground station enclosure. If this fails, we have manual override and fail-safes built in within the system, just so we are sure and we have redundancies. The overall capabilities in terms of analog measurement systems include thermocouples, pressure transducers, and load cells. If you want to come down later, I could run you through the entire system. It would be awesome. We also have PWM-controlled servos, and we also just lost the slide. We also have mechanical and solid-state relays and fuse protection and terminal blocks We've organized all the wiring with wiring harnesses. So thanks so much. I'm going to pass it on.
Hey, my name is Casper. I work on the GSC systems. So we wanted to complement the reliability of our ground station, and we wanted to reflect that with our human-machine interface. So we looked around, we decided to go with LabVIEW for our static human-machine interface. And what that means is that we have a nice little panel where we control all of our valves and parameters, as well as view our data in real time. So we have a piping and instrumentation diagram on our screen. You can see in the bottom right corner. On there is overlaid our parameters that are being fed from real time off of our engine. Those are filtered, of course, and we also have some intuitive valve controllers. So this allows anybody with next to no experience to control our rocket, which makes it really easy for anyone to use it. We also have a nice and robust logging system we made in-house, so we can get all of our data and we can get a nice snapshot of literally everything that's happening, from readings from our sensors to individual button presses on the panel. We also have graphing capabilities, and we developed a system that we can either have one operator or multiple operators, and it's all integrated in one system. You don't have multiple programs that you have to install. It's nice and robust, and we're quite proud of it. We're now going to pass it on.
My name is Anthony. I work on avionics. Our goal is to make expensive components accessible to our team. We use a modular stack-up that communicates using CAN bus, and our system features bidirectional communication that sends and receives data.
Okay, my name is Zool. I'm the team captain. I'm just going to talk about the GSC plumbing a little bit. So we have a scalable plumbing system that uses industry standard fittings that allows us to fill and purge our system. So we have high pressure and low pressure regulator. One is for our pneumatics, which gives us fast and reliable actuation of our fill and purge valves. And yeah, we use swage lock, MPT, and AN fittings. If I move the slide. Yeah, so to talk about what we're doing at Launch Canada this week, we're doing the Sprint system, which stands roughly for Small Scale Prototyping for Rapid Iteration and Testing. Our purpose is to collect nitrous and ethanol bipropellant data for our engine to create a scalable platform for future engines. Last year we came with a 250-pound rocket engine, roughly, which was deemed Gary, a Gary-related ablative engine. This year we're doing a heat sink engine, so we're simplifying that a little bit. We're also simplifying our test stand and our GSC in general, and this is going to allow us to be able to scale in the future due to these simplifications. Our thrust is aimed at roughly the same as Gary, which is about 250 pounds, and chamber pressure roughly the same as well. This project, given its smaller scale, allows us to rapidly iterate. So for reference, from the inception of this project, about a month and a half ago, we were able to get a cold flow out just a week ago. So this allows us to make quick improvements and increase accuracy of all of our nitrous flow models, and we expect to continue doing that throughout this week and after Launch Canada when we look to fly our engine, which we'll talk about the timeline in a bit. Yeah, this is also a training platform, so given the smaller scale, we want to continue doing this project even when we start scaling it up later on. This is going to be a way to attract new members and really grow the team. And yeah, motivation recruitment-wise, the rapid successes will give us a lot of new members and stuff like that. Yeah. So, this week we're going to be hot firing, and our primary goal is to demonstrate a throttling capability. So we have servos on board that are controlling our main fuel and oxidizer valves, and we hope to, during our second burn, throttle down to roughly 75% of thrust and hold that for the second half of the burn. If we have time, we're going to use our alternate injector orifice geometry configuration. We have two spare injectors, which we want to test out different mass flow rates of nitrous oxide, which would really give us some great data about our models. We're using like the modified Omega model from Emerson, if you guys know the UFT paper or whatever. Anyways, yeah, we would be really interested in seeing how that research actually translates when we're just varying one parameter at a time. This is like the first time we've actually been able to approach like really rigorous scientific data by varying one parameter, just varying like orifice diameter of our nitrous oxide, that would be really cool to see. And yeah.
Hi, so my name is Dimitri. I'm working on propulsion and structures. Basically, for this engine, we have multiple ways we can see how it is efficient and base its performance on it. So we have three ways of doing it. Thrust efficiency coefficient, that's basically taking the theoretical thrust we are calculating and our actual real thrust based on the load cell readings and comparing them both and see how much energy we lost we had there. Same thing with characteristic velocity. We're trying to take the actual mass flow rate theoretically we're supposed to have and the real one we're going to measure, and based on that we'll see where we have problems with friction and other problems. Then we also have an injector pressure transducer where we're measuring the pressure in the chamber and the injector, and we're basing that pressure on the theoretical pressure we're supposed to have to the actual real pressure. The reason we're doing that is because we're using a piston tank design, and for the first time when we're doing this, there's bound to be pressure losses. But we can always, based on the data we get, change that up in the future by changing maybe the bulkhead size, the O-ring size fittings, and other things. So based on this pressure reading and the actual real pressure reading we're supposed to get based on the theoretical, we're able to enhance our propellant tanks and any future designs. Now for the fun part, Dan, take over.
Hello, everyone. Thank you very much. My name is Giuliano Sciaparassi. I am the propulsion lead at Mach. This is some of the future projects that we have in store. On the screen over here, you can see we have our regenerative cooled engine. This is a 6.3 kilonewton ethanol nitrous oxide engine that is 35 centimeters tall and weighs roughly 15 pounds. This engine is what we have working on the side, and it's going to be a future test bed that we plan on adding things to with more development later on. So on the right image, you can actually see when this engine used to be an ablative. So 3 months ago, this was an ablative engine, and that's what we had as our Mach thrust vectoring control system. When we changed to regen, we modified the CAD. We also modified the lid geometry, so we had to redesign that. So unfortunately, we don't have the DVC for the new system there. However, that's roughly what it'll look like. In the image of the regen engine, you can actually see what we have is our torch igniter mount. That's where we're going to be mounting our torch igniter. And behind the engine on the other side, we have plates where we're going to be mounting the ball joints for the thrust vectoring system. So as mentioned, this is going to be a system that we're going to be developing for multi-year long project. And we hope next year we'll be hot firing this engine with these systems at LC. In the left, we have torch ignition.
Hello again. So I was working on the torch ignition with Jan, and the reason we're doing this is because usually the way to ignite an engine is to get the chamber to be hot enough to reach the activation energy of your propellant so you can hot fire. So the problem with that sometimes is that usually we use pyrotechnics or like any other like rocket motor boosters to ignite it. Things that for those you always have to change it, and there's always a problem of mounting inside the engine or inside the plumbing, and that creates a bunch of problems, and also it's not really cost efficient. So therefore, we're trying to go for an industrial way, and also to make it actually really cool, we're trying to make a torch igniter where we take a small amount of our propellant, inject into a small chamber on the side, as you see on the bottom right corner, and you also see the cross section, and we have a spark plug that ignites it. It gets compressed and then goes into the chamber, and it goes in the specific right portion of the chamber downwards to allow to go to the actual atomized particles of like the propellant, so we can get the most efficient like ignition. So this is the torch igniter, and next.
Hello, my name is Adi, and I'm in the transfer and control team. As you can see, this is the current timeline we have until LC 2026. Basically, last week we had our successful cold flow for our sprint system, and will be hot fired this week. Around October or November, we plan to have another hot fire for our Sabre, which is the regen engine, and thrust vector control and torch igniter will be implemented around early next year. It will be a ready-to-go flight-weight system for LC 2026. Coming to the cost breakdown, Mach decided to have sprint budget-friendly project It was designed, it was started as a cheap project for like new members to come in, learn about liquid rocketry, while the core team focuses on bigger and better projects down the line. So as you can see, the Sprint rocket propulsion, tripod, which is 3D tripod mount, which is 3D printed, thrust stand, plumbing, electronics are easily available and super budget friendly. Now we will go to Eve to showcase our sponsors.
All right, so this is a quick look at what our investors, who our investors are. We really appreciate all of the support that they have given us over the past year. Obviously, none of these projects would be possible without the funding and support we receive both from the school, but also from these companies who have graciously sponsored us. So if you're interested in any of these projects or want to support our team further, feel free to reach out to myself or anybody on this team. We'd be more than happy to talk with you further about that. Thank you so much for listening. We'll take any questions you might have.
I love that you call them investors and not sponsors, because they're not only sponsoring you, they're investing in you. That's great. Any questions?
Hey guys. I was wondering about the torch igniter. I was wondering if you could speak more to that and why you decided to go with that as opposed to other options.
Oh, sorry, what's the last part you said? Apart from
Other options like just.
Oh yeah. So the reason we went for a torch igniter is because it's mostly been an industrial way to like actually to ignite the wave. Like different like companies do it, and the reason previous engines we used to like use a small little pyrotechnic that will ignite the small little pyrotechnic that gets a chamber to enough temperature. So then we open the valves to get the propellants in. Then it goes to the ignition temperature and ignites. Well, the torch, the problem with that is that you always have to get the new pyrotechnic block, or like get a new rocket booster that's hot enough to get in there. And also, it kind of blocks the nozzle all the time. So the problem here is that we're trying to keep it as more efficient and have nothing always like fly out. The best way to like do this is to use a torch ignition as so far apart for now. So we're using a little torch igniter, and we have it on the side. We go on like right under to like the actual chamber where like we have a perfect like automation of our propellants goes down, and this will allow us to do this multiple times. It's reusable, and if we ever want to reignite our engine, like we want to like to do any other like new project, we can always have the ability to do that.
Okay, that's great. Thanks.
Other questions? I do have one from last year. The couple last years we saw Mach come to Launch Canada. You came with this setup, this kind of a, I think it was a Christmas tree that you, one of the leads called it, for your liquid engine. And now we see this new system. What have you learned from that system that you transferred to the new one? And how were you able to do that knowledge transfer so that that investment can be reused in this new generation?
Yeah, I think the biggest change is just simplifying everything and like creating using piston tanks. Like we've seen this with Waterloo and like Half-Cat, and this like piston tank raise is like it just simply is the way to go if you're going to be doing student amateur like rocketry at our level. I mean, obviously the Concordia scale, which goes a step above that, which someday maybe we can get there, but the stepping stone really is using piston tanks. We did have designs for our rocket, which we previously called Dayglow. I don't know if there was any posts online about it, which didn't use a piston. It was ethanol pressurized by nitrogen, so you can have variable fuel pressure. And we just had kept Dave Venturi there, and nitrogen was nitrous was choked at the injector with no Venturi. And that system was just a lot more complex than what we're dealing with right now, and it introduced a lot of issues, especially when it came to making it lightweight, which we want to do. And that's definitely what we learned from previous years. This fender, we used to call the system, like the Christmas tree looking thing, was never going to fly, and it used a lot of like industry standard practices, which was really awesome. It was the nitrous was supercharged, ethanol was pressurized by nitrogen as well, and it was like great for like really great robust data. But we think we can get even more data with a simpler system and iterate. on other things. And we have like a whole new team coming up, which is going to be avionics from last year too, and that would really only be possible with a simpler system that's lightweight. And yeah, hopefully that answered it.
Great answer, thank you. And we have time for one more question. Well, thank you.
For the torch igniter, you guys are gonna run fuel and oxidizer. You're gonna bleed it down to the igniter to get it started, and then blow out into the chamber. Is that correct? Did I hear that right?
Sorry, repeat the question?
How are you gonna light the torch igniter? I guess. Go ahead.
Yeah, sorry. If we weren't really clarified about that, when we have the propellants go into the chamber, we have like a small block. We have a spark plug on the side that's going to be activated by a small little step-up voltage booster. Sorry, I should have mentioned that. But once it goes in, we get a small amount. We need a really small flow rate. If we have too much, it'll be like igniting a match in a rainstorm. That's pretty much how it is when you have a huge amount of mass flow rate of nitrous and ethanol. So that's the reason we're igniting a very small mass flow rate. I think it's like 50 grams per second, really small amount. And when we have it inside, we inject a small amount of it, 2 nitrous quarts, and then an ethanol. And after that, we have spark plug inside. It goes just about midway to the chamber of the torch, and then it chokes the flow and goes into the engine itself. So we're using a spark plug ignition for it.
Okay, but that's you're bleeding nitrous and ethanol into the igniter chamber itself, and then lighting it, and then that lights into the chamber.
Yeah.
How are you guys controlling the bleed down into the igniter port to light it, and then throughout the test? Like, how are you plumbing that, and then controlling it on and off, or is it just going to stay flowing into there the whole duration?
It stays on, but we're planning, I think, on purging the system afterwards. We're taking it off the line from nitrous, but we're using a small amount of it. Come on.
Beautiful. Thank you for the very complete presentation and answers. Everybody, warm round of applause for Mark. And I love that you used your engine to dig in the ground. That's very Timmins-like. All right. Next speaker is fun in the sense that it's someone that you've heard about before and you've heard before. You've probably heard her voice on the PA announcement, and you've probably received emails from her for your own talks. The next speaker is our own Ariana Kresniak, which will be speaking about RDEs and be giving an introduction to detonation. So be ready for the PA announcement.
Hey there, Rocketeers! Announcing our next talk is going to be about rotating detonation engines. That's going to be followed by Warren talking about filament wound airframe components. Don't miss out.
Okay, so we're right on schedule. We're going to continue to be introducing Ariana Kresniak. She has volunteered with Launch Canada since 2021, since the 2021 test firing campaign of the LR 101. While attending the Lassonde School of Engineering, she was an original member of Arbalest Rocketry, contributing to the design, build, and launch of the first 3 Goose rockets. She graduated with a B.Eng in Space Engineering in 2022 and gained industry experience at Avaya Aerospace and Pratt & Whitney, Canada. In 2024, she returned to academia to pursue a master's degree at the University of Waterloo and studying rotating detonation engines. She's currently launching CanDet to bring RD technology to Canadian markets. So presenting Introduction to Detonation, please welcome Ariana Kresniak.
Okay, let me get my slides, and then we could rock. Okay, clicker is not. It wasn't plugged in. There we go. Okay. Good morning, everyone. My name is Ariana Kresniak, as Cyril introduced. I was also including a little about me. So yes, I went to undergrad at the Lassonde School of Engineering, where I studied space engineering. But my issue with this is primarily satellites and not rocket driven. So while I was there, I went to my program director and vehemently asked, how can I have a rocket course and what can I do to make it happen? So I went to all the classes, I sat up front in front of everyone, all the mechanical engineering students, and said, who wants propulsion? And organized with my program director a proposal to the school. Ultimately, the program was too small to be able to have the pull to make the course. But I met the people I needed to start forming teams. And that's where we created our first Goose rocket. While this was all happening, this was during COVID, and I took part in the LR 101 campaign. You've seen me around test firing multiple engines through Launch Canada and launching multiple rockets. We were the first team to launch out of MLS, with reaching an altitude of 46,000 feet. So I've been around, and that's why I'm here to talk to you. Now, my newest project is Canadian Detonative Energetics, CanDet for short, where we're wanting to take rotating detonation technology and put it into turbines to produce power. Now, in order to bring you up to speed, our audience is pretty varied today. We have people with basic launch experience, so I'd like to do some background laying to really get the foundations. I'd like to talk about compressible gas and where that really comes from. So a gas in a syringe can be pushed down on the plunger and it can be compressed. There is room between the molecules where they can move closer together as opposed to a liquid like water. Now, this is significant because when we are moving through the gas, it will build up in front of an object, transmitting through pressure how it has to go around the object. This is significant. When we're moving at low speeds, we can basically assume that air is incompressible. But as you get faster, up to Mach 0.3 and all the way up to Mach 1, the density increases and it builds up and builds up. This is an effect to push air out of the way, because when you're moving through a free atmosphere, you don't have a plunger. Your vehicle is representing the plunger, and the air has to get out of your way as you speed. Now, this is done transmission through pressure. This is molecules bumping into each other to be able to communicate upstream. You can think of this like if you're driving down the 401, you are the upstream, and an accident occurs downstream, it gets transmitted all the way up to you. You can't see the accident, but you feel the slowdown from 120, 130, all the way down to a snail's 30 kilometers an hour. This is transmission forward and backward throughout the stream. Now, when we're thinking about these pressure waves being emitted by an object as flow is pushed around, if that was to be a stationary yell, it's going to go out radially in all directions. But as you start to move, your new impulse or new emission point moves with, and your inner circles travel along. Eventually, when you hit a maximum speed that pressure can be communicated through the flow, you're going to be essentially turning your circles into a cone, which is where you get the fastest amount that it can move away from you. You can no longer hear your own shock diamonds. Now, as you can see, this is dependent on your velocity, some constant functions, but primarily it's to do with temperature. So we talk about Mach speed as being 343 meters per second, but really that's on the ground. As you travel up throughout the atmosphere or are local in your engine, it's significantly higher. So what's the point of all of this? The point is that you're building up pressure, and normally it's able to push the flow out of your way, but eventually it's too sudden of a shock. It can't get out of the way fast enough, and it still has to happen. Your vehicle is moving. And this is where you get a shock wave forming. If you can see this bullet flying through a Sheeran image, you see both a bow shock at the front that's built and lifted in front of the object, and then after you've shocked, behind it, it has to re-expand the density. So this is where you get expansion waves. Those are anchored on the shoulders of the object. And the whole purpose is that the shock is there to redirect flow. Its entire purpose, or it's a consequence of flow having to redirect around the object. So why am I wanting to talk about this in terms of engines? That's because there's multiple regimes of combustion. It isn't a different combustion, it's just that because we have this different subsonic and supersonic flow regime, we end up getting a difference in affecting the combustion. So all of your engines, every single one at this competition today, uses a deflagrative form of combustion. This means the propellants enter in and they're moving subsonically when they go through the reaction zone. It's a constant volume, or it's a constant pressure form of combustion, which means that all of the energy goes into expanding the gases and heating them up. And what's significant about this is that pressure waves can travel both forward and backwards through the reaction zone. Now, once you get moving supersonic speeds and you've created a shock wave, that shock wave couples with the reaction zone, and pressure waves can no longer travel upstream. So they can only be transmitted from the downstream up to the shock wave, or from the upstream down through it. What this presents is a constant volume form of combustion, and it raises the pressure as a result. Now, this creates a structure where your pressure spikes and then decays exponentially. The shock wave increases the temperature of the reactant to their ignition temperature and then entrains it into the reaction zone. This is significant. If you have colder propellant, you'll have a larger temperature increase due to the shock. Oh, actually, as one more comment, this also is representative of a gas turbine purely driven in the physics, where you have the shock wave as your compressor, the reaction zone is your combustor cans, and then behind it, where you have to expand the gases again as a result of the shock, you have a thermal choke that acts as your turbine. So it's a gas turbine essentially represented entirely by physics. Now, you can see in a representation of what's called a shock tube, you have your reactants entering into your detonation front, a spike in the pressure, and then an expansion behind to your product that has overall increased your pressure, which is significant. When we talk about our rocket engines, we typically look at them as being a pressure-driven system, where you're going from a high pressure field in your tanks and following your pressure decay throughout your lines, valves, manifold, injector, and then into your reaction in the chamber, and then again out your nozzle. This is representing a pressure gain system instead, where instead of having to have such a high pressure in your tanks, you can have a low pressure going into your injectors and gain pressure as a result of your combustion. But what even is a detonation to begin with in terms of how it's forming? Well, when I say detonation, I imagine every single one of you imagines a boom, and that's accurate. It's no different than a sound wave, but when I communicate with a sound wave, it's very low amplitude. And so fluctuations in the local temperature aren't really as significant. But when we're talking about a significantly high amplitude wave, you have a huge temperature spike that comes with it. And what this results in is that at the very top of your wave, you have a higher local temperature compared to the bottom. So you have a higher sonic condition. So the top of your wave is able to travel faster than the bottom, and it catches up and transitions into being a pressure plane. And that's your blast wave. You can see that your blast wave spikes, and then you have an expansion behind it that actually underdrives the pressure before normalizing. But that's a typical blast wave. Now, our other significant point that I'd like to talk about is when you have your shock waves and your detonation waves colliding with each other, such as reflecting off the ground, they meet together in a triple point, where and it's where you have your primary shock detonation, the reflection, and then behind it a transcendental wave that breaks off. This reflection is called a Mach stem. And here's a diagram of it actually being recorded, where you can see your incident shock is significantly lower in energy, your triple point in the middle, and the Mach stem leading your reaction zone. But what do we do with this in terms of an engine? How do we get thrust out of this? How do we make this usable? So far, we're talking about an explosion. We've seen a diagram of it detonating in air, but that's not what we care about. We want propulsion. We want movement. And so let's talk first about a pulse detonation engine. A pulse detonation, or to build to it, when we have our detonations, we use a thing called a Hugonio curve. This is quite simple. It's both this and the other line I have there, the Rayleigh line, are derived simply from governing equations from the conservation of mass and conservation of momentum and conservation of energy. A diagram like this is the ratio of a pressure-volume relation before and after the detonation. So the curve is called the Hugonia, and the lines connecting them are called Rayleigh lines. Basically, when you're crossing the detonation, the change of state goes from the locus, indicated as IC, up to your solution, and then it rides the Rayleigh line down to your next characteristic Hugonia. And this is how you transition states across the detonation. Now, the regions below, indicated on the graph by 1, 1, there's no solution there. Regions above, down in this region here, we have no solution. Up out here, we have no solution. We only have solutions for combustion in these regions. Down here is our deflagrative solutions, and up here are our detonative solutions. And the only solutions that exist are where the Rayleigh lines intersect with the Hugonia curve. Now, the most ideal detonation, called the Chapman-Jouet condition, is when the Rayleigh line is tangent to the curve. That's a perfect detonation, but the reality is that that doesn't exist in real life. Now, so we have up here would be the strong detonation, the weak detonation, weak deflagration, and strong deflagration. What ends up happening is that the strong detonation is highly unstable, but the weak detonation is not particularly powerful. So you are trying to have the ideal solution where they're just tangent, because then they have both converged into the same point, meaning you get the strongest effect and the most stability. What ends up happening in practice is that you aim for trying to achieve the strong solution and decay into the weak solution. Now, the thing that's significant about this is it's changing the combustion cycle. Normally, we would look at a Brayton cycle for a gas turbine, and everything within the curve is our usable work that's generated by the engine. Detonation can be closer represented with what's called the Humphrey cycle, and better than that with the Fichet-Jacob cycle. And as you can see, it peaks, and going this way is decreasing your volume, so it's condensing the fluid, and increasing the pressure. More importantly, over on this side, where we have the dashed lines or the Brayton cycle, and the solid line is the Fichet-Jacob cycle for detonation, this is the entropy line versus temperature. So we are increasing the temperature, but decreasing the entropy that's been produced, which is why it's an overall more efficient form of combustion. The claim is that it can be as high as 25, 30, 40% more efficient. But that's the theoretical claim. So let's tie it together and think of it in an engine. The cycle of a pulse detonation engine. A pulse detonation engine is literally just a tube that you filled with gases and ignited at a detonation condition. So you have a cycle for your condition where you fill it and then ignite it. A shock wave begins to travel down your tube, coupling with the reaction zone and transforming into a detonation. It expels gases and emits a shock wave. The pressure is your thrust. However, it's expanded behind it. So now it has a low pressure behind it in the tube. It is reflected back into the tube, where it has to then reflect off the end to then purge the gases and then begin refilling. This is a 7-step cycle, traveling through the tube at kilometers per second speed. But the struggle is that you have to reignite it every single time. So you just give it a pulse of thrust. Now, the solution to this is to put many tubes beside each other and set them out of phase. So they're pulsing thrust, but going pop, 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 pop. And that begins to feel more continuous, even though it's still discrete. But that doesn't do a whole lot for us. But what's going on in that tube? You can't directly ignite detonation in a gaseous mixture. There isn't enough energy density in the region that you're igniting. It's not combusting fast enough. So we have to start with deflagration and transition it into detonation. This is done with what's called a Schlecklin spiral. I know I pronounced that wrong. Where you've created an obstruction in the flow that the flame anchors to. See, what's going on is it's called the flamelet model, where the reaction through the flame is happening at a significantly faster time scale than any sort of diffusion or convection in the flow. So we can assume that the flame is very thin. Not infinitely thin, but very thin compared to the rest of our flow. Now, as the flow accelerates, turbulence in the flow creates pressure perturbations ahead that travel through the flame, as we discussed. And this wrinkles the flame. As the flame wrinkles, you're stretching the surface of it and creating more surface area, which accelerates the reaction, because a higher surface area of your reaction zone means more reacting fluid moving through it, which then creates more pressure perturbations, more turbulence, and then stretches it further into a large bend called a corrugated flame that then accelerates the flame. The pressure perturbations ahead, because you're producing pressure, build up together until they've produced a sudden shock wave, and the shock wave and the flame couple together, producing the detonation. Now, in recent studies, at this point about 4 months ago, this was produced with, instead of using the spiral, which is there to obstruct the flame and anchor it using wall viscous boundary layers, what they did was they lined the tube with copper foam. What was found was that the flame diverges into the foam, and that causes it to stretch very quickly and suddenly, which accelerates the flame. Moreover, the pressure perturbations ahead also diverge into the foam, which decelerates the shock wave. So it facilitates a transition from deflagration into detonation significantly faster than the spiral would, shortening the distance. And then over on the side, you can see the transition of the flame wrinkling until it becomes at the end a flame, a reacting plane. Okay, so we've talked about pulse detonation, and we're understanding that it's just giving us those little hits. How do we get it to be more continuous? And that's where we come to our rotating detonation engine. Because if we take an annular shape and we inject the detonation from a pulse detonation, we can start with a detonation already ready to go. This is significant because even if we could directly initiate detonation inside of this annular shape, the wave would go in both directions and then smash together and snuff itself out. So instead, we're able to start it with directionality, which is why I describe PDEs as an RDE igniter, because that's exactly what it is. And so our RDE is created by having an annularly shaped chamber instead of a cylindrical chamber. There's fresh propellant fed in from the bottom, oxidizer and fuel, that is eaten by the wave, and you have until the wave comes back around to put another round of fresh propellant. So the wave is able to continuously travel around the chamber. Here you can see that our wave leads the front, and then we have a shock wave breaking off behind it, and a slip line where our burnt propellants that are being accelerated by the shock wave meets the fresh propellants that are being injected behind. And this cycle turns the flow to be able to give thrust and propulsion out the back. Now, immediately you're probably thinking, well, that's not continuous either from the exit plane. You've got now thrust going around and around and around and around. How is that axially in line? But what ends up happening is that the wave is traveling again at kilometers per second speed. In, say, hydrogen and oxygen mixtures, the ideal version is 2.8 kilometers per second. In something as a liquid like ethanol, you're still getting 1.8 kilometers per second speed, so significantly faster flow rates than what would occur in deflagration. So from the exit plane's perspective, it's getting that thrust at 10,000 hertz, so it becomes a continuous plane. Now, in the more idealized case, you can see we have a reactant layer being fed in, our expansion wave, and so you have a pressure jump across the wave. Then you have your, the wave is moving much faster than the gases that are produced. So you have an expansion behind it. And again, we were talking, the expansion and shock waves, their role is to turn flow, to redirect it. So the expansion wave redirects it to be in line with the contact surface between the two. And when that travels around on the next pass, the shock wave turns it again to accelerate it out. But we've been talking this whole time about the macro level wave. I keep saying the wave, singular. But in fact, there is no singular wave. There are many waves down at a micro scale. If you take carbon paper and line the inside of the tube, what ends up happening is it imprints these diamond type patterns. They're called dragon scales, and this is the highest pressure point imprinted due to the detonation passing. This is a two-dimensional representation of a three-dimensional structure, and you can see that they're moving through time. So this is the highest pressure point, the Mach stem that we were talking about, and each cell represents a single wave. So here, moving forward, we have two triple points, and this wave cell is expanding. It's even better than the ideal condition. It's at 1.6 times the ideal speed, but it's quickly decaying. And by the end of it, it will be at 0.6. So we're not actually achieving an ideal process. We're sort of quasi-getting it, because the ideal process exists only in a free-moving detonative wave from an explosion. And we're trying to contain it and make it usable. So it's close enough. Here, on the opposite side, what we're seeing is that this wave is now decaying. Because the triple points expand, you think of it like a kaleidoscope of a wave decaying, and the waves around it are expanding into its space. And that's because behind it, we have transcendental waves that are redirecting the decaying wave's energy into the expanding wave's energy, which is how we get our balance. The whole purpose is to first shock the propellants to ignition, ignite in the reaction, heat them up and raise the Mach speeds so that sonic conditions can redirect energy forward and drive the wave like a piston. And so here you can see the individual cells in measurement and simulation. Now, these cells are used as the characteristic length for designing the engine. The entire sizing of it, the annular track size, the length of the chamber, are all determined by the characteristic length, which is the detonation cell width. And this changes and varies from propellant to propellant. So for hydrogen and oxygen, as an example, your engine could be as small as the size of a coffee mug. For air breathing, it increases by a factor of 10. But there's significant challenges in this engine. It's not perfect. The wave is producing significant back pressure. In a deflagrative engine, the rule of thumb is to have a pressure drop of 20 to 40% across your injector to prevent backflow. But if my wave is shooting up to 100 atmospheres, 200 atmospheres, do I need to make what I'm feeding it with 400 atmospheres? How am I going to contain that? That doesn't make any sense. So you have to let the wave produce the pressure for you. And that means you can be feeding it with significantly lower pressures. Case in point, a hydrogen engine can have a feed of only 275 psi feeding into your chamber, while your chamber then produces at the wave 600 psi. And that's because the pressure is only localized on the wave itself. It decays exponentially behind it and produces an average chamber pressure of only 60. So what ends up happening is that the injector ports where the wave is passing over are constricted. You have choked flow that you risk becoming unchoked. So that's what's setting how high you have to be feeding the pressure into your injector. And then it recovers. This is called the injector stiffness, and then begins producing additional pressure or additional propellants into your system. But you do not have a lot of time for this. With the wave speed so high, you have nanoseconds to recover, and then a microsecond to produce fresh propellant into your engine. What this means is that your flow rate has to be coming out of your injector at 1, maybe 200 meters per second. So that's one of the significant challenges that this engine presents. Now, the issue is, if theory is claiming that it's able to be so efficient, we've seen the pressure gain in experimental studies, but we haven't seen the efficiency gain. There are significant losses still within the system. And the reason why theory hasn't been able to represent it as well is because it's extremely expensive to simulate. This image is depicting a constrained detonation down a tube. And it was work done by Jackson Crane at Queen's University, so shout out to Queen's. And it's representing only 12 millimeters by 12 millimeters by 12 millimeters. But it took 10 million core hours to produce. This is because the wave itself, since you have a shock wave at the front, in order to resolve it, you need to have at least 10 cells across the shock wave, and each of those cells need to be microns in size. So if you are to produce a simulation representing that for your entire chamber, it ends up being 300 billion cells, which even on Canada's most powerful supercomputer will take 2 months to run using the entire computer. And a singular researcher doesn't get the entire system. So this is where, to deal with this, we've applied adaptive mesh refinement, where you can refine the mesh locally based on a threshold, like your pressure gradient, and have it be a very coarse geometry mesh feeding into a very fine mesh localized at your shock wave. This also gives you the advantage of being able to easily identify your shock waves just based on your refinement level. Yep. So we're going to end on some pros and cons about the engine, where theoretically it has a much significantly higher pressure gain or efficiency. We're not there yet, but we're moving closer constantly. The main advantage, though, is that since we're setting it on they're sizing it based on the detonation cell size, which is millimeters in scale, the engine itself only ends up being 5-10 centimeters across and in length. So you have a significantly smaller engine for mass reduction and volumetric savings. Case in point, when you scale up, Venus Aerospace down in Texas launched a 2,000-pound thrust engine that is only 8 inches in diameter, 6 inches long. So significantly smaller than the LR101 that is producing 1,000 pounds of thrust. So reduced mass and better volumetric packing because you can nest them inside each other. And because of its annular shape, it pairs perfectly with an aerospike, which can collect half as much thrust from the system alone. But there are some dangerous challenges as well. Compared to a deflagrative engine, you have no standoff distance in a detonation because it is right against the injector. And as we discussed, it's extremely expensive to simulate, so it's hard to refine your problems. Thank you very much, and have a great day.
We have time for one short question.
Talk to me after.
Okay, on that note, thank you, Ariana, for your presentation. Okay, it is 11:34, which means it is the time to have Oranos Polytechnique, our next speaker. So I'm actually quite looking forward to this talk. I was walking through the exhibit the other day, and I saw this wild two-stage rocket in the middle of the arena with gorgeous outer diameter transitions, carbon fiber top, fiberglass bottom. Anyways, I don't want to like ruin the surprise and spoil it for you all, but it turns out that that is what they're here to talk about. This beautiful airframe from Oranos Polytechnique Montreal, and they're going to present this technique and how they were able to achieve it. And let's talk about Oranos a little bit. Oranos is a team of multidisciplinary students from Polytechnique Montreal whose objective is to design, build, and operate high-powered rockets. The club represents Polytechnique Montreal at international competitions such as the Spaceport America Cup and uses its activities to develop Canadian expertise in the space industry and share members' passion for science and space. It also gives future engineers the chance to apply classroom knowledge to concrete projects. The session will explore advanced manufacturing techniques for compression molded fins and filament wound sections. So coming from Polytechnique Montreal, please welcome our next speaker. And once again, for those attending the live stream, feel free to ask questions in the chat. I will be monitoring it and be happy to ask them for you. So everyone, please, Polytechnique Montreal.
So hello everyone. Our presentation is going to have two parts. So one part is going to be on our fin manufacturing, and then the second part is going to be on our filament winding process. So for fin compression molding, we developed a new process in the past 3 years using compression molding to build our fins. So full carbon, we're stacking plies and we're heating and compressing the layup. And it replaces very costly CNC machining for the shape, especially since we don't have access to machines that can, well, the school doesn't let us machine composite in Polytechnique Montreal. So it's very low cost, very easy for students to make, and it takes about 20 hours between the time that the CAD is ready until the first fin is ready to be bonded to the fuselage. So over here we have a picture of the fins of Plutos that we launched last year, and that we're also launching on as I Sustainer this year. So the previous fin manufacturing Oranos was using was a layup of a carbon plate, and then we would machine it externally to have the desired shape. We would have blunt edges, and we wouldn't be able to have like a taper on the fin, and machining was extremely expensive, and we also had lead time for machining, so really not very accessible for us students. So the new process was to determine a ply count based on cured ply thickness of the prepreg we were using and the fin thickness. Then CNC machining aluminum molds. So we have the molds at the bottom. We would then slice the CAD to have different templates for the different fin layers, and we would cut them. We tried cutting them by CNC, but it was very slow. We had to have many G codes for the different shapes, so we decided it was just easier to cut them by hand. And we have the plies at the bottom in the two pictures for two different fins we did. We would then lay up the fins in the molds. So it's way easier when you have good prepreg that has a good tack. And if not, we would heat it a bit until we were able to stack all the plies. And then we would compress the layup in a 20-ton autoclave press and cure it at 95 degrees Celsius for about 12 hours. So we see at the bottom a fin that was cured. Might not be that visible on the picture, but we see some resin excess that was pushed out of the fin. So really good indicator of a good carbon film. We would then demold that part and sand cut the edges until the fin is exactly like we want it to be. So we actually have that fin and the mold at our table if you want to come and see it. So what's great about that process is that we have continuous plies from the root until the tip. So the last plies we put on both sides are continuous and they cover all of the change of section. We get clean, sharp leading and trailing edges, high fiber volume content, and very low delamination, especially since we have those plies at the top and bottom that just cover everything up. We can easily adapt that to any type of prepreg system as long as autoclave is possible with that prepreg system. And there's no limitation for geometry as long as you consider good demolding angles. So over here we see the section of the fin that was used for Demas, our sustainer for the IREC 2025 competition. It's very accessible, as you probably saw through the process. So everything is done by the students, from machining, cutting to layup. There's no really need for advanced composite machining. We don't need an autoclave. We just need a press that can heat. So it's not very big equipment either. Minimal cost. We just need the materials to make the molds and cut the plies. We can make 3 fins in 3 days since the process is really quick. All the plies could be cut at the same time. And if you have many molds, you can even cure them all at the same time. And it enables hands-on student fabrication with basic tools. It's compatible with most prepreg materials, as I mentioned earlier. So conclusion on that is that it's reliable, repeatable, and very low cost. So we've manufactured like 5 sets of fins with that technique in the past 3 years. It's structurally robust and fight ready, so very minimal adjustments made after demolding. And it's already been proven with integration through various airframes. And future works would be to better calculate mechanical properties. So the fiber we use is not périmé, I forgot the word for that. So we would want to test it better and be able to have really good qualifications of the properties, and then doing micrographs to have values for the fiber volume. So I'll let Gabriel Poirier and Gabriel Bois talk about filament winding.
Hi, my name is Gabriel. I'm here with my teammate Gabriel. So we're both working on filament winding for the past 2 years. So the first year was about testing everything and trying to understand how it works. And then the second year, the last year, we were able to start making some real parts that we're gonna fly this week. So for filament winding, it's an additive manufacturing. It's a process that consists of winding a filamentary material under tension with resin onto a mold, a rotary mold. So it's just one piece of filament. You can use it with fiberglass, carbon fiber, and also with Kevlar. It's really strong for a lightweight compared to other process. You can choose the fiber angle that you want. Also, you can make the geometry that you want as long as there's a revolutionary angle. So not just like cylindrical parts. So that's why we use it to make the nose cone and the transition. It's used for fuselage in rocketry, also pressure vessels, automotive drive shafts, and Gulf Club shafts. But there's a lot of challenges with this process, like getting the best angle of winding possible, demolding the parts, and then the thickness, controlling the thickness of the part. So here we'll look at the process of filament winding. You start with continuous rovings of fiber. In our case, we use fiberglass. And then you combine the different filaments if you have more than one. It then passes through a resin bath where the filament is impregnated with resin. Then you got a roller that removes the excess of resin. And then it goes onto the machine that puts the filament at the right place on the mold with the mandrel rotating.
All right, so now I will talk to you a little bit about the winding angles. So just for the definition, the 0-degree angle is parallel to the axis, and the 90-degree angle is completely perpendicular. So I'll tell you a little bit about the challenge of the winding angles. So first of all, the pros of increasing the angle. So basically having the angle more perpendicular to the axis is that you can wind better in concave geometry. So what I mean by concave geometry is you can see on the picture of the upper right frame, the red line represents what the fiber would look like if you wind it at a 0-degree angle. So you would have a concavity filled up by resin, but no fiber in this part. So this is the yellow triangle that you see between the fiber and the mandrel. So if you increase your angle, you can avoid this kind of situation. Also, by increasing your angles, you avoid the slippage. So in filament winding, the slippage is your biggest enemy because what you want is the fiber to be exactly where you predicted it would land. So if you slip, you're not at the place you're supposed to be, and therefore your part becomes just hazardous. So the other advantage of increasing the angle is that you can make friction turns. So this is a very easy way, I would say the easiest way to wind your parts. For example, if you have just a big cylinder, you can just make friction turn at every end, and this will give you good results, but you might not have the exact angles that you would want in this situation. So that's the reason why you have pros also for decreasing the angle. So as I said, most of the time it's closer to the desired pattern, because as most of the parts we make work in compression during acceleration, you want the fiber angle to be as close as the axis. Also, it allows you to have ellipses at the end of each part. So once again, this is an application as an alternative of the friction turn, and this allows you to have a better winding angle for your parts. So here you can see what a good winding angle would look like without slippage. So every fiber is equally spaced, giving you a smooth layer surface.
So now here's a look at the machine that we bought for this project. So it's the X-Winder 4-axis. You can see the machine on the left. So on the image you see the carbon fiber used. In our case it's fiberglass, but it's still similar. So the fiber goes through like tension system. Then it goes in the resin bath where it's impregnated, and then it goes to the head of the machine, and you see in the back the rotating mandrel. So that's how it works, and we have a little video. That's our one of our winding, and you can see how it works. So we have like a friction turn at the end, and then it comes back. So yeah, that's about it for this process. And on the other end, there's like an ellipse. Yeah. And so I'm gonna talk a little bit about the test that we made, because at first it was really hard just to be able to work with this machine. So on the right you can see the first test that we made. It's not great, but we were just happy that the machine worked. So there's like too much epoxy, and also we had a bad filament that we used. It was really hard to work with it. It would always break. So That's why it looks like this. And then on the left, you have the second test that we made. Much better. It's not as thick as the other one. But for those two parts, we didn't use like reusable reusable mold. So we would just destroy the mold to get the part. But in our case, for the real parts that we want to do, we want to be able to reuse the same mold like many times. So that was just for testing, but it's not the same process for the real parts. And after we were done with those tests, we went to test on the nose cone. So that means that we have to do like a perfect code because the machine that we bought comes with a software, but it only generates codes for cylindrical parts. But for the nose cone, we had to make our own code, and then here's a test of the code. Unfortunately, we were not able to demold this part because we didn't really think that much about demolding it. It was just to test the code, but we're gonna talk about how the demolding process works now.
All right, so as my colleague mentioned, the previous part that you just saw still sits on the main roll, so obviously not ideal for flight. So quickly we came to a solution to unmold our parts. So what we wanted is a quick, cheap, and easy process to have a iterative design. So we came up with this wax bath solution. So essentially what you see on the right image is boiling water. On the top is hot wax heated by the boiling water. So the wax is melted, and then we have the mandrel rolled into it. And what you see on the side is the wood plate that remove any excess wax. So this gives us exactly the right dimension and the curve that we want. And it allows us to melt the wax during the demolding process to release the part easily.
So then, once we were able to demold the parts, we were able to make some tests because it's really hard to like make some analysis about filament winding because of the shape, and you cannot predict like for sure how it's gonna break. So we did just some tests with thin layers, like 2 layers for a transition and 2 layers for a nose cone, just to see like what would be the resistance. And we were really happy with the results. We had 36 kilonewtons for the transition, and then 31 kilonewtons for the nose cone. So we knew that we would be good for the other parts because for the real parts we use at least like 6 or 7 layers of fiberglass.
All right, so now I will talk a little bit about the improvements that we want to make to our process. So first of all, the programming. So the machine that we bought comes with a software that is very limited, especially for complex geometry. So what we did this year is that we had a custom G code written by Python code. So this allowed us to bypass the software but still use the G code of the machine. This year, what we want to make is to completely bypass everything that is related to what came with the machine. So we have our own software, and we directly speak with the API of the motor controller to avoid any slippage during the winding. So what you see on the screen is our new process. So what we want to do is to have the curves inside it works directly on the parts representing the winding pattern, and then export this curve via macro directly to our custom software that talks to the API of the fidget controller of our machine. So this allows us not only to be much quicker because we can iterate in SolidWorks and then just send it to the machine and it will wind the exact pattern that we give it, but also it allows us to extract this curves and use it, for example, in simulation such as ANSYS composite. So with the same curves, you can wind on one side and on the other side put it in ANSYS composite and make sure these two match together, so we can iterate and have much stronger parts with this process. So hopefully we can reduce a little bit the thickness of our fuselage and therefore the weight. Another improvement that we want to make this year is to add more filament during the winding. So what you see on the screen is the double winding that we experienced during our last winding for the nose cone of our flying parts. And so as you see, there are two fibers coming into the resin bath, and then they are merged together on the roller directly on the surface of the mandrel. So this is good because usually when you have a single filament, it is the complexity comes to have each filament, as I said earlier, equally spaced. So what you want is to have them as close as possible, so you have as much density of fiberglass in your parts and not so much resin. The resin is just to glue them together, basically. And if we have two filaments, you can see on the screen that they are already merged before even touching the parts. So there is no gap in between them, and this is good for our ratio fiberglass and epoxy. Now I will talk to you a little bit about the sanding process. So as you saw in the previous pictures, the winding is not perfect. We have to make a friction turn, as my colleague mentioned, on the nose cone. So this friction turns at the tip of the nose cone builds up a very thick layer of fiberglass. So we have to sand it all. So we have basically a lathe that we can sand paper on with the parts turning very quick. So this also allows us to have equally sanded parts in the rotary axis.
So now, even though we're pretty happy with the job that we've done since the past 2 years, at the start we didn't even know how this process works. Then we made some tests that were not really great, as I showed you earlier. And now we have made 4 parts that are flying for this year with 2 extra. So as you can see there, we got a nose cone that we're gonna be flying this week. So you can come check it if you want. And for the next year, we would like to increase the number of layers that we use to make the process faster. Then we would like to have a tension system that works really well, because now it's just me like holding the filaments to put the right tension on the fiberglass, so that's not ideal. I just got 2 ends, so we cannot use more than 2 filaments. Then we would like to be able to predict the resistance of the parts with like finite elements, because now we just like break the parts to see, to have an idea of how strong it is, but we don't know for sure for bigger parts and thicker parts. And then we would also like to improve the sanding process, because it takes a lot of time, and it's hard, like with our hands, to get the best surface possible. Thank you, everyone, and if you have any questions, you can ask us, and also Anne-Sophie will come if you have questions for her.
Great presentation. Do you have any questions for Oranas? I can maybe start the ball. I have to say how impressed I am that you went from idea to purchasing the equipment, to programming it, to sending it, to testing it, to validating it, and improving it all in the span of a year. That's very impressive. The fact that you even have parts today that are built that way. That's very impressive. And I think that after this talk, we'll have a few teams that will want to do something similar to improve the performance of their parts. Any advice on where to start and how to make this happen? Having gone through it yourself from the start?
So yeah, for sure, this process came with a lot of challenges. So as I mentioned, the unmolding process. So obviously, when you're trying a new process like that, you take some risk. So for example, we didn't want to machine. We could have just machined aluminum mandrel and wind on it and have the unmolding process by just putting it in the freezer. But because it's so new and we have such a low confidence in this new process. You have to take it one step at a time. So that's why we came up with cheaper solution for unmolding. And yeah, I would say that really take it slow. Sometimes it's good to have feedback from people who already made it also. And yeah, if it doesn't work one way, don't try to push it forward. Try to maybe find another, and most of the time there is an easier way.
Thank you. We have time for one more question. Awesome. I also want to say the wax approach to be able to demold your mold, great idea. I'm going to steal that.
I was just wondering, for example, you're using fiberglass for the mushroom and everything, but for example, if you were to use instead like carbon fiber, like you said, Kevlar, would it change anything to the process or something, or would it be like exactly the same process, you just change the material?
Yeah, so yeah, exactly. So the fiber is the skeleton of the part. So obviously you can change it. You just have to include it in the way that you design the curves of your path of winding. So essentially, what would change the most is the width. For example, I think carbon fiber tape are much bigger than the fiberglass tape, or it's like 2 millimeters wide. So yes, but yeah, but it would be a lot easier because, as I said, one of the biggest problematics of little tape is that you have to put them close together enough so there is not too much resin in between each of them. So the bigger the tape you have, the less of this gap you have, and therefore a better port.
Beautiful. Everybody, please congratulate Ornos Polytechnique. Thank you for your presentation. Thank you. This brings us exactly to noon, which is lunchtime. But we have one more group of speakers that would like to say a few words before we leave for lunch. They came from very far. They traveled intergalactically to interstellarly or intergalactically, which would be the most proper term. One of those. They'll come to give us a few words before we leave to go have our own sustenance. Please welcome the Klingons to the stage.
Katlok Tarangan. We are here from Keynote. We were invited to come and learn about human technology, and we've noticed one thing. Humans do better when they collaborate with each other, and eventually collaborate with other species in space. All of us are interested in science. We're interested in discovery. We are passionate about precision, about creating something that no one else has done yet. We are passionate about being the first ones to achieve something, to make a difference for our planet, for our countries, for where we're from. But there's something that glorious wars have been fought over. Unfortunately, if we're fighting, that progress can't happen. And that is multicultural communication. We've noticed here as Klingons walking among humans that humans are very social beings. Humans will walk up to us and say, "Hi." Klingons do not have a greeting. We do not have a word for hi. Klingons are very focused on the task. What are we doing? What do you want from us? So hi is like, you're being rude, you're wasting my time. We have things to do, we have places to be, what do you want? So you're likely to get the response, "Nuk nech," which means what do you want? Now we have a human looking at us saying, this guy's rude. I just went up and said hi, and they're demanding to know what I want. And now they're staring at me because I don't know what's wrong with this guy. And then we have to pull out our bat'leths and fight him. No? Humans would say that's a little bit excessive. I've been told that. I've been asked to leave. On Kronos, that's the way we handle our issues, and that comes down to the multicultural communication we're talking about. Because amongst humans, it may not be that much of a difference, but there's still a difference. We need to understand each other. So once again, I thank you. I appreciate the invitation, and we would like to wish you Kapla Battle Jack, which means success and honor in all you do. Katlo.
I will not say hi, and I will still steer clear. So on that note, thank you. And I don't know what Klingons eat, but we will go have some smash burgers. Thank you, everybody, for coming at this first half of the second day. I'm looking forward to having you for the other part of the day, the afternoon, which will have a lot of other interesting speakers. We'll talk about more tech dev. We'll have a talk about our main sponsor, MDA Space, and we'll also have some more student speakers. So everybody, please come back this afternoon, and thank you for attending the morning. second day at the Launch Canada conference. This is the last part of the conference, so I hope you're going to enjoy and suck in every instant of it, because after that, we're at the launch site with the mosquitoes. So enjoy the nice weather, the roof over our head, and the Wi-Fi. We will start the next team, and the next team is quite a historic one, I'll say. And before I talk about the team, I just want to give a quick overview of what we're going to expect for this afternoon before we get started. We'll have Arbalest Rocketry that will present. Then we'll have one tech dev team, which will present a rocket tracking camera from Rockets. And then we will have Adam Lackman from Airjet Rocketdyne to talk about his Rocket Facts Live. We'll finish these speakers with Mac Tapazoli from Transport Canada, which will talk about orbital launch safety. And our last speaker will be our keynote speaker from MDA at 3:15. So please attend for that one, where we will talk about our future in space. But now on to the team that is actually next to the podium. It's a historic one. It is the very first team to ever launch a rocket from the MLS launch pad in Nova Scotia. And that is our national launch pad for the moment. And that rocket, Goose 3, was a multi-stage rocket. Today, they will also present a multi-stage. And the presenter, Nathan Minuk, and I think there's two other presenters. Nathan is a second-year space engineering student at York University and president of Arbalest Rocketry. He has dreamed of designing spacecraft like many of us and rockets since childhood, a passion that has led him to join this team, to join Arbalest Rocketry, and later grow up the ranks and lead the team. Nathan and his teammates are working to design and develop rockets, such as the Goose rockets, to gain hands-on experience and pursue their shared love for space exploration. So they fit perfectly within this competition. So presenting now the development of Goose 4, a multi-stage solid rocket, please welcome Nathan Minuk and his colleagues.
Yes, thank you so much for having me on here. Today we'll be discussing, well, just how we developed our current rocket, Goose 4. There's a lot that went into it, a lot of hard sweat and tears, and we're happy to show it off. All right, so welcome to our presentation. Before we can get into just the overall design of the rocket, I think we should give some background into Arbalest Rocketry itself, because I don't know if everyone here is familiar with us. So basically, we started off back in 2019. We started with a very small team, basically worked out of their parents' basement. Basically, we all had the shared passion of, a love for rocketry and doing what we think is best, Basically, we, worked at our best. We didn't have the most when it came to funding, but, we still pulled together and made rockets, because that's what we enjoy to do. As you can see on the slideshow here, you can see our team in the bottom left corner when we designed and launched Goose 2. Then in the top left, you can see Goose 3. And on the bottom right, you can see our current team now for Goose 4. As you can see, we've gone a lot larger since those days, and I think we're going to continue to get larger and larger with the coming years, as I have a lot of high hopes for our very talented team. So a few other things I want to bring up. We do lots of outreach here at Arbalest. So, for example, we've been to both, look closer. Okay. We've been to both moonshot events so far. We like to do an outreach outside of our university, and of course, a lot within. We've also been to a few other events, such as Industry Night, which is an event at York University where they bring over companies and other people from the industry to basically present and look around and try to recruit different people. York won us at Industry Night, and we gave a presentation, had a booth for people and employers to see. We also enjoy running tutorials for not only our members within our club, but people outside our club and within the university. Like, for example, we had Professor Hansen give a tutorial, well, two tutorials, to students relating to CFDs and the best ways to utilize and get started with Star CCMA, well-known CFD software. So there's a lot of things we like to do here and there to try and do plenty of outreach and help as many students within and outside our club as possible. As we're all here to learn, and it's best to help everyone get hands-on experience. That being said, Goose 4 is a pretty new rocket. It is part of a long line of rockets that we've had since our founding of the club. Goose 1, unfortunately, never actually came into fruition. It never left the design board, mainly due to COVID-19. Then we had Goose 2, which was successful and launched at the first year of Launch Canada, and I believe got third place. Then we got Goose 3, which was a two-stage rocket that launched at MLS.
but unfortunately is at the bottom of the ocean and is no longer with us. Then we have Goose 4, which is the current rocket, another two-stage rocket, which we are expecting to be successful and actually, survive, unlike its predecessor. So let's hope for the best. Moving on from that, we'll go over the exterior and the interior design as a bit of an overview, then I'll elaborate a little bit further into the actual design of Goose 4. On the exterior, there's not really much to say. We have two sets of fins. We have 5 fins on the first stage, and then we have 6 fins on the second stage. And then not really much else to say. It's all made out of fiberglass, and we have a really nice finish, which is thanks to our sponsors. They did a really good job with that paint. But there really isn't too much to comment on the exterior. However, within the interior, we of course have our avionics bay. We have our first stage motor, which is a 98, and our second stage motor, which is a 75 millimeter. In the nose cone, we have space for the payload bay, which we're going to elaborate a lot more on what the payloads do exactly in a little bit. But for now, I'll just leave it at that. Then we have the first avionics bay and the second avionics bay. The first avionics bay is fairly standard. It has just a cot, so like Blu-rays and Blue Jays and featherweights for mainly for tracking the rocket and doing everything needed for flight. And we also have SRAT, which is a PCB, which I'll elaborate slightly more on in a little bit. That being said, when it comes to the actual operations of the rocket, what we plan on doing is that we're going to have our first stage ignite, and we're expecting to reach an apogee of around 10,000 feet. At that point, we want to deploy our main parachute, which is a 9-foot, and then of course the first stage is going to drift at the ground. Then second stage is going to ignite, and we're expecting for it to reach an apogee of around 27,000 feet. And then at that point, the drogue parachute is going to deploy, which then after it drifts for a while, we'll have main deployed around 1,000 to 1,500 feet. Then when it comes to propulsion, as previously stated, we have 2 motors. We have a 98 N5600 motor, and we have an M2080 motor. Unfortunately, we're supposed to have 2 98 motors on our rocket, but due to certain geopolitical issues, we weren't able to get the second 98 motor, so we had to downsize the second stage motor. That's actually also the reason why our fin count is not exactly, is a little sporadic, because we originally had an even amount of fins on both stages, but it became 5 and 6 to account for the change in center of mass that happened with the motor being changed. You can also see in the image the thrust curves for both the second and first stage motors. The second stage motor, unfortunately, not being nearly as strong as the first stage. I think it was around an average thrust of 2,500 newtons. My memory is not mistaken. You can also see the FEA. I ran on the thrust puck on the second stage to ensure that it falls within safety standards at Launch Canada, and just so it doesn't blow up the rocket, because you don't want that. When it comes to the overall construction of Goose 4, there was a lot of hard work that went into it, and there was a lot of really talented guys within our team that put in their heart, sweat, and tears into making sure that this rocket is in the highest quality that it could possibly be, and I think we did a very good job with that. So let's some overviews. So some of the manufacturing bits we did, like when it came to the fin can, we had like a fiberglass fin. Then we took a G10 plate, dremeled it out into the proper shapes we need for each fin. We then 3D print a jig to hold said fins into place. We would then epoxy them, wait for the epoxy to dry, apply fillets to them, and then do tip-to-tip layups on all of the fins. I believe we did around 6 tip-to-tip layups, if my memory is not mistaken. Some of the interesting methods we use for sanding the rocket and making sure it's of the highest quality. We have a mini lathe, which we then set upwards, and then basically put our tubes on it and basically start sanding around it. It's not a strong mini lathe, to be clear. You can stop it with your hands, so it's not too dangerous, but it's definitely an unorthodox means of sanding our tubes, but it worked well. You can actually see in the image in the bottom right, us actually sanding said tubes with on the mini lathe. We did it. Yeah, like 6 hours of sanding. It takes a lot of time, especially for the couplers, because they need to fit smoothly onto the main rocket.
If you sand well, you'll feel the results.
Oh yeah, and you can definitely see the results on our rocket. I think it turned out beautifully. So when it comes to aerostructure, we're actually been trying to get a lot better at CFDs, or computational fluid dynamics, because it's going to be primarily for future projects, but we also want to start getting better at them right here and now. We've been using a lot of ANSYS and a little bit of Star CCM, but primarily ANSYS to do all of our CFDs. And at first, they weren't the greatest, but I believe that our members have gotten more and more effective at doing said simulations. As you can see, like on the image, you can see like a pressure contour on the right. I believe this is when Goose 4 is fully assembled, and it's at the rail velocity, which is like 207 meters per second. So it's not at Mach speed. So you're not going to see the shock wave, of course. But you also see some pressure contours of like while showing the airflow to the left, which I believe look absolutely fabulous. Our CFDs are getting a lot better, and they were partially used to help with the trajectory analysis for Goose 4. But a lot of the experience that was learned through CFDs that we did on the Goose 4 model will be reused on future Goose models for something a little bit more sophisticated, but we're not going to talk about that here, of course. So when it comes to the another component of the aerostructure, one of the more interesting components is we have a fin can, which I showed off with the skiff here. Basically, the spin can is basically a can that's going to be spinning throughout flight. Unfortunately, only the first stage will have a spin can. The second stage used to have a spin can, but because of the motor downsizing, only the first stage will be operational throughout flight. And as you can basically see in that GIF right there, like the fin can has proven to be like very effective. We have ball bearings that are placed on to ensure that it has a very smooth transition, and the fin and the airflows can be pushed against the fins and cause them to spin really fast, which will help with stability throughout the flight. And we're hoping that our cameras will actually record the spinning fin can, so we can get a lot of footage and data off it for potentially future rockets in the distant future, hypothetically. So moving on, we also had the fin flutter analysis. To be honest, we had a very simple fin flutter analysis. This was taken straight from the Apogee website. We basically just, I made an Excel calculator and basically plugged in all our values, and this is our speeds for both first stage and second stage, which luckily will not snap throughout flight. Our second stage, flying at Mach 2.3 is when we can expect the fins to start fluttering, and then Mach 5.8 for stage 1, which makes sense when you look at the actual shapes of the fins. So yeah, then there's the avionics bay. This was one of the overhauled designs from Goose 4. Our avionics bay for Goose 4 last year was definitely not up to par. There was a lot of dangly wires and a lot of sleepless nights in a hotel washroom. But this year, luckily, there's none of that. No sleepless nights in the washroom. It's done, it's ready, and we have a lot more to show off than what we did last year. For starters, we completely overhauled how the cameras went in. Before the cameras were kind of like in place, and to get them into the fiberglass molds, you would kind of need to use like a tube to kind of shove them in place, and it was really ineffective. And yeah, well, integration was not great. But this year we actually have them on like a nice little hinge. So basically what happens is you push in the avionics bay and then they fall into place, and you can just screw them in. So it's a lot easier, a lot easier to develop in, just a better design in every single way. We also have our own PCB that our PCB members have been working very hard on, which they have done an amazing job. This is definitely something better than what we had last year, which was primarily just all costs, as the PCBs for Goose 4 never actually got into a finished product. So luckily, it's safe to say that we have some working here. We hope to get flight heritage from these PCBs, but we'll wait and see what happens. So there's also a bit more to show off with the PCBs. This is kind of like what they look up close up. There's two PCBs. They both have their own radio antenna and GPS. Of course, we'll be relying on the COTS throughout flight, but they're there to get extra data and just to demonstrate some heritage. So then there was another thing we redesigned, which was the launch lug. Last year we had a bit of an issue where when we put the rocket on the launch rail, let's just say the lugs started to bend a little, and that's not exactly ideal for flight. So we had to scrub because of that. So we went back to the drawing board and we had to redesign our launch lugs. You can actually see in the top right image the old launch lugs. Basically, it was just like an aluminum piece with like a hook that would attach onto a 3D printed launch rail. Basically, the idea behind it was that it would save as much altitude as possible, but because this 3D printed launch rail would fall off the moment the rocket leaves the launch rail, which is actually a fairly good design. We've used it on Goose 2 and we used it on other rockets, but like it doesn't work when your rocket's 42 kilograms. You start to run into some static load problems. So we had to change things around. So originally, like the first the design iteration of the fin or sorry, not the fin, of the launch lug, kind of looked like a fin almost. We're using a lot of CFDs to try and get into place. It basically, what we did, we took the original lug. We thought, okay, let's use that as an emplacement. We'll put it on and have like a hole that like secures the two. It turned out not to be the greatest design. However, we stuck with one component of the design, which was basically kind of like using that embedded piece that's flush with the inside of the tube and having the launch lug on it, like connected through a pin. So this eventually evolved into this current version of the launch lug, which is probably the most aerodynamic version of it compared to the previous iterations. And so far from all of our simulations, all of our testing seems to be perfectly effective. And I think it will 100% work on the launch rail without any worries of bending, hopefully. Then we have our biological payload. I will talk about the engineering side of it, but then I'm going to take it away to Sina, who is a biologist and is far more experienced with this type of stuff, as I only designed the engineering side of this. So I'll explain this as best as I can. So basically, well, actually, we actually have it here. So you see the camera? Yeah, so this is the biological payload, this one right here. Basically, how it works is that it has a camera inside right over here. So it's kind of hard to see, but there's a run cam that's going to record the entire, like the biological algae throughout flight. I'm not going to take this off, actually. And basically, it's just going to be doing that throughout flight. It's connected to another payload, which we'll discuss a little bit more in a little bit, but we'll get there when we get there. But yeah, that's basically how it works. Basically, the camera that's being used is the RunCam Thumb Pro. I added a few, I don't think you can really see them, but there's quite a few holes for venting because the last thing you want is this camera overheating throughout flight. It's secured with 4 M5 screws, which of course are threading into 4 brass heated inserts. So that's about it, really. I designed it so this thing's going to essentially have a 3D printed thread. The reason why is I don't want this thing spinning, because if it spins, because this is how it's getting powered, it's from this payload. And if this spins, this is getting snapped off, so you don't want that. So we're going to have a lock nut here and a lock nut here. This is going to make sure it won't spin at all, because spinning would be far from ideal, to say the least. So that's the main idea behind it. Outside of that, I'll let Sina talk about the biological parts of the payload.
Okay. So thank you, everyone. These guys are really interesting. Nathan just talked about the engineering bit of it. So you might be wondering, why do we need to engineer something that holds algae? Well, this is the reason. Here you can see an image of Pyrocystis fusiformis. This is our biological payload we will be flying on Goose 4. On the left, you can see a pretty clear image that was actually taken this morning from a microscope that we have on site. What's really cool about these guys is that they are bioluminescent under stress. What does that mean? That means that if you apply shear stress in any form, they will emit light through a chemical reaction. And what we're trying to study is to see what the limits are of these little organisms. And what we're going to do is place them in the payload bay. And once the rocket is launched, they will experience enormous amounts of stress, and they should bioluminesce pretty beautifully. There's some images online of these guys. You can see what they look like if they bioluminesce on the right. As you can imagine, a large population of them, it would just be a beautiful glowing vial. And another thing we're doing with the same payload, this is actually 2 experiments, is survivability study. So what we're going to do on the other payload is look how many cells are in that vial before launch and how many actually survive the launch. Now, you might be thinking, okay, algae, these guys, they seem very small membranes. How can they possibly survive a rocket launch? Well, they've actually adapted to high pressures and forces. They live over 100 to 200 meters underwater. So we have theorized that they could actually survive a rocket launch, but this has never been done before. So this will be the first time that these guys are placed in a rocket, and we should see if they survive. We should see some beautiful bioluminescence. And the data we get from this will actually guide further research into using them as either biosensors or different sensing organisms. And my own research is actually on these algae, and I'm hoping to get some really good data for my own research in September. So that's the story behind the dinoflagellants. Thank you. So Nathan can take over from here.
Yeah, I'll take it away. So then we have one more payload. It's going to be our vibration sensor. This was not made by me, so it's better for the person who designed it to actually talk about it. Do you want to do you want the slides?
Hello, everyone. Yeah. So this payload is a piezoelectric vibration sensor. Piezoelectric materials are basically, if you apply a stress or a strain to these, they create a potential difference. If you apply a stress and a strain at a specific frequency, you will get that potential difference, that signal at the same frequency. With this information, I decided to integrate this basically as a payload on the nose cone of our rocket. Obviously, the nose cone itself is going to have different vibrations from other parts of the body. A future goal with this payload would to actually, if we can show that these sensors can get accurate vibration data from the rocket, to have these placed throughout different parts of the body in the future. To test them, we've tested them at the vibration bed at York University, sending them through different frequencies. They've even been tested on, let's say, acoustic instruments. If you look at the image in the bottom right, that was actually placed on a ukulele. If you play the note E, it is roughly, I believe, 330 hertz. And you'll also notice another peak all the way to the right at about 660 hertz due to the acoustic qualities of the instrument. This is just one of the things that this piezoelectric material is able to pick up when it's sensing these vibrations. So this will be something very interesting to find on a rocket. And another unintended feature of this payload is that we'll actually be able to see at what vibrations the biological payload is seeing high activity. The camera will turn on at the same time as we start recording data, so these can be cross-referenced and hopefully add a bit more actual numbers to the visuals that we see from the biological payload.
Alrighty. So that is basically it when it comes to all of our payloads and basically all the inner workings of Boost 4. I want to thank all of our sponsors who made this possible. We would not be here without their funding and their help. I want to thank York and Lassonde for giving us a position in the Bergeron. Without them, we would probably be homeless right now and or operating out someone else's garage. So I greatly appreciate that they've developed more of an interest in our rockets ever since. I also want to thank all of our hardworking members who have put in all of their hard work and time throughout the year and throughout the previous year to make sure that we're here now at Launch Canada. It's a great pleasure to be here, and I'm just the president, but like most of the work really goes to everyone here. They put in a lot of work and they've earned their spot in this team. So I want to thank you all for listening to my presentation, and I want to thank the Lord, and have a good day, everyone.
I just want to add a small thing. Almost all of our team right now is completely new members just from the beginning of the year. Really only 2 members on our team have actually launched a rocket before. So this has been a completely new experience for all of us, and it's been amazing. So I want to shout out the entire team, as Nathan said.
Thank you. We still have time for 1 or 2 questions if you are open to it. Do you have any questions from the audience? I can maybe start it because I have to say, I think it's the first presentation where we see a full review or overview of a rocket here, where I really feel like I'm almost seeing a judging presentation. It's amazing to see it from A to Z and see the whole process from the payload to the spinning fin. And talking about greater picture and overviews, you have developed as a team historically kind of a family of rockets, where they've kind of progressed from 1 to 4. And can you tell us a little bit about the lessons learned that throughout the years you've learned and you've been able to bring from Goose 1 all the way to Goose 4, and how you do that knowledge transfer within your team?
So that's a bit of interesting question. So there's been a few lessons that have been transferred here and there. One of the biggest difficulties I would say we've had at Arbalest is that it's kind of a lot of the members who were previously a part of our club never really passed down much information as their achievements kind of went down with them. We've had a few people who left behind, like Jordan Berlin. We give a shout out to you. He has done a tremendous help in making sure that our understanding, especially of the manufacturing and just the overall design of rockets, like remain as we definitely learned like quite a few lessons here and there, especially from Goose 2, I would say, is where I think we learned the most, because Prime Deal was successful. But there's also a lot from Goose 3, but the issue with Goose 3 is in the ocean, so we couldn't get all the data for 50 years, which is a bit of a dilemma. But overall, I'd say it's somewhat difficult passing down the knowledge, but like with what we've put in place now, I think that won't be the case anymore. I've put a big emphasis on newer members and members who are here in this team to pass down knowledge and what we've learned from all of our activities to newer members, because I don't want any of that knowledge getting thrown away, because having to start from scratch all over again is not a fun experience, and having someone to mentor you will really help you a lot, because otherwise you're kind of just screwing over future generations of hardware team members.
Great answer. Thank you, Jordan, for sticking around and sharing your knowledge, both for Launch Canada and Arbalist. We really appreciate you. Jordan! Any other questions? Yes, in the front. I had a lot of fries today, so I'm going to jog.
So your rocket is going to go supersonic.
Yes.
At what altitude?
So I know second stage, that's going to be reaching, I believe, Mach speed. I believe probably, I'd say around 11,000, 13,000 feet.
So at that altitude, are we going to be able to hear or feel the sonic boom?
No.
No?
Sadly, you will not be able to due to the
Can you
orientation.
make it
of the sonic.
happen lower so that we can? That's awesome. Thank you.
Okay, so you've mentioned that the algae bioluminesces when there's shear forces going on, but there's also G forces going on.
Yeah.
Is there a way to separate the reaction to see the effect of G forces on the algae?
That's a question for Tina.
So with the current design that we have for the payload, you cannot. We're just looking at all the different stresses that are going to be placed on these dinoflagellates when we launch the rocket. So that includes vibrational, G-force, and shear. Again, the whole point of this is to just stress them as much as possible. We're not trying to isolate different forces. It's just a matter of what's the limit, can they survive this? Maybe in future payloads, there's been discussion of putting more accurate instruments or to control for different forces that are being applied, so we can study each individually, but that would be definitely a future project, which I hope to continue next year if I am still with Arbalist. So that's what I would say.
Wonderful. Thank you, gentlemen. Nice round of applause for Arbalist Rocketry. Wonderful. So we are right on time. I think there is a microphone that was left here. Is this for us? Is this? Watch out. Don't be scared.
Hey there, Rocketeers! We're teeing up our next two student technology development presentations. The first one is going to be Rocket with their rocket tracking camera, followed by a presentation from Moss about their freehand cooling system. Come and check it out.
Okay, wonderful. So we are now at the Tech Dev Challenge part of the afternoon of the second day of the Launch Canada conference. Thank you everybody that's here in person, and thank you to everyone that's on the live stream that couldn't attend in person but is still logging on. We have one more part of this conference after this one, so this is the before last, and we're going to enjoy every minute of it. And to start this Tech Dev Challenge section, we have another historic team. Actually, this is the winning team of the very first Launch Canada in 2022, Rockets. Rockets is Canada's most decorated high-power sounding rocket team, known for pushing the boundaries of rocketry. After attempting to break the Canadian altitude record with Takik, the team gained invaluable knowledge and set their sights even higher. They built Arrow, a 4-inch minimum diameter rocket to break the world's altitude record for an O-class motor. This small but powerful rocket reached Mach 3, the fastest of any student-built rocket in Canada. Despite challenges with waivers at this year's Spaceport America Cup, in less than 2 months, Rocket successfully launched bow and arrow, the first student-built two-stage rocket by a Quebec team in 2024. So now, representing Rockets, I'd like to welcome an elder of Launch Canada, one of our most loyal customers, someone that, like me, cannot retire and cannot get enough of Launch Canada. So everyone, please welcome Mathieu Gagnon. Does Arbalest still have the slide clicker? It's on the
Okay. Hi, Sharks. I'm Mathieu Gagnon from Rockets. I'm here seeking $0 for 0% of my project. Donations, however, are appreciated. So today I'm going to present the Woohoo computer vision tracking camera. So here's a short presentation plan of what we're going to cover today. So I'd like to start by introducing our team. Cyril did such an amazing job, so I won't get into specifics, but our team accounts for 31 active members working across multiple projects, 4 graduate program students, 26 undergraduate students, and myself doesn't count in any of those. We account for 6 active women in the club, and some of our accolades are listed below. Again, won't get into details. Okay, so today, technological advances enable us to explore areas that were previously inaccessible. Space exploration is a key example where it is becoming possible to collect valuable data and inspire future generations. The main objective of our technical demonstration project is to design an image recognition camera system for the Rockets Club to capture images and videos in real time during rocket launches. A potential market-viable rocket filming service will be developed as part of this project. So at the core of our system is the Canon CR-X300 that many of you may have seen before. Our team has also created a digital twin for this camera, allowing for theoretical testing without real-world environment rocket launches available. As many of you know, they're very few and sparse between with very limited launch windows. So this allows us to test and develop the system very easily without having actual rockets launch. It'll allow us to capture real-time footage, provide for great marketing and publicity opportunities, identify flight failures or events in real time, and create a market-viable filming service. So just a high-level overview of our system and how it'll be presented is that we have the Canon CR-X300, a Blackmagic Video Assist, which is a little monitor that allows us to see in real time. Multiple remote monitors placed throughout the site, so access for Rocketeers and Launch Canada live stream officials to be able to show the footage to everyone, whether they're at the launches or not. And an AI processing computer, which runs everything in real time, allowing us to track the rocket. So you might be asking why you should invest. Well, let me present you what our solution brings to the table. Technology fills a critical market gap, provides an affordable system that's autonomous tracking, so you don't need an operator present at all times. It's a vision-based rocket tracking system, so there's a lot less external factors such as GPS or radio telemetry, which could struggle from low signal availability. And it's specifically designed for the needs of student and educational launches. Having come from the same background, I obviously knew what some of the challenges and needs of teams were, and I spoke with a lot of the teams that are here today to address those specific problems. Finally, it enables students to simulate almost industry-grade operations by integrating object detection models in real time, predictive motion tracking, and automated gimbal response to those AI responses. So very quickly, I want to do a market sizing breakdown. Obviously, this being a tech demonstration, we did a lot of research into what the viability of this project was. So we looked at 3 key markets. the total addressable market, the serviceable available market, and the serviceable obtainable market. So very quickly, the descriptions are there. I'll just go over them super quickly. So the total addressable market is obviously all global educational, hobbyist, and small rocket launches. The value is estimated at approximately 50 million in terms of everything that's available to us. The serviceable available market narrows that down to North American and European student rocketry teams, small launch startups such as Nord Space or Reaction Dynamics, and aerospace research test facilities. That estimated value is at around 4.5 million annually. And finally, our realistic serviceable obtainable market for the first 1 to 2 years is narrowed down further to Canadian, US, and select rocketry teams and events targeted. So Spaceport America Cup, Launch Canada Challenge, some that are already familiar with our work. And that estimated value is at approximately $150,000 to $250,000. So we obviously looked at the strengths, weaknesses, opportunities, and threats of our project. I'll highlight some of the key indicators, but there are some more listed here on what exactly our project brings to the table. So we're combining AI-powered object detection with predictive motion tracking and real-time camera control. Our rugged and portable design ensures rapid field deployment. So in dynamic launch situations, such as Launch Canada, where we have multiple pads, multiple people launching, within 15 minutes, we're able to pick up and set up our station at a different pad, at a different launch site, and try to get as much footage as possible. And then it's uniquely suited for repeated use in competition and test environments. Obviously, reliability, cost efficiency, and ease of use are paramount in those situations. We're out in the desert, we're out in remote places. And so the whole system is powered by battery, features solar panels, and is completely independent from any sort of main power system. So we obviously looked at our key performance indicators. So how do we assess our own performance for the project? Some of them include marketing, so social media, seeing what our cost of acquisition for customers or potential clients would be. So we're looking to keep that under $200 per customer. Something that's really easily obtainable with a platform such as Launch Canada is that we can speak to multiple teams, multiple industry people for free. So the cost of acquisition is almost zero besides our cost to get here and the cost of making the project run. We then go into technical KPIs. So we're looking at the amount of time that we can be locked onto the rocket during the launch. So we're aiming to get at least 60% of an ascent, which is our main goal this weekend. Detection latency, so the time between the launch and a successful lock-on of the object, we're looking at keeping that below 500 milliseconds. So obviously half a second to be as snappy and responsive as possible. And then video quality, obviously everyone wants nice launch footage. So we're aiming to be at a minimum of 1080p and 60 FPS. To continue on the KPIs, we have customer-related KPIs. So we're going to hand out customer satisfaction surveys, try to get feedback and input on how people like the footage, if there's any inputs on how we can improve it, any sort of specific metrics or specific data they'd like to have on their flight. And then we're looking at obviously the retention. So once we do acquire customers or events or launches that we are filming, how good are we at keeping those customers and acquiring new ones at the same time? And then financial KPIs. So that would be post-demonstration. So following Launch Canada, if we intend to take this to market, the idea would be obviously looking at our return on investment. So our ratio of sponsorship funding to prototype development costs. So our target is to 1.5x within the first year. Small fun fact is that the prize money for the technical demonstration category is more than the cost of the project. So I think it would be the first rocketry project where we would actually make money doing it, which would be fun for the team. And then our customer acquisition costs, again, related to the marketing. It's keeping those costs low. Obviously, just by networking and being present at these events, we can get interested parties. Cost breakdown during a year. So it comes down to three main phases. The research and hardware acquisition, where we received the funding from our school and started the project. We then went into prototype and integration. So this was lower cost, much more technical details, getting into the nitty-gritty of optimizing the system. And then we're in right now the demonstration and deployment phase, where we're finalizing our travel, marketing expenses, and finalizing sponsorship with all our industry partners. So sharks, who wants to film some rockets? So what you can see here, oh, the picture kind of messed up, but what you can see here is images taken from 3 test launch events that we attended. And so we can see that we're able to track rockets pretty small and pretty far into the sky. And so we're aiming to improve on this and show this during Launch Canada and for the live stream. So I'd like to conclude by thanking and acknowledging some of our stakeholders. So obviously Launch Canada for acting as both clients and evaluators, influencing future adoption or endorsement of the technology. Student Rocketry teams for being the project's primary end users, early adopters providing feedback and demand. Sponsors and investors, so both real, such as Canon Canada and Blackmagic Design, which helped us enormously, and prospective sponsors, which rely on the team's execution to validate business case and technical feasibility. Suppliers and technical partners, so involved in hardware procurement, component customization, and camera module integration. And finally, educational institutions and aerospace organizations, such as ETS, which provided most of the funding for the project, and others who may later implement the system into programs or research initiatives. Thank you for listening. I'll open the floor for questions, comments, anything.
I do not have $0 to get 0% of your company, but I do have some questions from you, from the audience.
Hi, so from your photos that you showed in your presentation, it showed rockets at lower altitudes, but for most student teams and Rocketeers, the bigger issue with getting film of the rocket from the ground is rockets at higher altitudes, and that's where most of the anomalies tend to happen. What can you expect to be able to actually get like good quality footage so you can diagnose issues that happen in flight like at higher altitudes, like say 20, 30,000 feet more?
Yeah, that's a great question. So the launches we did were obviously low altitude launches. I think we were limited to 5,000 to 6,000 feet. So that's why we came to Launch Canada to test at those higher altitudes. We did, since those events, add a dynamic zoom feature. So our camera features a pretty powerful lens. And so we're able to keep zooming during the launches. Most of those pictures are static. So it was a static zoom from takeoff to apogee. And I would add that like the majority of rocket destructing events would happen like max Q and below. So for the majority of the teams here, it'd be like up to 10, 15,000 feet where, your rocket spontaneously spins out of control and you don't really know why. The idea would be, well, we could look at that footage and see, okay, well, here we can, in this frame, we can see a fin starting to split off. It happens quick and fast. So the more footage and information we can get, the better we can identify what happened. And then, yeah, that zoom trying to get further and further view. Does that answer your question? Yeah.
What about for like multi-stages when
the
events are actually having like much higher?
Yeah, multi-stages is a tricky one that we haven't had the chance to address or to test. Although the AI model is trained on 2 stages, so it can recognize 2 stages. And the way it is set up currently is that we'll take the highest confidence rocket that we detect. So often for 2 stages, once you lose your booster, that top sustainer section resembles more a rocket to the AI model than the dropping booster, and so it'll lock onto that top section.
How far do you plan to go with the zoom feature?
We can go up to the equivalent of a 900 millimeter zoom for people who are into cameras, but yeah, it's like a telephoto lens, very high zoom level. And so it's what we were provided by Canon, and it's a pretty up there in terms of what's available currently. Before getting into 2-foot lenses.
Do you plan on getting to 2-foot lenses?
Not currently,
what
but
about like
maybe in future iterations.
Maybe like an entire observatory worth?
Yeah.
That'd be cool. Okay, thank you.
Yeah, thank you.
Canon, which also makes cameras for space. Not a lot of people know that.
Hey, Matthew. It's been really cool to see how your project has developed in advance over the few years, from better optics to better cameras, and now an entirely new chassis. So I was wondering, what sort of design limitations or design risks have you identified with this current new design?
Sorry, I didn't hear the end.
What sort of high risks do you identify with this new design?
Yeah, so the risk is obviously the system is vision based. So in general, a lot of tracking systems will be telemetry, GPS position based. Obviously, we're dependent on line of sight. So if weather conditions are bad, if we have fog or just general clouds, if we don't have good line of sight with the pads, it can provide it basically makes it very difficult to track. So that's one of the big limiting factors that we have. Aside from that, I'd say it's just being able to, one that we looked at addressing a lot is being ready in a dynamic environment like Launch Canada. Launches happen within like 5 minutes of notice. So it's being ready to quickly deploy the system and film. So we've done a lot of practice of like, okay, the system's completely shut down. How quick can we get it up and filming to try to get those launches? And so it's going to be testing how efficient we are at that.
Do you have any estimates on how long it would take you to relocate to a different site and then start recording?
Yeah, without travel time, because that can be a big limitation, we're anywhere from like 20 to 25 minutes from like pack down, throw everything in a van, travel time, and then set back up. We really focused on making it as simple as possible because we knew that would be one of the big challenges of Launch Canada is we want to film our team's rockets, we want to film other teams' rockets. Obviously, launches are taking place simultaneously, so getting to and from is a big thing.
Awesome,
Yep.
thanks. Earlier you had mentioned that your current design allows for 900 millimeter zoom lens. Is that optical or is that digital?
So it's 600 millimeters optical and 1.5 digital on top. So we're able to dynamic crop to get to 900, but optically it's limited to 600 millimeters.
Awesome, thank you.
Thank you.
Any other questions?
Yeah. Hi again. Do you plan, like in the future, do you plan to have like a module that someone could put on their rocket to give like, if they're going beyond like visual, like if the camera can no longer see the rocket because of like weather conditions, is there in the future will you have like a module that someone can put on the rocket so that it doesn't lose track and like if it goes past a cloud?
Yeah. So we evaluated a lot of like additional tracking factors we could put, like certain visual cues on the rocket or radio, like a radio module that would give us just a general direction, or even we looked at infrared light, like putting infrared reflectors on the rocket to get a nice pinpoint in the sky. Those aren't currently implemented, but they're all things that would be possible with our current solution. And so that would just be like an added improvement. But the idea being is that the system can be installed without the teams needing to add any additional parts to the rocket, without needing to modify the rocket. Obviously, if teams are willing, well, then we can boost the chance of having something reliable.
Thank you.
Great presentation, great questions, and great answers, everybody. Let's thank Mathieu Gagnon for his presentation. Let's hope we don't lose any rockets this year, and next year we might have to invest in one of your cameras. Okay. This brings us to our second Tech Dev presentation. which requires me to just refresh my notes here. Okay.
Hey there, Rocketeers! Could the previous presenters please check their pockets? If you are missing your USB drives, please come to the tech dev booth and pick them up. Next, we've got Mom presenting their regen cooling system. Come and check it out.
So presenting next, we have Mark. It's our second presentation today. And most importantly, if other teams bring the heat, Mark gets rid of it. And he stays cool, calm, and collected when presenting. So on that note, we will have them come up here and present their liquid regen cooling system as their technology development challenge presentation. Everybody, please welcome Mark. Cool, calm, and collected.
Thank you very much, Cyril, for the introduction. Just waiting for the presentation to come up shortly. There we go. All right, hello, everyone. My name is Giuliano Shabarassi. I am the propulsion lead for Mach. This project is very special to all of us on this team. We spent a lot of time developing this summer and throughout the entire year. And we are very excited to present it to all of you. We hope you enjoy this presentation as much as I will enjoy presenting it all to you. So this is SABRE. This is an acronym which stands for Student Additive Bipropellant Regen Engine. This is our very first regen engine, and it is also, we believe, the largest student-built regen engine here at Launch Canada today and in Canada. There you go. So this is the itinerary for the presentation. First of all, we're going to be covering a little bit about cooling, a bit of a background context. Next, we'll be talking about the development of the engine. So basically, when that note, we're going to be talking about why did we choose a regen engine? Why is this engine special to us? And why did we go through all the trouble of making an engine like this? Lessons of regen cooling will be covered later. This is some of the things that we didn't learn or didn't know about when we went into the project that are really important. So if members of the audience and here at Launch Canada may develop their own regen engines, that may be an important panel. Future plans and testing. So this engine SABRE is going to be a test platform that the team is going to be building upon for years to come. And we'll be talking more about what we actually plan to do with it later. So part one, how to cool a rocket engine. So there's many different types of engines out there with different fuels, different materials, and every single rocket engine is unique. Some engines have a heat sink, some engines do ablative engines, some engines do regen engines. The challenge with cooling down a rocket engine is that the combustion gases are very hot, up to 3,000 degrees Celsius, and the material properties often cannot withstand temperatures as high as this. So engineers have to get creative. In that picture there, you can see a thruster for a hyperbolic thruster for the Peregrine lunar lander. You can just see how red it is. I just thought that was really interesting to show for a different approach to cooling. So as many of the people here at Launch Canada may be familiar with, one method is ablative cooling. The team actually had an ablative cooled engine here at Launch Canada previously that was similar to this, where you have an ablative liner down your combustion chamber, and around your nozzle, with a graphite insert around your throat to avoid any ablation around the throat. This works well for a wide range of propellant types. So we did a liquid engine last year. This was good for a liquid engine. This can be used for hybrids and even solids as well. And it's seen here often at Launch Canada because it's very cost effective. However, yes, so this is actually the ablative engine that we had last year. That picture there is from September 2024. So right after Launch Canada, we did another hot fire. And that is the picture of the design of the engine. Over there, it's a cross section. Okay, so now moving on to regen. Regen is much more significant in terms of its cooling because it has the capability of doing long duration burns. A lot of the reason why regen is used in industry is for if you have a second stage, it has to burn for 5 minutes at a time. But ablative engines are just not capable of doing that. The performance of a regen engine is very advantageous. And it's why we really, as Mach is focused on developing industry technology and learning that for ourselves. This is why regen was very attractive to us. These are some examples of some regen engines that are actually used, and there's two different approaches here. So you can see there's a copper liner on the inside for the Merlin 1 SpaceX engine. We actually don't do that concept, more on that later. But, and then on the left, you see a very early Mercury Redstone engine, which operates on a different principle without having the line channels the same way. However, manufacturing techniques have evolved. And now in the 21st century, we have additive manufacturing and metal 3D printing. So this technology now makes it possible for student teams to build large regeneratively cooled rocket engines, such as the one that we are presenting here. So on the left, you can see a new Rocket Lab Rutherford engine. That picture is from this year. And in the middle picture, you'll see a NASA test of a regen engine at Marshall Center. And on the right, that's our engine. So now with that in mind, let's move on to the development of this engine. So how did this come to be? So let's go a little bit back to the past about last year's Launch Canada and the lessons that we learned in order to get here. So that's a picture of our hot fire at LC 2024 last year. And you can see our inspection. You can see how we didn't have a graphite insert around the throat. And so the part actually began to ablate and wear away at the throat. In the image on the right, you can actually see the grains in the material of the Garolite ablative. And when the fuel or the hot gases is coming in on an angle against that grain, it has a lot of friction, and it wore away at our Garolite ablative liner. So later this year, the team moved on, and we wanted to add in that graphite insert. This is an engine that we actually plan to bring here. The Chimera engine is an ablative engine with a graphite throat. It uses ethanol and nitrous oxide as fuels with 6.3 kilonewtons of thrust, and it has plans to have a 9.2-second burn time. The most important aspect of this engine is that it has a pourable ablative liner. So what this means is that finding Garolite tube stock for a part this big is very difficult to find. So we had to make our own ablative liner. 3 months ago, the team ran into a lot of development challenges with this pourable ablative liner. And the regen project started in February and continued working and building. And then eventually it caught up to the development of the ablative engine. And the team had to make a choice. Do we continue development of the ablative engine, or do something innovative that hasn't been done before at LC and make a very large regeneratively cooled rocket engine? And we decided the latter, as you can see. So the Sabre evolution right here, you can see the CAD design. Some of the pictures are a little bit skewed, so I apologize. Must have been the way it was transferred over from one lab to another. But in May, you can see the development of the CAD. You can see that we're still using the ablative injector and the ablative lid. As this project was started roughly on the side, the development of this engine was focused on using the same parts of the ablative engine. We didn't have the time to design a new injector and to design a new lid. And that dictated a lot of the designs, a lot of the interfaces at the top of the part. We did experiment with different cooling channel geometry, which you can actually see in the first two images. It may be a little bit hard to see, but in the second image, where the channel goes at the top, we have vertical cooling channels that are short and narrow. I'll talk more about our cooling channel geometry later, but just a little showcase of the design evolution. So this is our MATLAB that we use to characterize the cooling channels. The development of this engine was quite interesting. 2 months ago, we had an unfortunate incident where we lost the cooling calculations. However, we were able to find a program, open source program, that was able to help us model the cooling channels. The problem that we faced with our old program is iterating the temperature of the fuel further upstream is a challenge. What this program does is it takes the heat flux and it integrates it to find Q, or energy. And using MC delta T and knowing the specific heat capacity of ethanol or fuel, we were able to solve for delta T, or the change in temperature. This is where we struggled with before, and it was a big area of help. In the image on the right, you can see the cooling channel geometry that we originally had, and this is also mentioned in the research paper underlined. So in the top image as well, you can see our current geometry. Essentially, the program works by taking modeling a channel with its width, its height, and the thickness of the channel wall. And this is our channel performance. So this is what we believe we're going to see in terms of our chamber. The blue graph is the temperature, the red graph is the heat flux, and the gray is the curve of our rocket engine contour. So the blue graph here has a temperature spike at the throat. And due to isentropic relations, this is where we believe the highest temperature in the engine will occur. Optimizing this location of the engine was a challenge. We experimented with different geometry designs, and we settled on a design that's very short and narrow. So the conductivity of Inconel 718, which this part is made out of, is very low. So the first design that I showed you previously would not work because the heat is not able to propagate through the material to take advantage of the vertical cooling channels. So in reality, what we had, if we did something like that with Inconel, is the heat is only going to be on that surface that's closest to the engine. So we have to change that up, and this program was a big help in that analysis. So the next thing that we did is ANSYS at the throat. Finite element analysis. One of the failure modes that can occur with regenerative cooling is the pressure inside of cooling channel at the throat can be quite high. And under stress, this can actually cause the part to buckle or cause cracks under pressure. So we used a steady state structural analysis and a thermal analysis inside of ANSYS to model the cooling of the engine, make sure that we wouldn't have those failure modes occur. This was done by looking at the ultimate tensile stress of the material and comparing it to the stresses that we would see in the finite element analysis. So in this graph here, you can see the two different graphs in our FEA. So you can see they're both static structural. One models the deformation, and the other models the steady state pressure. So now, with all that said, with our ANSYS, with our MATLAB program, modeling our cooling, this is our final product. This is what we have on stage here today. So in the image on the left, we have our channel geometry. The iterative channel geometry that we have is dynamic and changes at every location inside of the engine. So at the nozzle, we have a 60 thou wall thickness with a channel thickness of also 60 thousandths of an inch. When that moves up to the throat, we want to increase the velocity of the fluid to increase the heat transfer. So that channel thickness goes from 60 thousandths of an inch to 30 and gets smaller. And the throat, to allow more heat transfer, also gets smaller to 50. So that gets to 50 thousandths of an inch. Further upstream into the chamber, we have 80 thousandths of an inch for the wall and channel thickness. So what this means for our coolant is that it's not going to be working as hard in the nozzle and the chamber to keep the engine cool. And this is important because ethanol has a lower boiling point of around 80 Celsius. And under 39 bar, which the engine will be experiencing at the inlet, the boiling point is 480 Kelvin. To make sure that the fluid does not boil heading into the injector, we had to get creative with this geometry to make sure it only obtains the energy that it is needed to ensure that the engine stays cool. So with all that said, let's move on to some of the lessons that we learned throughout this process and throughout this project. So these are some questions that we asked the supplier. So if any members of the audience plan on doing their own regenerative cooling questions, this is what I highly recommend you clarify with any supplier. So metal properties should come from the supplier in their powder. For example, this engine was made out of Inconel 718. And one of the mistakes that we made was finding properties from the internet. Instead, we later just determined that we needed to go to the supplier and ask them about the powder of Inconel that they have. Each powder is different and patented, and some can have slightly different powder size distributions, ultimate tensile strengths with different heat treatments as well. In the image you can see, it's also the orientation of the part print. So actually, this part was printed upside down, widest at the base and built up. This dictates how your support structure is going to look like, which you need to take into consideration when you're designing your CAD design, for example. And the last point there, support structure in mind. This is very important. So this is a gallery of some of the feedback that Volsopine gave us. And this is because this is our first time doing a regen engine. So we didn't know some of the design considerations that were needed for additive manufacturing. Every part in green is a part that was changed in the post-process design with their team, such as all of the MPTs and lids and interfaces. So now let's move on and talk about future plans and testing roadmap of Sabre and of this project. So first things first, we need to go and do some post-process on this part. We achieved this part a few days ago, and we have yet to do some of the post-process parts that I mentioned in green on the previous slide. That includes threading the pressure transducer holes there, the MPT holes for the thermocouples as well. We have a 1/2 MPT hole for our fuel inlet, which we have to be very careful of. We also need to go and use a fly cutter to make sure that the top of our engine's flat, because that's an interface for our lid. To summarize all of this, every single interface that this engine will have with another part, we will have to either thread or flatten to make sure that we have a good interface. And so now moving on, as I mentioned earlier, this engine will be an iterative process that the team will be working on in the future. This is a multi-year long project. On the right-hand side, you can see the team's torch igniter mount and successfully mounted on the side of the engine. This is what we plan to bring, not at the next hot fire, but for next year's launch candidate. On the left, you can see a mock torch thrust vectoring system. Now, the engine on the left is actually a previous version of the ablative. So when we actually ditched the ablative and we changed to CAD, there were some things that were changed with some of the geometry that we didn't have time to go in and adjust. So that's just the ablative engine, but it gives you all in the audience a visual into what our thrust vectoring will look like. In the end, Sabre is brought to you by Mach and Volsopine. Working with Volsopine was a great experience. They taught us a lot about additive manufacturing, the process of additive manufacturing. And I hope all of you in the audience also learned about, if you plan to deal with additive in the future, lessons that are very important. And that's everything. This is our project. Thank you very much for listening, everyone. Thank you.
Great presentation. Engines like these are typically what you see on LinkedIn, achieved by companies of 40 people. And this is students from Mach in Canada that accomplished this. So congratulations. It's beautiful.
Thank you very much for having us.
Do we have any questions from the audience? We do have 5 minutes for questions. Beautiful.
Yes. Any questions?
Hello. Hi. Sorry, I want to ask, why did we use a specific Inconel alloy that you used, the Inconel 718?
That's a great question. Thank you for asking. Inconel is a super alloy, and it retains high strength at high temperatures. So at around 700 degrees Celsius is where it retains its strength, in contrast to other alloys like aluminum, which may only be a few hundred. The advantage of using Inconel, although its conductivity is lower, is that it can take the brunt of all that heat. Other student teams and other parts use Inconel for high temperature components for that reason. It stays very strong. So this was a big advantage on how we were able to make the wall thickness so thin. Although I mentioned a little bit of thou, but the wall at the end, I said it was 50 thou. That is 1.2 millimeters for context, for some people who may not be familiar with thou. And our wall channel thickness is 0.7 millimeters. Inconel 718, because it stays strong, is able to make sure it doesn't deform and has a high tensile stress. So it makes sure that this part's not going to achieve some of the failure modes that may occur with, let's just say, stainless steel, for example. Thank you.
Interesting. Thank you.
So do you have an estimate of what the kind of outlet temperature of the ethanol is after it passes through the regens channels before the injector?
Yeah, so we believe that it's going to be approaching the boiling point at steady state. So our modeling was done in steady state to optimize the curve to get the lowest possible peak. If this engine was running for an indefinite amount of time, we believe that it would approach the boiling point. However, we plan on doing a 9.2 second hot fire burn with this engine, and so it's not going to achieve steady state in that amount of time. We know that it's going to be below that figure. Another thing that we can also do as well with our ethanol fuel is dilute it. The advantage of ethanol is that you don't have to use 100% ethanol. The graphs that we showed on screen were done with 100% ethanol for redundancy, but you can reduce that to 90% and have 10% water, which increases the heat capacity of your fuel. Water is a very good coolant, for example.
And just as follow, I think I missed that in the presentation. So your kind of channel profile, you say changes throughout you figure that profile numerically, right? Like through modeling, that's how you determine.
That's correct, yeah.
Okay.
I do have a follow-up question. The advantage of these engines is that you can simplify a lot of technology into one core component, right? You have your cooling channels, you have your plumbing integrated, your fittings integrated. But the difficulty that I've seen historically with testing these engines is that they're very expensive. And so the iterative process is harder to have subsequent steps. What is the plan that Mach has to test this engine, make a new iteration? Do you have that partnership, and is that lined up and secured?
Yeah, absolutely. Thank you. Actually, at this year's Launch Canada, the engine that we plan to hot fire Mojave Sphinx will be testing some components of Sabre over here. So Mojave Sphinx is actually not an ablative engine and has a heat sink on the inside. And we plan on inspecting like for example, it's aluminum, and we plan on doing a short duration burn with that fire. This also does not have an ablative in it as well. So we can look at the way the Mojave engine can handle its burn to get an idea of how Sabre could handle its burn as well. We can also use, with the same ignition system on that engine, on this engine as well. We plan on iterating with different types of ignition systems. We're going to start with using a motor ignition, so like an SRV motor ignition inside the chamber. But what we did last year was just made an epoxy igniter, and we just put it inside the engine. We plan on doing that, testing that again if you have time, and that's what we're going to be testing for our first fire with Sabre. Thank you very much.
Wonderful, thank you. A nice round of applause for Mach.
Thank you, everyone.
Thank you. This brings us to 2 p.m. and brings us to a next speaker that I've talked a little bit about during the conference so far, and I just want to make sure. Okay, I see him in the back. I'm going to confirm that slides. Are slides ready, Ariana? Okay. We will have a PA announcement. Okay. Ariana, if you want to do a PA announcement, it's now.
Hey there, Rocketeers. Did you know that in 1991 there was a
Okay, we're gonna get started. So I talked a little bit about our next speaker throughout this conference, and for a very good reason. If there is a single reason I still have LinkedIn today, and maybe the Consat team, but that's another platform that I like following. So let me introduce him. Adam Lakeman is a ballistician and the unofficial vice president of morale at Aerojet Rocketdyne in Huntsville, Alabama. With more than 26 years in rocket propulsion. 26, that is my age. That's crazy. He began his career on liquid engines at Pratt & Whitney, nice, before moving to ATK to work on solid propulsion and joining Aerojet in 2010. Outside of his engineering work, Adam runs Rocket Facts, LinkedIn's top source for entertaining and innovative, informative rocketry trivia and hand-drawn diagrams. He is a great speaker and a great drawer. Today, he will be presenting Rocket Facts live to us, to the Launch Canada audience, where he will blend technical insight with humor and a deep passion for rockets. Everybody, please welcome Adam Lakeman.
All right. I never speak into a microphone. I'm used to walking around, so I don't know what to do at a podium here, but we'll try to go. Afternoon, everybody. Hope you guys are having a good time. I am. It's a pretty cool show. It's my first time at a rocket competition and my first time in Canada, so killing two birds there. The clapping's going to stop soon. Don't worry. So yeah, when I got asked to present at this by Adam, and Ari called me up or emailed me, I guess I decided it was going to be Rocket Facts Live, and I didn't really know what that was. Rocket Facts is something I do on LinkedIn for fun, and it's kind of taken off. I didn't know what live was going to look like, so I'm just going to wing it while I'm up here. Most of what it is, for anyone who's not familiar, is just, one day I was sitting at the beach on vacation board, and I decided to attack my liquids brethren. I work on the solid side of the rocket business, so it's a constant battle between the liquids and the solids guys over who's better. So I put an end to it with one rocket fact about how solids are the best. And no offense to the liquids guys, only half offense to the hybrids guys, but go solids. And then it just kind of ballooned from there. Some of the posts have been pretty irreverent. There's one up on the screen right there. And that's one, actually, my mom came up with that idea. So if you want to try to understand why I'm the way I am, it can kind of blame her for some of my personality. But she liked the idea of doing one on strap-on boosters. And I said, what's the best way I could describe this with crayons? And that's what we came up with. But anyway, who am I? And how am I still employed, more importantly? Funny story behind that I won't share here, but I was almost able to spend all my time up here for this competition because I might not have had a job to go back to because of these, but all in good fun. But anyway, I'm a ballistician right now at Aerojet Rocketdyne. And for folks who don't know what a ballistician is, that's basically I do solid rocket motor grain design and performance analysis. Supporting a number of programs, which I can't talk about here, but mostly on the defense side of the business down there. And I'll stay on the good side of the ITAR monitors. This unofficial VP of morale, that's not a real executive title. I'm not a real executive, but basically I sit around work and make my coworkers smile, crack jokes, give them things to make things, even when times are tough, still kind of upbeat at work. Purveyor of Rocket Facts, we talked about that a little bit, and a frequent tester of HR's patience, which I kind of alluded to with the almost not having a job part. But I still do, so I guess I toe the line without actually going across it. Things I like. This is, again, first time in Canada. I wanted to point out that I like Dunkin' Donuts. French fries without gravy. It's a good one. American bacon. I don't even know if you guys call Canadian bacon up here. Deer that are smaller than my car. I haven't seen a moose yet, and I hope I don't. But the thought that, there's an animal that's that much bigger than my little Honda Fit is terrifying. Just roaming the woods up here. Going out and about, love that. And my favorite thing, I love that Lord Stanley's Cup, is where it belongs in sunny South Florida for the second year in a go. Go Cats. All right, things I don't like: tree sap, bagged milk, not being able to wear shorts and flip-flops year-round, although the weather has been nice up here so far this week. Although today was the first day that I've ever worn a sweatshirt in August in my entire life. You don't have to do that a lot down in Florida where I grew up. Chad Kroger, he should be higher on the list. And mooses, which I discussed. I hate mooses. Tapooses. So rocket facts, like I said, it was more just sitting at a beach and just, taking a stand against the liquids guys, thinking they were the best with all their shiny plumbing, all that pipe work, all their ability to throttle. And I put them in their place. And then it kind of snowballed from there. I've worked on my crayon art. I happened to have a pack of crayons and just started drawing, and I rolled with it. It turns out one of the nice things about crayons is you can put some information down on paper, but never have to worry about getting too detailed. So you can get a lot of things wrong, and it just kind of gets blended away. My inspiration down there at the bottom, my mom hiding behind her middle finger, and another inappropriate rocket fact that I did on why rockets are shaped the way they are. Yeah. She was a school teacher for 20-something years, so I guess I caught the teaching bug from her. Because aside from doing that, I also, teach at work. There's classes we do on energetics that I travel around to Aerojets different sites and teach our new employees about solid propellant, what it is, how we work with it, how to behave around it, why we do everything the way we do. And then it gets to the end of that part, right? Now the live. I didn't really know what to do. I thought maybe I'd come up here and bring some crayons in and just start drawing some stuff on paper. And then I realized I'm not that fast, and they only gave me a half hour. So if you guys want to throw ideas for something you want to see, and I've already got one for you, Adam, on something I can do about, rockets in Canada in general. But if you guys have any ideas, let me know. And before this week is done, I'll scribble something out for you. But in the meantime, I guess if there's any questions you guys have on rockets or anything, I can try to spit some knowledge at you, or lie convincingly. If I don't know the answer, I'm pretty good at sounding like I still do. And most of the time, people don't realize I'm making things up. So you guys can try me out.
So, okay, I will bring the microphone around. Perfect.
I didn't give the heads up to the mic guy.
No
I'll
worries.
pass Cyril.
So you've alluded fairly heavily to your preference for solids. So on that note, when you're doing fancy port geometries and everything's getting real thin, I've heard about frames being set up to help prevent the propellant from breaking off in large chunks as it's sort of ablating away or burning away. How do you control that or maintain its regression?
Well, ideally, you want to design your motor to not have that happen, right? You design it so when it burns back, you don't have any thin, unsupported pieces of propellant flapping around like roast beef out the window, right? Because if it breaks off, that's a bad day. Best situation is it breaks off and burns up in the chamber normally, so you can get the energy out of it. Second best situation is it breaks off and goes out the nozzle unburned, so you don't get anything useful out of it as far as thrust. And the worst case is it breaks off and plugs the throat and blows your motor up. So ideally, we want to design it so that doesn't happen at all. So when we're burning back, we'll look at how thin propellant does get in places and make sure that there's nothing that could possibly break off. We can avoid it. And if there is, we just change grain design. Sounded like that was the right answer, right?
It is.
See, I told you I can be very convincing making stuff up. What else you guys got?
Hey, how's it going?
Good.
Good. Since you're a solid expert, I have a question. So there's a lot of papers on TNT equivalent of solids from a long time ago. With your experience over the years, what ratio, sorry, this is a very technical question, what ratio do you use? So for example, a LOX and kerosene, it's 20% of the total mass. What is the ratio used for, can you give a couple of examples of solids mixtures, and what is the TNT equivalent percentage you use? Thank you.
Oh, TNT equivalent, I don't know. the oxidizer to fuel ratio?
Basically, it's the amount of the equivalent TNT that the explosion will.
It depends on how big the rocket is.
So no, per kilogram. So
per kilogram.
For example, HTTP plus the aluminized, it's usually people say 1.0, but I wanted to know if if it's not something you're using these days, that's okay. But that's not something you know. Okay.
No, I know that when you add it up, it's very capable of blowing the roof off the test phase. I know that from experience. Yeah, and I don't really gauge how big a blast it is from whether the roof comes off, but how high the panels go and how far they land.
Okay, that's.
But yeah, per pound, it probably depends on formulation, right? There's a lot of different formulations for solid propellant, and each one is unique. Each one has unique output. So I mean, some are more energetic than others. Some are far less energetic, and we choose to use those for other performance reasons, not necessarily thrust performance, but other tactical advantages they provide that are more important than performance. We have some propellants that we categorize as a 1-3, or I guess a mass deflagration hazard versus a mass detonation hazard. The detonable propellants would be higher. But as far as, values compared to TNT for this generic formulation, I don't know off the top of my head. Probably varies again, just depending on which propellant you use.
It's hard to find. I'm telling people to use 1.0, but I have a feeling it's still slightly lower than that because it's not TNT.
I think
okay, thank you.
Overall, it probably is. Most propellants are not designed to be as energetic as a true high explosive. Some of them end up being that way, again for reasons of certain performance aspects of propellants like that. But yeah, in general, yeah.
I have a selfish question myself. So you said that you have a preference for solids.
Yeah.
Can you tell us what is your most disliked solid motor and your most favorite liquid motor?
Oh, my favorite liquid engine, pardon me.
Sorry.
Well, it was going to be RL60, but I'd have to go with the RE180 as far as a liquid, just because of the elegance of it, and I worked on it a little bit when I was still at Pratt. Favorite solid? I don't even know if I can tell you here.
Most disliked solid.
Oh, the most disliked solid. All right, that's an easy one. All right, everything that Northrop makes, the big solid boosters made by Northrop, right? Every time they fire one of those, especially the 5-segment ones they got now, and they talk about how it's the biggest motor ever fired, blah blah blah. It's always wrong. The biggest solid rocket motor, biggest single motor ever fired to date was made by Aerojet in the 60s, the 260-inch motor that they dug a hole for in the swamps outside of Miami and put the motor in the pit, tested it in there. It was going to be for Saturn, for moon launching. The government went another way, but Aerojet was working on a monolithic metal case made by a submarine manufacturer, somebody who could make a big metal tube that would seal up, not the segmented approach that at the time the Thiokol ultimately took later. But yeah, they put, I forget how many million pounds of propellant inside that motor. They only ever made a half-length one, so it's full diameter, only half as long, so only half as much propellant. But that thing burped out like over 5 million pounds of thrust, which is still about 50% more than those big 5-segment boosters that Northrop puts out. So every time they say biggest motor ever fired or biggest solid, they're not even close. And that motor's still sitting in a pit in Miami, out in the Everglades, rotting away down there. The last motor they built and fired, the third one, still sitting down there. If anybody's adventurous enough and not worried about tetanus or pythons or alligators, it's out there.
Thank you. It's a great answer.
I don't even think I've sworn once yet, have I? I'm doing pretty good. HR would be proud.
I got a question about thrust curves. So when we design at least our student rockets and we look at the thrust curve of the motors that we're going to be purchasing from suppliers, we tend to see like a spike at the beginning and the thrust seems to trail off. I'm just wondering if you're burning from the center out and that surface area gets bigger, I would think that your thrust would be increasing because you have more surface area burning. I'm just wondering why that isn't the case.
So if you're purely burning from the inside out, you'd have a progressive trace like that, right? It would start off from where you're sitting, it would start off low and it would go up as you burn back and that surface area increase. But if you're burning from the ends in as well, right, they're going to cut down somewhat. So depending on how the motor's designed, if you got more of an effect of the ends burning in versus the inside burning out, it might be enough to overwhelm that increase in surface area by decreasing it as the ends come in. That's just purely the motor itself, right? Because in performance, you also have to account for nozzle erosion. As that throat erodes and gets bigger, it's going to drop your pressure as well. But that's more of a full up built rocket motor level than just the cartridge you're buying. But if you get a regressive trace, it's because your surface area is dropping off with time, and it's likely because the ends are burning in faster than the surface area increases. You burn from the inside out. Sounded like a good answer, right?
No, it makes sense.
And very convincing when I'm making stuff up.
And not swearing.
I've got two questions. One to build on that. So I quite like two stages. And for the second stage, I'm quite a fan of head-end ignition. Now, when I did it, I just routed igniters around RTV silicone and a G10 plate. And I have all my fingers. But what would be your recommendation for sealing the head for head-end ignition?
RTV, O-rings, and a good, snap ring or some other stout sealing thing to keep the igniter from getting blasted out the front end. Sealing is one thing, but having mechanical retention is important too. RTV is not very stout. You can peel that right off your bathtub. Makes a good seal, but as long as it holds in place. And O-rings, same story, but you need some kind of mechanical retention there. And head-end ignition is the way to go on every stage if you can do it. You only want to light from the back end if you have to, if there's no other way. Because otherwise, when you're lighting from the front and that flame wants to head toward the back end, it's going to light everything else along the way. You're going to get your motor up and running quicker. If you light from the back end, that flame trying to crawl up to the front of the motor while everything else is trying to go out the nozzle, you're basically swimming upstream. So if you care about getting going quick, you want to start from the front.
Vindication. So the second question is that the rest of us are feeling left out. What do you hate most about hybrids and the emerging detonative engines?
What do I most about hybrids?
Hate. Roast
Hate.
us.
What do you say? Worst of both worlds instead of the best of both worlds? Yeah, so you have the, ideally, right, on paper, it's supposed to be the best of both worlds, right? You can throttle them, which you can't do with most solids, because you can control the flow of the oxidizer in and out of the chamber. From a safety standpoint, this is why it's great for college kids and doing school projects. You got your fuel and your oxidizer separate, so it's inherently safer than, say, solid propellant when your fuel and oxidizer are already mixed and all you need is a spark to set that off. But it doesn't end up working that way. You don't get quite the same energy density as you do with the solid, right? You've got to have a separate tank. You've got all this extra plumbing weight you got to account for, and the valves for, dealing with the oxidizer, the liquid oxidizer. You don't get the complete mixing in the chamber. It's not consistent from end to end. You start off oxidizer rich at the injector end where you're putting it in, and by the time you get to the back of your solid grain, you've consumed a lot of your oxidizer. So now you're more, I guess, oxidizer poor at the back end than you are at the front end of the motor. You get some waviness in the burn back. You can mitigate some of that with the design of your grain and try to put swirls in the design to kind of spin things around. But, with the solid, your propellant is perfectly mixed the whole time from start to finish. You've got the ideal oxidizer fuel ratio because that's all set when you're pouring the ingredients in the KitchenAid and blending them up. But And on the liquid side, you obviously get higher ISP than you get out of a hybrid, right? Some of the liquid propellants, they just put out, more energy per pound than that you're burning. So they exceed solids quite a bit, but a lot of the liquids are also pretty low density compared to solid propellants. So hybrids kind of take the worst of both systems and combine them. But again, safe, and they're great little learning motors. I guess, again, I don't want to crap on the folks here who do hybrids for a living. Now I get why that question was asked while you were sitting next door. They're good, and they do have some advantages on paper that hopefully can be hashed out in the real world. But it's still pretty new as far as getting it commercialized, right? But again, great for student teams, just because colleges will let you do stuff. A lot of colleges won't let you make propellant on campus because you're basically making explosives, and from a liability standpoint, they're not keen on that. So they prefer liquids, which are expensive, hybrids, which are safe and much cheaper, so much more attainable for students to work on. So they're good learning rockets. But best of luck commercializing.
So I have a question, and I don't know if it's valid. I'm just going to ask because I'm still new to solids and big solids like I'm firing now. Are there any benefits to having a solid that has variable energy density through the core, where let's say you want a slow acceleration and then have it increase as you're getting further in the burn? Do people do that, or is it always uniform and they burn and you just manage the thrust curve?
That second one.
I'm sorry?
There are motors where you can put different propellant grains in them, right? There's boost sustain motors where you can have a booster grain and a sustain grain, two different propellants, one that burns fast, one that burns slower. Or you can control it all with surface area, right? You gotta design your thrust in up front on most solids. Again, can't really throttle. It's the same formulation.
It's the same formulation with the same energy density, but you're changing the physical
Yeah,
characteristics.
there's no practical way to change that.
You're
on the
not
fly.
doing like a layer cake where you pour one kind and then pour a different energy dense propellant on top of it and build it up like that. Or do you do
You
different?
can do that.
Yeah.
Not like multiple layers like you talk about, at least two. Where you can have propellants either end to end, or there's even some that have been done like popsicles, right? Where you've got some center core propellant that you can then plunge into another one once it's cured, right?
Oh, okay.
So yeah, there can be some layering like that, but not throughout where you can ramp up and down.
Oh, okay.
Right. That gets very complicated from a manufacturing standpoint.
Right.
And there's no feasible way to manufacture that. So if you want to control that much, and there's other ways to do it, which I can't discuss here.
Okay.
But yeah, typically you don't have that much throttling you want to do with the solid anyway. You usually want to get it going and then sustain for most of the tactical world, right?
Right.
That's sufficient. Get it moving fast, and then once it's up to speed, just have enough thrust to overcome drag and keep you
Right.
cruising.
Okay, thanks.
Yeah. Isn't she at her limit now?
Last one for the day.
I swear I can drive. So you were talking about the submarine manufacturing method down in Florida. We live in the timeline where it was the Saturn V that happened. Would you have preferred Saturn V or the Sea Dragon?
Man, Sea Dragon would have been cool.
Yeah.
That would have been cool. If the 260 became a thing, they were going to barge that out of the Everglades. Aerojet had actually dug a canal out, and they were going to float it up to the Cape. And had something gone wrong, it could have ended up like a Sea Dragon. But yeah, the Sea Dragon is really cool on paper. It would have been very hard to pull off. especially a metal case in a saltwater environment, right? You had a lot of considerations to deal with there, making sure it didn't rust apart. And never mind, like when the environmentalists caught wind of what that thing was doing to the local sea life when they lit it off underwater. But that would have been a cool thing to see. But the Saturn V is pretty cool in its own right, even with all its liquid engines. But it's all pretty much Aerojet Rocketdyne engines on there, top to bottom with few exceptions. So we accept the Saturn V as it was ultimately built. All right, college kids, what else you got?
Okay, here's one for me. We always, tell students that when you're designing things, it's usually consideration of how stuff fails that drives design a lot more than how it's supposed to work.
Sure.
And rockets tend to be really good at failing in bizarre ways.
And spectacular ways.
What is your favorite rocket failure?
Ooh. Everything SpaceX has blown up, And let this be a lesson, kids and adults. Always take time to do a proper failure investigation. Don't assume that because you think you see right away on camera data that I know what the problem was. Take the time to look at everything else too, even if it doesn't seem obvious, because you may find out that just because there's something simple that, oh yeah, that's clearly what happened here, doesn't mean it's the only thing that went wrong. And I guess SpaceX is getting ready for their 10th attempt to do their Starship and see if maybe they can pull this one off on Saturday or Sunday. Sunday. What's today? Yeah, the 24th. So Sunday, I guess their next launch window for attempt number 10. So sadly, I'll be on the road, but I look forward to hearing about how it failed. But yeah, those are always my favorite, and it's not because I don't respect the people that work at SpaceX. I respect them. I disrespect them for some reasons, but those are why they would put themselves through such personal pain and suffering. For the gain of one billionaire who could easily afford to hire enough people to let them work 50-hour weeks instead of 100-hour weeks. But yeah, mostly because I just don't like it too long. But personal failure. I won't say the program, but it was August. It was Arkansas, southern Arkansas, which is a lot different weather-wise than northern Ontario in August. So it's, about, I don't know, 100 degrees hotter in whichever temperature system you prefer. And, plenty humid. And we tossed the motor off into the woods, static test, which went non-static pretty quickly. And we started a 90-acre forest fire, which took the state fire department to come help us put out, since most of it was not on our property. And yeah, got to spend 2 days looking for motor out in that. Fire was out before they let us go out there, but the sun was plenty hot anyway, so we almost lost a chief engineer and a customer because they didn't understand how to survive in humidity. Meanwhile, South Florida guy is just sitting there down in Gatorade and happy as a clam, and just watching his soft Utah and California coworkers almost die. But yeah, that'd be my favorite. Sole of my safety shoe melted off. I keep that as a souvenir. Only my right shoe lost the sole, and the left one held together. But I keep it on my desk as a coaster now because it turns out it's good and flat on the inside, so it'll hold the Coke just fine. Oh God, what else? I got a sweet little alligator grabber. They gave us little grabbers that went to the store. The company did, and picked up all of the little yard flags and grabber claws they could find in this tiny little town in southern Arkansas. They cleaned all the stores out, and there was one that looked like an alligator, and I threw that bitch in my trunk and took that home with me. I was like, I'm keeping this one. That's company property that I'm stealing. But yeah, that was my favorite. And that was one of those tests that we figured out what went wrong like immediately. But we still did a full investigation on it. And instead of being ready to turn around and do it again in 3 weeks, like some companies do, We did a full investigation, solved our problems, fixed them because turned out it wasn't even a motor issue, it was a test setup issue. But we didn't test again for almost a year, which seems like forever, but you know what? We didn't fuck up again, and we nailed it. Haven't had a problem since. And again, the motor was flawless. It actually, when I had to do the calculations to figure out how much thrust it generated, flying in a way it was not designed to do, that was a fun little test of my ballistic skills, and one I never thought I'd have to do for work. But I still have the napkin, literal napkin I did that math on, saved away. So that's my favorite. That's my favorite failure. It didn't seem fun at the time, but they never do. But looking back, my second favorite one was when I almost blew the ass end off of an interceptor. My first grain design as a ballistician, not properly analyzed by structures or my mentor, and I spent the rest of my career at my previous company as an enemy of our VP of engineering because of that. So that was a good one to look back on too. I enjoyed that it upset her so.
All right, one more question. What is your favorite oxidizer and why?
My favorite oxidizer, ammonium perchlorate. Yeah. It's got twice as many oxygens as oxygen does, for one. Super oxidizing. It is technically less unhealthy for you than ethanol is. So yeah, that's only a 1 on the health side on the hazard diamond. So you can eat it. It's not tasty. It's tastier than other oxidizers, but it's not something you'd want to put on food. I made my intern eat some when we were in Arkansas a couple weeks ago. I took him out there to go experience solid propellant, which we don't do in Huntsville. It's all inert work in Huntsville. We do our live stuff in Virginia and Arkansas. So I took him out to Arkansas toward the end of his internship and told him to try some of the AP. We went in one of the grinder buildings. So he tasted it, and he said it was salty, which is true. But yeah, that's my favorite oxidizer. Till we get a good one with even more O's on it.
He was quite salty that day, probably, following that tasting test. Everybody, let's round of applause for our speaker. Unfortunately, it's all the time we have, but you will stay at the conference.
If you guys still had questions, I can come and hit you up when I fall off the stage here.
If we can keep bothering you, we'll be happy to do it. So thank you for
That's what I'm
staying
here
here
for.
today. Wonderful. One other hand of applause for our speaker, Adam Lackman. Everybody, thank you.
I gotta say, you have a way to summarize such a lengthy career in such a charismatic and simple way for all of us to really you really have a good overview on your life. You've reflected a lot through this. I love it.
Hey there, Rocketeers!
This is the last time I promise that I'm saying this, not only because it is the end of the conference, but because this is our keynote speaker. But this time you'll clearly understand why without the next speaker, this competition would be absolutely impossible. You know, Launch Canada is great. I think I'm biased, but I also agree with the statement. Rockets, scientists, smash burgers outside, and launches starting tomorrow. It's all great stuff, but running this event requires hardware, software, bulldozers, drones, and satellites for GPS, for internet. And the company that is about to present is at the very foundation of all this, not only because they are Launch Canada's biggest sponsor, but also because this company is the prime contractor for most large-scale aerospace engineering projects in Canada. So I'm ready to bet my last $5 that you know who I am talking about. $5 because actually our $5 Canadian bill gives it away because they are on our $5 Canadian bill. And that would be because we're talking about the company that is behind the Canada arm. Sorry, the Canadarm, not the Canada arm. I've learned that one recently. I don't want to steal the scoop, but not only is MDA Space behind the Canadarm, but also satellites, space logistics, and operations. MDA Space has also committed to being Launch Canada's largest sponsor for the next 3 years, so thank you. That really makes my life easier and makes my day. And so representing MDA Space, we have David Mann. With more than 30 years of recruiting experience spanning retail, banking, telecom, aerospace, and now space communications, exploration, and Earth observation, Dave has led teams and recruiting activities across Canada, US, Europe, Asia, and Oceania. Dave's career has focused on some of the fastest growing companies in Canada and North America. In his current role as Director of Talent Acquisition at MDA Space, Dave's team has facilitated the addition of more than 3,500 employees, many of those that are here today, whether as a volunteer or as a student, well, maybe not employee yet, but interns, and close to 1,000 co-op students, of which many are here, over the past 5 years. At the same time, MDA Space Talent Acquisition Team has expanded their search for talent worldwide in the pursuit of the best space talent there is in the world, to bring them back to our country, to Canada, so that we can all benefit from it. So on that note, presenting our future in space, I would like to welcome to the stage our keynote speaker, Dave Mann. Thank you so much.
Well, thanks, Cyril. That was my presentation, by the way, so I'm done. But seriously, I wanted to take a moment and thank Adam for having us. This partnership we're really excited about. As Cyril said, you know, we committed to the next 3 years. Part of that commitment, by the way, is that we're paying all of the initial registration fees for you guys for the next 3 years as well. So that's pretty exciting. I also want to take a second. I know they're not here, or the team's not here, but there are some alumni here from Space Concordia. So shout out and congratulations to Space Concordia for, you know, I know we're still kind of waiting to see what the final results are of the launch on Friday, but regardless of what they did, it was a tremendously exciting and historic event for their launch. So we're going to get the, okay, perfect. All right. So, as you know, the presentation today is talking about the future of space. And as Cyril mentioned, we're doing a lot of stuff in space already. So I'm going to kind of talk about all the things that we're doing, but also talk about what's coming next, certainly from an MBA perspective. Before I do that, I'm just going to show this little video to get you guys hyped up a bit. And I've got a bunch of videos throughout because, you know, they say pictures are worth 1,000 words. I don't know what videos are worth, but certainly a lot more than my words. So we'll have some good content here. Oh, we don't have audio? Awesome.
No, well, a couple of them are, but they're up. We're at no joy.
How many engineers does it take in a room?
As with anything technical, something's always about to fail on us, right?
You have space operations, you have conference operations. It's all complex. We need like a robotic arm to do something in the back to help out, maybe.
Well, it's always the technology fails. When you're up here, standing up here with the spotlights on you.
Whoever fixes the volume first gets a free internship at MBA. This is the technical interview, but you don't know it yet.
Well, if we can't get it going, I guess I can kind of narrate some of them. But okay, like I said, we've got a few videos, and I think they all have audio. What's that? Yeah, you're yeah. Oh yeah, okay, you got it going. Just need some volume. Okay, so that's just a little primer to get you a little bit excited about space. Who's excited about space? Right. Okay, I wanted to start with a little bit of insight into the space economy, both in Canada as well as globally. And a couple of interesting facts here. You can see that the space economy in Canada is, as of 2023, is worth about $5 billion, not an insignificant sum of money. The interesting thing is almost a third of that is MDA. If you look at what our revenue is. So MDA is a big player in the Canadian space economy. In the 2023 State of the Space Economy report by CSA, they highlighted 3 areas that Canada excels in, right? One of them being satellite telecommunications, space robotics, and remote sensing. And coincidentally, or maybe not coincidentally, those are really MDA's 3 key business areas and things that we do well. So as goes MDA in Canada, I think goes our space economy. So some of you may have seen me talk before, and I like to talk about legacy, right? What we're doing, I think, is bigger than any of us. We're getting ready to go back to the moon. That's to prepare us to go to Mars eventually. And I think that if you put it in context of Apollo 11, the first mission to land on the surface of the moon, if you were part of that, if you or your parents or your grandparents were part of that mission, I think that would form part of your family legacy.
right? And the stuff that we're doing, I think, is going to be as good, if not, more impactful than that Apollo 11 mission. So, there's a real opportunity to form part of your legacy and do things that are bigger than ourselves. So, who is MDA? A couple things. We're 55 years in operation, and then if you kind of scroll down to the bottom here, in that 55 years, we've achieved 100% mission success, right? That's over 450 missions. We've got 40 years on orbit. We've never had a failure, right? So that's an impressive track record. We now have over 3,800 employees, right? So, we've grown 5 years ago, that was, 1,600 employees. So we've been growing at a rapid trajectory over the last 4 or 5 years. A couple other things I wanted to point out, 140 million square kilometers of the Earth's surface has been imaged through our Earth observation satellite system. And we have over 3 million hours of supporting Canadarm1, Canadarm2, and soon to be Canadarm3 in operation. So I'm going to talk a little bit about our lines of business. We have 3 lines of business. Our geointelligence business, which is based in Richmond, BC, and they do Earth observation missions. We design, build, and operate ground systems that will task the satellites, will take the downloads for those satellites. We do geospatial analytics out of our geointelligence business. And we're doing space domain awareness, right? So that's, where we're going to make sure that satellites don't collide or that, things aren't going to endanger the International Space Station, things like that. That's what we're doing right now. Moving into the future, we're moving into MDA Chorus, right? That's going to be the next generation of Earth observation satellites using synthetic aperture radar technology. Synthetic aperture radar lets us look through the clouds, lets us look through smoke on a battlefield, right? It allows us to even penetrate the ground if we wanted to. So I'll share a little video. Hopefully this one will work better for us. There we go. Thank you. And the cool thing about MDA Chorus is it's not just a single satellite, it's a 2 satellite constellation. So we'll have our initial satellite, which will be sort of, if you envision a wide field of view, then followed 60 minutes later by a satellite that has high resolution, smaller field of vision. So the first satellite will identify things that we want to look at, and the second satellite will focus in on those. Using MDA Chorus and our existing technology, we're able to do things like dark vessel detection, right? This is where we're able to spot the ships on the ocean, correlate them with transponder data, and we can find the ones that don't have transponders. If ships have turned off their transponders, they're probably doing something nefarious, something like human trafficking, drug smuggling, or illegal fishing. So we're able to spot those ships that have turned off their transponders, and we're able to send the authorities out looking for them. Next up, we've got our robotics and space operations business, and this is where we're doing space exploration and infrastructure. The $5 bill, the back of the $5 bill, you can see Canadarm2, which is currently, in operation on the International Space Station. We designed, we built that, and we help operate that out of both NASA and the Canadian Space Agency. Obviously, before that came Canadarm1, which was on the Space Shuttle program. And now we're building the next generation, which is Canadarm3. And Canadarm3 is it's going on the Lunar Gateway, and that's really going to enable us easy access to the moon and then eventually the lunar gateway that is going on is going to allow access to Mars as well. You can imagine the complexity differences between a robotic arm that's on the space station that's 400 kilometers above the Earth compared with the lunar gateway that's going to be 400,000 kilometers away from the Earth. It's going to be going around the dark side of the moon. You know, the International Space Station is crewed 24/7, 365 days of the year. The lunar gateway is probably going to be crewed for a third of the year, a quarter of the year, something like that. So it's going to have a lot more autonomous operation. The lag time, the latency, for signals to get back and forth will be measured in seconds, 2-3 seconds for signals to get back and forth. And round trip for a signal to come down to Earth and then go back up, a 4 to 6 second delay can be catastrophic when you're trying to dock a spaceship. So we have to have a whole lot more machine learning and autonomous operations built into that. So that's really the future. The MDA SkyMaker is what we're branding, what the technology that's coming out of that Canadarm3. We're putting that not just on the Lunar Gateway, but we're putting it on other products as well. So I'm going to start off, and this is a little bit of a long video, and hopefully this one's going to be YouTube, so hopefully it'll work all right.
In the 1960s and 70s, we made history. The world watched as NASA's Apollo program took humanity to the moon. From Neil Armstrong's first steps on July 20, 1969, to the final mission Apollo 17 in 1972. During the Apollo program, 17 missions were carried out, 6 of which successfully landed on the moon. The discoveries made there have become the foundation for our current space exploration. And now, more than half a century later, we stand on the brink of a new era in space exploration, called the Artemis program. But what is Artemis? The Artemis program is the successor of the Apollo mission. It's named after Apollo's twin sister, the goddess of the moon, symbolizing the effort to send not only men, but also the first woman and the first person of color to the moon. In 2010, NASA was tasked with developing a new program to go beyond Earth, with the goal of deep space exploration. In 2017, NASA announced the Artemis program. As the successor to the Apollo mission, with the ambition to return humans to the moon and establishing a sustainable presence. But this program goes further than just the moon. It aims to lay the foundation for missions to Mars. But why do they want to go back to the moon? Aside from being an incredible experience, they are primarily going back for scientific discovery, economic benefits, and to inspire a new generation of explorers according to NASA. They will build a global alliance and seek to explore deep space. To conduct long-term research on the moon and beyond, NASA plans to launch a new space station called the Lunar Gateway. The Gateway will serve as a stay for crewed Artemis missions and as a platform for scientific research in deep space. The first module of the Lunar Gateway, the Power and Propulsion Element, also known as PPE, is scheduled for launch late 2028, along with the habitation and logistic outpost. These will form the foundation of the station, which will be expanded over the following years. Before the space station is launched, there will have been 3 Artemis missions to the moon. The first Artemis rocket was already launched in 2022. On November 16, 2022, Artemis 1 was launched as an uncrewed test flight. It had the goal of testing the rocket systems and the spacecraft's performance. During this first mission, NASA also tested its latest rocket, the Space Launching System, also known as SLS. The SLS is the most powerful rocket ever built by NASA and is specially designed for the Artemis program. The SLS is capable of transporting astronauts, spacecraft, and heavy cargo into deep space. The rocket has two external fuel tanks that together hold 2.3 million liters of liquid oxygen and hydrogen, which power the main engines during the launch. These are 4 RS-25 engines, which were previously used in the Space Shuttle program. These engines are extremely reliable and powerful. On either side of the main fuel tank, 2 solid rocket boosters are mounted, providing extra thrust during the first phase of the launch. Together, this generates 8.8 million pounds of thrust at launch, surpassing the Saturn V rocket used for the Apollo missions. During crewed flights, the astronauts will be seated in the Orion spacecraft. Orion will transport astronauts to the Moon and beyond, and will return them safely to Earth. The next mission is Artemis 2, scheduled for late 2025.
That's now 2026.
This will be the world's first crewed mission, sending 4 astronauts aboard Orion on a journey around the Moon.
And Canada gets an astronaut on this mission because of the work that NDA is doing to support the Artemis program.
Space flights. Artemis 2 will not land on the Moon yet. After Artemis 2, the Artemis 3 mission is planned. This will be the first crewed moon landing since Apollo 17 in 1972. 2 astronauts, including the first woman and the first person of color, will land near the moon's south pole. Artemis 3 is currently scheduled for late 2026.
That's now 2027.
After these first 2 missions, the lunar gateway will be launched, but will be called as the Artemis 4 mission. After this, many more missions will follow.
And you can see Canadarm3.
And start the first research projects on the Moon and beyond. One of these projects is the Lunar Terrain Vehicle, which NASA plans to bring to the Moon during the Artemis 5 mission, scheduled for 2030. This unpressurized rover, designed for astronauts and spacesuits, will allow them to navigate the lunar surface. This is an unpressurized rover being developed for NASA that astronauts can drive on the Moon while wearing their spacesuits. With all these missions and research in prospect, they hope to one day be able to take a step towards Mars.
And MDA is currently working on multiple lunar terrain vehicles as well.
The Artemis program marks the beginning of a new era of space exploration. The ambitions are greater than ever. Not only returning to the Moon, but going beyond. It's an exciting time for space enthusiasts. What do you think of the Artemis program?
So exciting to be part of something that's going to be heading to Mars and really expanding our knowledge of space and expanding our knowledge of our solar system. I mentioned that we're also working on multiple lunar rover programs. Here's one of them that we're currently working on. This is called the Lunar Dawn, and this is going to be the Uber of the Moon. There's going to be a lot of commercial entities that will be operating on the Moon's surface, and they're not going to have the resources to build their own rovers and their own infrastructure. So NASA is funding this, but it will be available for rent by the day or the hour. It'll be autonomous or crewed. And you can see the Canadarm3, or the SkyMaker product on the back of the Lunar Dawn. I don't know if you can stop that. I think it's still running in the background. So that's kind of the future on our robotics and space operations line of business. And then we have our satellite systems business. That's based out of Montreal. By the way, our robotics and space operations business is based out of our Brampton office, which also serves as our corporate head office. Our satellite systems business based in Montreal, St. Anne de Bellevue. We are both building, we're priming new LEO constellation programs, as well as we're a merchant vendor for satellite subsystems, antennas, electronics, payloads, that sort of thing. I'm going to share a quick video from our CEO about how this world is changing, because it's really undergoing a rapid transformation, and I think he captures it better than I ever could. So what he's saying here is that we're going through a transformation from a geosynchronous, where a satellite is going to be 40,000 kilometers above the Earth, down to a low Earth orbit constellation kind of approach, where instead of having one satellite that's going to cover a third of the Earth, you're going to have multiple satellites. So if you think of it like like driving down the highway and your cell phone gets passed off from cell phone tower to cell phone tower. In this scenario, the satellites moving past us are the cell phone towers moving past us. I don't know that we're going to be able to hear Mike here. Sorry, Mike.
He has video minimized, and it's on autoplay. That's why you can't.
This one's got some audio too. Hopefully we can get a little bit louder. This is really talking about, so the future in this world is this product that we've developed called MDA Aurora, and MDA Aurora is really two different products. We've got a broadband LEO constellation product, and we have a direct-to-device LEO constellation product, and it's really, quite frankly, changing the way the world's going to communicate. Is there a volume on the player? This is an embedded video.
No, the second YouTube video you showed, you minimized it, and it's autoplay.
Gotcha. If we got audio back. And it's gone.
Routing tens of gigabit per second of data traffic, either locally or through the whole constellation.
We'll be getting a good laugh about this later on at dinner tonight.
Standards, and it's powered by a very advanced software that can manage thousands of users simultaneously.
So we're talking about software steerable antennas,
which basically is very efficient power-wise and also designed for high-volume manufacturing. The challenge for the D2B market is actually quite different. What we're trying to do is to close a link between a cell phone and a satellite that can be thousands of kilometers away. Our D2B product focuses on a DRA that is extremely large in diameter, such that we can effectively establish this connection with the user. In this case, our onboard processor is compliant with 3GPP standards, and particularly the 5G NTN standard. And eventually, we're preparing it to be compliant also to 6G standards.
So what this means is that we're going to be able to get direct reception on our cell phone no matter where we are in the world for voice, for data, for texting.
Efficient and high power, and also it's designed with high volume manufacturing in mind, which is at the core of the value proposition for both our products. Both the direct-to-device and the broadband products are actually driven by innovation and flexibility. So they are pushing the limits of what satellites can do.
It's not only about what our satellites do, it's how we're building them. When I started, we were producing one satellite every 2 years. Now we're working at producing 2 per day.
Did you get that? Going from one satellite every 2 years to
We're
2
working
per
alongside
day.
machine learning and robotics to create the building blocks that will allow us to develop an automated process and streamline every step. This automation means that we can build multiple constellations at the same time. It's incredible progress.
And several weeks ago, we just announced our 4th constellation.
We're not just connecting people, we're connecting industries, like agriculture and automotive, and devices of all kinds anywhere across the globe. The possibilities are endless, and this really is just the beginning.
So that's a little bit about the future in our satellite systems business. I'm going to play one more video for you, and then I'll wrap up. And this is really, I call this the goosebump video because every time I see it, I get goosebumps.
As you grew older, you started to put the pieces together and began making things of your dreams of life. We know because we are. We dream of a future where people and countries communicate and act on what we matter together. We dream of sending humanity to the moon and other worlds. And ensuring its safety back home. And as we put the pieces together, we will stretch all our eyes and learn to help it out. Give humanity the idea to predict radical changes that might put an end to our we gave the world a platform to communicate and collaborate as one. As one. Passion and innovation. Purpose and purpose. Learning, innovation, and progression. And we are just getting started. How far can you go? How far can you go? How far can you go? Because without people like you,
So on that note, I started off talking about legacy, and nope. I started off talking about legacy. I would suggest that what you guys are doing here is you're building a legacy, right? You're charting a path that future generations are going to follow in terms of, rocketry in Canada. What Space Concordia did this week, what you guys are going to be doing here this week is it's going to be, people are going to be building on what you're doing. MBA is doing the same thing, and we're here, and we've committed to being part of this for the next 3 years because we see you in us. And, we want, hopefully, to be having you guys come and work for us and be part of building a future together. So on that, show of hands for how many people in here either work at MDA, have worked at MDA, or are coming to work for us in the, the next 12 term. So a few people, mostly over in this section. Okay. Good.
I also have a question. Who here would like to work for MDA? It's pretty much the rest of the room. We've got 100% success rate.
All right. Well, that's it.
Thank you. Yes, do we have questions for MDA? I'm so sorry. Do we have questions for our speaker here? Yes.
And if I can't answer them, we've got a bunch of engineers in the room that can probably do a much better job answering.
Hi, is MDA giving $5 bill?
And I must say, if I can ask a question myself, every year when MDA comes, they announce this a new line of products, and I get surprised to see the production of satellites. And then, I see images of satellite production quite often on YouTube, and it's surprising to me to see you pan across the shop, and you can see the Canadian Quebec flag in the background. That's not a sight that we're used to see those satellites being produced in the foreplan. And so, can you explain a little bit how you're able to have such a high production volume in Canada, as I heard you went from 1 a week to 2 a day now, production of satellites? 1 every 2 years to 2 every day. How are you able to achieve that in Canada? Maybe in the microphone. Thank you.
Good question. The product that we've designed has been designed for manufacturability in mind. And then we've designed manufacturing 5.0 kind of technology that is going to help us automate, and we productized this Aurora product so that it's repeatable. We're not going out and selling a new version to customers. We might put different payloads in, to be able to figure it to what they need. But 90% of what we're selling to each customer is the same thing. We get really good at making that really fast and inexpensively. It drives the cost down and it changes the economics of satellite communications.
Amazing. And it increases Canada's footprint in space. Do you have any other questions for our speaker?
Oh, hi. Thanks for your presentation. It was very insightful and inspiring as expected. Just wondering about the satellites and what bandwidth, how many satellites MDA is expecting. Are you owning the satellites or do you build them for others? And can you tell us about the constellation and bandwidth?
Okay, I'm gonna ask the group over here. Anyone can talk about bandwidth to put up your hand, but I'll answer the other questions first. Currently we have multiple contracts. Typically we have, with these contracts, we'll have an initial contract, we'll have options for additional satellites, etc. But just the most recent one that we've signed up for, we signed up for an initial group of 100 satellites with an option for another 100 satellites. But EchoStar is planning on building out to 1,000 satellites eventually. So, the initial numbers might be in the 500, 600, 700 range, but it's those follow-on orders that could grow into the thousands and tens of thousands.
And I assume you're not launching anything from Canada yet. Is your ambition to launch from Canada?
I think my understanding, and again, if any of the engineers have better response to this, my understanding is the launch inclinations coming from Canada will be very specific. So possibly if we need, a launch inclination that is only available from Canada, we would. But at this point, I think most of our launches are happening from the US.
Thank you so much.
I think we have some engineering answers, so I'll pass it on over here.
Yes, and only to complement exactly what was brought up. So for some of the frequencies they're going to be using, it really depends on the client or what type of payload that we're carrying. So we can go equally for something like C-band or something like K-band, or equally. And for launches specifically, it's really also depends on the client for where their specific satellite, whether it's going to be LEO, MEO, or GEO, where that satellite is going to end up being, where it's going to be launched is going to majorly affect their costs and everything. But it is for sure an impact that if launches in Canada could happen, would be a major effect to them and also to us in the types of proposals that we can bring to them. So that's for sure something that would be beneficial for everybody.
And sorry, you asked one question about whether we own the satellites or in most cases, certainly the communication satellites, we will not be the operators. We're selling them to satellite operators. But in case of geo intelligence, the CORUS satellites, for example, we will be the owner and operator of those.
Any other questions for our speaker?
Hey there. I've got a question relating to how satellites are maintained in orbit. So right now, at least from the SpaceX side of things, I know that they typically they just deorbit their satellites at the end of their lifespan and or supplement the fleet with additional satellites as needed. Do you think there'll be a point at which repairing and upgrading satellites in orbit will become more cost effective than simply setting new ones up?
100%, and that's a business model that we are actively working on, either to go up and repair, refuel, or potentially deorbit those satellites. We are working with a couple different providers that are looking to do just that. What I will say is Elon has the luxury of free, relatively free and unlimited launch capability or capacity. So, he's building more disposable kind of satellites. The rest of us have to, maybe think about things that are going to last a little bit longer.
Thank you.
Thank you. I do have a question related to part of your presentation where you mentioned that robotics and the space exploration part of the business was based in Brampton, and then the satellite communication business was based in Quebec. If I am a student and I'm interested in doing a little bit of both, involving myself in one part and then evolving my career to another part, is there the ability at MDA for me to eventually work on both?
We are getting much better at doing that. We share engineers across the organization. It's something that we've struggled with historically, but we're starting to see more and more of that happen. And, we have career portals for internals that they can see everything and they can apply if it makes sense and if it's something that they're interested in.
So there's an option to start your career, but also evolve your career at MDA and do many things in one same company.
100%.
Do we have any other questions for a speaker? Okay.
First of all, thank you for the presentation.
You're welcome.
Taking into account the effort that MDA is doing into the unification of the international knowledge, as being part of the Artemis program as well. Does MDA have any plans of expanding operations outside of Canada, the US, or the United Kingdom as well?
Yeah, very good question. We do have operations in the U.S. We have a group in the U.S. that supports Canadarm2 on the International Space Station. They're based down in Houston, as you might expect. We have existing businesses in the UK, and we've just purchased another business that operates in the UK, Bulgaria, Israel, and they also have an office in the US as well. So we are expanding globally. We expect that to continue. We expect to see, additional growth, in all parts of the world, both organic and non-organic.
I would like maybe to ask another question of something I heard recently, and I want to confirm. I heard that the Canadarm operations are now, for the last couple of months, have been based in Canada, something that has historically been done in Houston in the US. Is that a true statement?
It's a true statement other than the last couple of months. It's CSA in St. Hubert has long been a backup site for Canadarm2 operations. What is happening is we are also building out, primarily for Canadarm3, we're building out a mission control center in our Brampton office where we will be running mission operations for Canadarm3, as well as the commercial versions, the Skymaker products on commercial space stations, commercial vehicles, etc.
So if I join NVA as a student or as a full-time employee, I can design, fabricate, and operate spacecraft?
Potentially, yeah.
That would be wonderful. So maybe one more question. If I'm a student and I want to join MDA to do any of the three, how can I do it?
Linda. Stand up, Linda. Linda Priest here runs our campus program. Her and one of her colleagues in Montreal. And Linda would be the person that you could reach out to. And you can check us out on mda.space/careers as well. But Linda, if you want to.
Yeah, sure. I can just add something. I mean, I have had the pleasure of speaking with many of you already over the course of today and yesterday, but really our cycles for the recruitment are kind of constant. Like as soon as we start, or we have our full student start, then we will start hiring for the winter, and that continues like that. So really, if anyone has an interest, please know that we are on our own portal where we have a co-op specific part to the career website and also on the university portal. So come and talk to us. We are also tomorrow still here for the launch. So if you have a chance to chat there, once we wait for the next rocket, then we also happy to chat with all of you.
And by the way, we are hiring now at a pace of about 270 co-ops per year. So lots of opportunity. We're always looking for the best and brightest, which is why we're up here.
And I think that is a perfect way to end it today. Everybody, please give it up for Dave and for MDA Space. Okay, so with our keynote speaker now concluded, this brings us to my last comments. I have two more things to say. First, I'd like to thank our sponsors one more time, without which this would not be possible. And that's a nice segue because the first people I have to thank are the front row. So thank you, MDA Space, for supporting Launch Canada, making this possible, and also giving an output for all these students that then want to lead a career in aerospace engineering. So thank you very much. Thank you for Timmins and Metagami First Nation for hosting us. Thank you for Maverick, Pratt & Whitney, Softenway, our Escape Velocity sponsors. Thank you for Discovery Porcupine, MagFab, Logistic EOS. Thank you for Nord Space, Fuzia, ICOM, Delcom, Randing, Marotta, Astos. Thank you for all of our ground control sponsors and everybody else that has made this possible. Thank you to our volunteers as well. And thank you for the entire crew of you, the students, and the other people that are taking care of the arena for being here today and making it such a success. Thank you very much. The last thing I have to do is just plug our YouTube channel. You know, not everybody here might be able to attend the launches, might have other tasks. If your parents at home want to participate and be part of it, if your friends want to see you launch a rocket or not launch a rocket, depending on how it goes, hopefully it goes well. Please go on our website, go on our YouTube channel. The live stream is excellent, I must say. And it's always better, like the F1, to watch it online than to watch it on YouTube. But then you have two more things to do. I'm done for the day. If you have some time and some hands, I'm not done because we would really appreciate it if you can help us tear down the arena. You know, it took 2 days to set up. We have an afternoon to tear it down. If you have some time, we would appreciate it. And the last thing you have to do is to have fun, to launch some rockets, to launch Canada and launch the North. So everybody take some pictures, have fun, and make us proud. Thank you very much. And let's go launch some rockets.